identity. And Wittgenstein will completely trash everything that we're doing today. We'll see. Tears. All right, any questions before we launch in? Yo, what's up? We got 5 people. This shit cray, you know, and Owen and Camille might show up too, so that would be better attendance than some non-Thanksgiving classes, right? So honestly, I really did consider ordering, hey, yeah, gang's all here. So yeah, I really did consider ordering a turkey suit, and some of them were legit really hilarious. I mean, I'm totally gonna do this in a future year. There was one, it's just, I'm gonna do this hands down, people having class on turkey suit. So the way it works is you step into the legs of the turkey, but then on the back of this inflatable turkey are fake legs, and there's a man riding the turkey. So it looks like you're riding it looks like you're a turkey that some dude's riding you. It's just hilarious. So I'm gonna do that, but it wouldn't arrive in time. So.
Would you consider doing the Easter Bunny for Paradox and Infinity next semester?
Whoa, yeah. There's probably thank you. Yeah, there's probably a really structurally analogous Easter Bunny costume, and I just think it's so funny because then it seems like you're like 2 things walking around, and so you'd be really poofy and you'd be like, you know, writing on the board or something. It would just be, it'd be hilarious. All right, so. But, you know, true statements in the world we live in today, there is exactly one hero. We don't know who that hero is. There is exactly one. So the way that we schematize this is we say, of course, that there's at least one hero, and then we say it's not the case that there is at least some other hero. So it's not the case that there is some y, but the y is also a hero, and y is distinct from x. So another way you could do this, and I think this is the way I normally do it, is to use a for all statement. So you say, there is at least one hero, and for everything else in your domain of discourse, if that thing y is a hero, then x is equal to y. So this is how you get, there's exactly one hero. I think honestly on Monday we probably handled uniqueness, and this is the same. I gotta do full screen this sucker. So, and this is basically the same as if, you know, the uniqueness statement. So, and uniqueness is really important. We'll see the last thing that we learned how to schematize today, once Ben Q is done analyzing our display capabilities, is definite descriptions. And definite descriptions will rely on our ability to schematize uniqueness. So, in general, if you're talking about some property A, remember A can be really complicated. So A wouldn't have to be a single predicate, it could be, you know, this very complicated property. You'll just say, you know, G is the thing that is an A, and for everything else, if that thing also has the property A, then that thing's equal to G. Or, you know, in a shorter form, for all the things, Y has the property A if and only if G is equal to Y. And again, you know, we typically won't have like free constants floating around. We'll typically have everything bound. But here, you know, if you're talking about a specific thing, like Greta, then you'd be saying Greta has property A uniquely. Any questions on this? Cool. All right. So you could do exactly and many things, and so you're going to introduce and many bound variables x1 through x of n, and then you say that all these things are distinct from each other, and then you say they all have the property in question. So each of these n distinct things has the property A, and then you say for everything else, if that thing also has A, then that thing y has to equal one of these x of 1 through x of n. And so this is how you would schematize their exactly n a's. Everything in here is bound by these existentials. You see our mega big opening parenthesis, our mega big close parenthesis. Now another way you could do this would be slightly shorter is, if you really wanted to, you could kill this line and you could replace the if-then symbol with biconditional. And you're basically saying, here are my n distinct things, they're all different from each other. It's not the case that any one is equal to the other. And for everything in the domain, that thing has the property A if and only if that thing is equal to one of these sentences. So that would be a little bit shorter. But in general, I don't know, I always think about it this way with my little if then. So get used to the if then, and then somebody comes along and tells you a way to save a line, and you're like, screw it, I don't want to save a line. I got all the ink in the world. This isn't real ink. This is computer ink. All right, so yeah, and you could make the property A more complex. Here's a simple example. There are exactly n things that are B's and C's. You would just do this pattern, replacing the A with, B. So this AY would be parenthesis BY and CY. Cool. Exactly. So there are at most NAs. The easiest way to do this is just to view it as the negation of there are at least n plus 1 things. So if somebody says to you, there are at most 2 A's, they're saying it's not the case that there are at least 3 A's. That's basically what's going on. So it's kind of similar to, I guess in probability, somebody's like, what's the chance that you get at least 1 heads? You calculate the probability of getting no heads, and then do 1 minus that. So this is like a similar idea. So basically we're saying that there are at most n things, less than or equal to n things that are property A. This is the same as it's not the case that there is greater than or equal to n plus 1 many things that are A's. So if you're going to do at most 2 heroes, you're saying it's not the case that there are at least 3 heroes. So we know how to do at least 3 heroes. That's the thing. That's this whole expression without the negation sign. You're saying introduce your 3 bound variables. X is a hero, Y is a hero, Z is a hero, and it's not the case that X is Y, and it's not the case that X is Z, and it's not the case that Y is Z. So this thing would be there are at least 3 heroes, and then for there are at most 2 heroes, you just negate that. It's not the case that there are at least 3 heroes. That just means there are at most 2 heroes. So another way you could do that would be with the universals. You're basically saying for all triples of things in my domain, if each one of those things is a hero, then at least one of those 3 things has to equal some other thing in that triple. So this also says that there are at most 2 heroes. And you could get the second thing by pushing through this negation symbol, doing the quantifier conversion, they would end up being equivalent. So whichever one you prefer. Me, conceptually, I don't know. I think about this first one. This one comes more easily. I just think, okay, there's at most 2 heroes. I think it's not the case that there are at least 3. I can do at least 3. That's really easy using existentials, and I'm just negating that. So I find that easier to remember. But maybe you prefer the universal approach. And again, we could, figure out how to write this for arbitrary many, at most n things. Cool. All right, so then we'll do, so we did all the numerical stuff. So we can, we can count, basically, with our predicate logic identity. So, yeah, counting. So now we'll do both and neither, and then we'll do the definite description. And then we'll basically learn how to schematize all these different kinds of sentences. Isn't that why we're here today, to schematize sentences? So when somebody says both heroes inspire, what this means is that first there's exactly 2 heroes, so that's a key thing to remember, because you might not get this intuitively off the surface structure of both heroes inspire, but it's making a strong numerical claim that there are exactly 2 heroes. That's implied by both heroes inspire, and those exactly 2 things have the property, namely they inspire. So we know how to do exactly 2 heroes. We're just saying there is an X, there's a Y, and it's not the case that X is Y, so these things are different. So right now, at this point we've done, there's at least 2 heroes. Now we have to tap on to get the exactly for everything in the domain of discourse. If that thing is a hero, then the thing is either X or it's Y. So now we've done exactly 2 heroes, and then we just have to, so we're still in the scope of our mega parenthesis, everything's in the scope of these existentials. We just have to say these 2 heroes inspire. So IX and IY, where capital I will be our inspirational predicate. So IX and IY. So we're just saying, first, there's at least 2 heroes, then we tack this on, okay, there's exactly 2 heroes, and those 2 heroes have the property of being inspirational. So when you say both heroes inspire, this entails that there are exactly 2 inspiring heroes, but not necessarily vice versa. So you could imagine models that had exactly 2 inspiring heroes and had a bunch of other heroes who sucked, and those heroes were not inspiring. Then it would be true that there are exactly 2 inspiring heroes, but it wouldn't be true that both heroes inspire, because both heroes inspires implies that there's exactly 2 heroes. So, for instance, if you had exactly 2 inspiring heroes, but then you had some other not inspiring heroes. And remember that to say that something is not inspiring does not necessarily mean that it is uninspiring. And so in your guys' evaluations, of this class, if you write, the class was not inspiring, I won't be that offended, because that doesn't mean necessarily that I was uninspiring, right? Now, if anybody says that I was uninspiring, I'm going to say, you didn't come to class enough, because, we read some Wittgenstein, and that at least was inspirational, right? So, we can count on that. Any questions about both? Cool. All right, so now we can do neither, which is similar. So neither or neither hero inspires. This means, again, that there's exactly 2 heroes, and now neither of them has the property. So it's structurally very similar to both. You're basically, you're saying, again, there's exactly 2 things. So that's these first 2 lines here, there's at least 2 heroes. And for everything else, if it's a hero, then it's one of those things, X or Y. And also, it's not the case that X inspires, and it's not the case that Y inspires. So. Cool, all right, definite description. So this is a particularly fun thing we can do with logic, and before people really got comfortable with predicate logic, they thought that something like this, the definite description, wouldn't really be captured via logic. So one of the, early, you talk about like low-hanging fruit papers. In early 1900s, Bertrand Russell published a paper in a good philosophy journal on the definite description, basically just showing you could schematize as part of language using predicate logic. And it's like, honestly, pretty trivial. But that's what low-hanging fruit is, right? You just have to be the first one to pluck it. Yeah, I wonder how much this kind of thing motivates students to work in like new and burgeoning fields, because you just think, well, the younger a field is, the more likely it is to have low-hanging fruit. The older a field is, you could go work in like atomic spectroscopy, right? But people have like done that to death. Similarly with classical mechanics, like you could still work in that area, but it's like, they pretty much figured it out. All right, so what are definite descriptions? We're just saying the so-and-so. So if you guys say something like the instructor of 24.241, that's a definite description, and it refers to me. I am the instructor of 24.241, but not for much longer. So are we happy about that? No, I love this class. I'm going to miss this class. So I would do this class my whole life. So we want to give an analysis in particular of when we predicate something of a definite description. So if you guys say, the instructor of 24.241 is my favorite instructor, that's a thing you might say. Then you're predicating a property of that person. So we're saying that there is something, which is A, of course. And this is the key thing that you're likely to forget. We're saying it's the only A. So we're saying there's a unique thing that is A. This is really the linchpin of Russell's analysis, that when we say the A is B, we are asserting this rather strong claim that there is a unique thing that is A. And then finally, we're saying that this thing, the unique thing that is A, has the property B. That would be our predicated method. And so we can schematize this in our quantifier logic. We're saying there is at least some x such that x has the property A, that's this part, is A. And now we do the only part, the uniqueness, which we've done a lot. So for anything else in our domain of discourse, if that thing also has the property A, then that thing has to equal x. So at this point we've done, there's a unique thing that's A, and then we just say the unique thing that's A has the property B, so Bx. And this is our analysis of the definite description. So it's really not something new to memorize per se, because we've already done, uniqueness claims, and we're basically we're just understanding that whenever you see the, in front of something, you're thinking, okay, this is going to be a definite description. I'm going to assume there's a unique thing that, has that property, and then I'm going to predicate some further thing of that thing, x, once I've said x is the unique thing. So this is, it's a schema, it can get pretty complicated. So at least one of the practice problems, I think not a homework problem because I took Mercy upon you guys for Thanksgiving break. At least one of the practice problems with definite description is legit pretty convoluted to get it into this form. But it is in this form. It's just, shouldn't be complicated. So again, you could save a little bit of space by using the biconditional, and you could say, there's at least some x such that for all y has the property A if and only if x is equal to y, and also x has the property B. And then we just compress this part into our little biconditional. So, but again, I was brought up as a horseshoe man, and I will continue to think about this in terms of horseshoes, and not the biconditional. But you guys are young and impressionable, so maybe 20 years from now when you're schematizing definite descriptions, and you won't be, but All right, so, we got in, late last night, I was thinking of the author of Waverly. This is the classic example. Got this in the slides for my future self, because I figured I'd probably bullshit about this anyway, so I was like, let's put it in. So who is the author of Waverly? Well, the author of Waverly, this is a definite description. It presupposes that there is a unique person, unique author who wrote Waverly, and now we're ascribing to this person the property of being Scottish. So you might be thinking, what the hell is Waverly? That's a good question. That's what Wikipedia's for. Waverly is a historical novel, and it was written by a Scottish poet and novelist, and it seems as though this poet, he was established as a poet, and he took a risk into writing novels. And he wasn't sure if, it would suck or not, so he published it anonymously. And that was his first novel, Waverly. And it was good. It was well received. But he still was not confident, and so in subsequent novels, he published the novels under the definite description by the author of Waverly. And so I think this is partly why Russell used this as the example, because someone was going around publishing books using a definite description. So it's a really good example of a definite description, You could basically give up your name, and you could just figure out a good definite description for yourself. I guess what we had a musical artist, Prince, who then changed his name, and people would refer to him as the artist formerly known as Prince. Another good example of a definite description. Yeah. All right. So here's our symbolization key. Capital A for X is an author. Capital WXZ for X wrote Z. Capital S for X is Scottish, and lowercase l for Waverly, which is an object in our domain of discourse. So this domain of discourse includes authors and at least books. So try to schematize this. The author of Waverly is Scottish. Please think about it. Anybody need scrap paper? I'll make sure I take attendance, although I think I can probably just remember. Oh, And again, if you guys end up with any hardship relative to the problems at deadline, just feel free to get in touch. I will be very lenient in your cases because you came to class the day before Thanksgiving. Okay, so we're saying that there is somebody who's an author at Waverly, so that's the first part. And then we're saying that's a unique thing. So we're saying for anything else, if that thing is an author at Waverly, then that thing Y has to equal the first thing X. And furthermore, that first thing X is Scottish. That's what we're saying. So there's at least one thing X such that X is an author, and X wrote Waverly, and for anything else, if that thing's an author and wrote Waverly, then X is equal to Y, Y is equal to X, and also X is Scottish, and the whole thing's in the scope of our existential. And any part that has a Y in it is in the scope of the for all Y. So the parentheses that really matter are this one and this one, keeping the Y bound, and these outer ones keeping all the X's bound. Any questions on this? Any questions about the definite description? All right. Oh, okay. We have some more stuff. The versus exactly one. So this is definite description. The hero inspires. We're saying there's a unique hero, and that thing inspires. Contrast this with the sentence, there is exactly one inspiring hero. These are different sentences. So there's exactly one inspiring hero means there's at least something that's a hero, and for all the Y's, if Y is a hero and Y is inspiring, then X equal to Y, and also X is inspiring. I guess, to make it easier conceptually, I should move this and IX to be right after here. Doesn't make a difference, but intuitively what we're saying is there's at least one thing that's a hero and is inspiring, and for anything else, if that thing is a hero and inspiring, then it equals the first thing. And so these are, they have different forms, and these are not logically equivalent to each other. So to show that they're not logically equivalent, you just come up with a counter model. That makes one true and the other false. So we can make the second one true without making the first one true, kind of similar to previous example we talked about. When there's exactly one inspiring hero, but there's also some non-inspiring hero, then it would be true that there's exactly one inspiring hero, but it wouldn't be true to say the hero inspires. Because again, the hero inspires entails this uniqueness claim that there is a unique hero. So when you say the hero, you're meaning there's exactly one hero and nothing else in my domain of discourse is a hero. Whereas when you say there's exactly one inspiring hero, you're saying there's a unique hero that is inspiring, but there could be many heroes, just, who aren't inspiring. Subtle distinction. And that's what this class is all about, right? Subtle distinctions. We are logic chopping. So it's very controversial, this analysis of definite descriptions, and probably by the lights of most linguists, it has been convincingly refuted. But nevertheless, we talk about it because it's a great illustration of the power of our quantifier logic. And it works in a lot of cases. So it's kind of, in contemporary guys, it's been replaced by presuppositional theories. And I guess in a sense, these go back to Strawson. So this also is like a pretty old idea. So on Russell's view, if you say something like the hero wears a cape, well, this is false if there's no hero or if there's more than one hero. And some people just don't find this intuitive. This is maybe one of the examples that motivated Russell, so maybe Russell thought this was a good making feature of his theory. There is no present king of France, where we might say something like the present king of France is bald. If you want anything that is a sentence in QL to be either true or false, you need to say this is either true or false. This is going to be a sentence in quantifier logic. Well, there is no present thing in France, so it seems more natural to say that this is false. Nevertheless, you might think these are the wrong truth conditions. You can give lots of arguments for that. There's just many counterexamples, many different kinds of counterexamples of Russell's theory. And so you might instead think that these definite descriptions, relative to the uniqueness claim, are really doing something like the following. They are presupposing, when we make the statement, we're presupposing that there's a unique thing. And that's just in the background of our presupposition, but it's not part of what the sentence says. It's not part of the content of the sentence. It's just something that we take for granted in making the assertion. So, but again, as always, we're not doing linguistics here. I had a fun discussion on Monday at a philosophy of language reading group where they were giving us semantics for preference statements, like I prefer, I guess, dark chocolate to milk chocolate, and you give semantics for that. And the semantics presuppose a best relation, and it presupposed an ordering on things. And I was like, well, how could this possibly succeed? What's in question here is, the notion of best, and what's in question is this ordering. And the language people were like, oh, Hunt, ever the philosopher, the aim here in semantics is not to give a reductive account. The aim is to construct a theory that saves the truth conditions, as observed by ordinary speakers. And I was like, this isn't philosophy. But it was illuminating. All right, so I guess one final distinction that is important, this is on the problem set, I think, is singular possessives versus plural possessives. So another context where definite descriptions are frequently used is in singular possessives, like when you say something like Joe's Cape, or when you say the philosophy department's library's copy of Wittgenstein's The Philosophical Investigations. I was going to bring my own today, but then I realized that the philosophy department has a copy, and I would save myself the hassle and also the risk of, I put this thing in a bag that was a very dirty bag. I almost could have put my beloved investigation in that as well. And I would have been very sad. So when we say something like, the instructor, you could embed these things. Yeah, the instructor of 24.241 coffee canteen. That would also be a definite description. So when you say something like Joe's Cape, you're really just saying the cape that Joe owns. So if we had some more complex sentence, Autumn wears Joe's cape, then this is equivalent to Autumn wears the cape that Joe owns. This is clearly a definite description of the cape that Joe owns. And so we'll just treat it like we have been treating it. There is something such that that thing is a cape. Capital G was the cape predicate. J for Joe, Joe owns that thing. And for everything, if that thing's a cape and Joe owns it, then that thing's equal to the first thing. So here we've done the uniqueness part, the unique cape, the unique thing that is a cape that Joe owns. That's what we've done. And also, Autumn wears that thing X. Autumn wears that cape. So this is how we would schematize Autumn wears the cape that Joe owns. Hopefully intuitive. Just think about the meanings of the sentences. Then you don't really have to memorize anything. So in contrast, plural possessives, when we're like, those are like everybody's things, many people's things. So like Joe's capes, So Autumn's wears Joe's capes. This is not a definite description. So we're saying Autumn wears every cape that Joe owns. So we're saying for all the X's, if X is a cape and Joe owns that thing, then Autumn wears it. And this has nothing to do with uniqueness. We're just, Autumn wears Joe's capes as Autumn wears every cape that Joe owns. And so this is even simpler. Plural possessives are not definite descriptions. That's the key thing to remember. Cool, all right. So we've done all the schematization stuff. And I guess now what we'll do, I say, just to make sure we get through it and to reward you guys for good behavior, let's jump to the homework questions. Do some of those, then we can do some of the practice questions. Which honestly, some of the practice questions are harder, I think. The homework questions, whose fault is that? That's my fault. And then I'll hopefully read some Wittgenstein to you, some pleasing therapeutic Wittgenstein. And if we're really killing time, then we'll do the donkey sentence thing that I mentioned last time. So we'll talk about that, which is illuminating. Another thing where we run headlong into linguistics and we just say, nah, basically. All right, so you have auto checker on all of these except the last 4. So let's do the last 4, right? The other ones, I think you can at least try out many different things until you get it correct. So Mars has 2 moons, and again, the claim here is 2 moons just means at least 2. This is the stipulation that we're making. In general, this is an ambiguous claim, and in some contexts, it probably would mean exactly 2. But we're stipulating that when we see sentences like this, asserting, there's n many blah, we're reading them as at least n many blah. So try to schematize Mars as at least 2 moons. Oh yeah, this is our domain of discourse. It's celestial objects in our solar system of discourse. We have asteroids, moons, planets. OXY is X orbits Y. Mars is little m. There's a little I for Io that's relevant for some problems. And we have a larger than relation. So we're thinking at least 2. So we're going to start off with 2 existentials. We're going to have a mega opening parenthesis where everything else we write will be in the scope of these 2 existentials. Now, one thing you're liable to forget is we want to say at least 2. So you have to say these 2 things are distinct. So you have to say it's not the case that X is equal to Y. And then you have to say that these 2 things that are different have the relevant properties in question, namely they're moons, and they're moons of Mars. And so to be a moon of Mars, you have to orbit Mars. So we're saying X is a moon and X orbits Mars, so that's capital O, XM. And then we're saying Y is a moon, and also Y orbits Mars, so capital O, YM. And then we're like, is there anything else in the content of this sentence? Mars has 2 moons. It's like, nah, I think that's it. So then we check it. And I can check it because I am in the instructor's version. So you guys can't check it, but I've checked it for you. And we assume that my carnap is the same as your carnap. But what does it mean to say that my carnap is the same as your carnap? That's a question about identity. Any questions about this one? Super chill. Cool. All right, Mars has at least 2 moons, or sorry, at most 2 moons. So try to do this one, which is, at least slightly more exciting. None of this is really exciting, right? When instructors in a class say that such and such is exciting, what they really mean is, I'm getting paid mad money to teach this shit. I'm getting a raise next semester, so that's pretty dope. I was already happy with the amount of money I was making. Okay, so how do we start this one? Ray volunteer to join?
I just took out the part where it says that x cannot equal y, and added a part where it says that if it's a moon and it orbits, it has to be one of x or y.
Oh, okay, cool, yeah, let's try that. So are you using the biconditional thing?
No, I just did like the horseshoe, but
Oh, horseshoe, okay. Because I think there's probably a way to do this with biconditional. There's an x, there's a y. Oh, but that's so, So your thought is do this, and then what do we add after?
and then I said like for all z, if you know mz and ozm, then it has to be z is x or z is y.
Okay, yeah, let's try and see if this works. It's not how I was thinking about it, but we can try stuff out. So for all z, if mz and xz, then z is equal to x, or z is equal to y. So I think looking at this, that this is the way that we would schematize. Normally, so if we want to do there's exactly two moons, then we would write this and we could keep in the not identity thing. Your thought is, well, we're not necessarily saying that x and y are distinct. So yeah, I feel like this should work. And we got all of our, let's see, I missed the parenthesis, so I needed one final closing parenthesis for the initial ones. Let's see if Carnap says, all right, so Carnap says no. But that's not, just that Carnap says no, in this case, I think Carnap does sometimes screw up these kinds of identity things, so it is possible that this is logically equivalent. It is not how I recommend you guys solve these things in Carnap for this reason. But if I had a human grader was grading this and I thought about it, I'd be like, yeah.
Doesn't there have to exist at least a moon?
Mars has at most two moons. Yeah, good question.
The issue might be that technically it would be right if there's no moons, but here we're stating that there's at least a moon.
Yeah, are we saying that there's at least? So if I said Mars has at most two moons, I think that would be true even if there wasn't a single moon of Mars.
Yeah, I'm saying
I see. Oh, we're here. Okay.
That,
Yeah. So this is our counter model for equivalence. Thanks, Manny. So this sentence is true only if there is at least one moon of Mars, but Mars has at most two moons is true in models where Mars has no moons. Yeah. Cool. So this one will not work. So I think what I recommend you guys on these at most questions is just to think about your negating the next number, at least the next number. So Mars has two moons is the same as it's not the case that Mars has at least three moons. So then we can do Mars has at least three moons, and we're basically saying, so we'll do that first. Mars has at least three moons. We're saying these things are different from each other. It's not the case that x is equal to y, and it's not the case that x is equal to z, and it's not the case that y is equal to z. And each one of these things is a moon of Mars. Okay, so this would be, there are at least three moons of Mars. At least three things that are distinct. Each one of them is a moon and it orbits Mars. And now we're just saying that's not the case. So to say it's not the case that, you just negate something. So not the case that, blah, blah, blah. Let's see if this works. Yeah, all right. So this one totally works. And again, you could, if you wanted to, do three universals. You'd be saying something like for all x, for all y, for all z. You'd say x is a moon, x orbits Mars, y is a moon, y orbits Mars, and if z is a thing that orbits a Mars and is a moon of Mars, then z is equal to y or x. Basically something like that. Cool. Any questions about this one? All right. There are exactly 2 moons with an atmosphere. So the goal here is to say that there's exactly 2 moons that have an atmosphere. Yeah. So I'll let you guys try to start this one as well. All right. Anybody want to get us started on this bad boy? Exactly 2 moons with an atmosphere. If anything else is a moon with an atmosphere, then it must be one of these 2 things. That's the key thing. So first off, we're saying, of course, that there are at least 2 moons with an atmosphere. So that's the easy part. To do that. So to do at least 2 moons, we're saying these 2 things are different, so that's not the case at x equal y. And x is a moon, and y is a moon, and x has an atmosphere, so atmosphere is T. So we used A for asteroids. And so now at this point we've done, there are at least 2 moons with an atmosphere. Now we have to get the exactly. And so to get the exactly, we're saying, imagine there's something else that has the property in question, namely a moon with an atmosphere. Then it must equal x or y. So we're saying, for anything else, for all z, if z is a moon and z has an atmosphere, then z is equal to x, or z is equal to y. And so then we close our consequent, and then we close the scope of this for all z. So that's our second parenthesis, closing this guy. And then we close the outermost parenthesis, the scope of the x and y. So the tricky thing, for a question like this is really just to get the parentheses right. That when you introduce this for all z, you have to introduce a new parenthesis for that. Every time you mention a z, it's got to be in the scope of that thing, bound by that. And now we're like, okay, we're in an if-then statement. If-then has an antecedent and a consequent. If it's a complex antecedent, it has to be in parentheses. So that's where these parentheses come from. And then similarly, if the consequent's complex, it has to be in parentheses. So these parentheses matter because in general, things don't commute with conditional. Whereas you see in problem 10, we didn't have to be sticklers with all of our parentheses with these ampersands because ampersand commutes. And so, technically, this is technically what I wrote up here, missing a ton of parentheses is not even a well-formed formula of QL. But Carnap accepts this kind of thing because it's, we have a convention for understanding this as a well-formed formula. It's really, every time there's a pair of conjuncts, they get parentheses, so you could go through and you could systematically tack on parentheses like this, and it would be a monster expression, you don't have to do that. But these parentheses matter for if-then statements. All right, any complaints about this before we trust it and check it? All right, let's go. Yeah, cool. So that's how we do exactly 2 moons with an atmosphere. So something that you might have missed is we're not saying and for anything else that's a moon, it's X or Y. We're saying for anything else that is a moon that has an atmosphere. There could be, as far as this statement is concerned, there could be moons that don't have atmospheres that are different from X and Y. This sentence is saying there's exactly 2 moons with an atmosphere. Any questions about this one? All right, let's do our definite description. So Earth's moon is larger than Mars' moons, and we have a mega hint here for ourselves and our posterity that singular possessives get treated like definite descriptions. So Earth's moon is the moon of Earth, and we handle that using our Russell theory. And this plural, Mars' moons, this is not treated like a definite description. Plural possessives not. So try to give this one a try. Oh yeah, and here's our schematization key. And yeah, I guess if you're done with this one, feel free to move on to our practice problems for this week. We'll probably do, we might just stay on definite descriptions and do, this one's really, really convoluted. 11.6b. The smallest planet has no atmosphere. Little circles get really dusty. Maybe a little bit. This is the kind of thing, if you guys are ever designing things, think about where dust can collect. People try to design fancy shit, they don't think about that. And then, just imagine that this room needed to be dusted. You would have to design some little peg device with little dusters on it, sit them into the pegs and pull them out and dust it, right? Otherwise it's like that. This is how I feel about Sterlite crates. You guys ever have a Sterlite crate, for bathroom stuff? It's a plastic crate, molded plastic, just bad for the environment, it's like petroleum downstream product. But there's just all these little molding things, and so just dust collects everywhere. And it's like, to clean these things, it's like,
What is it used for?
Oh, it's just like a crate, kind of like a milk crate
Oh.
kind of thing, yeah. So just like to store stuff, but not great design. Okay, Earth's moon is larger than Mars' moon. So we're thinking the moon of Earth is larger than Mars' moons. So when we do the moon of Earth, we're saying there's a unique moon of Earth. So we do that part first, and then we say it's larger than Mars' moon. So we're saying that thing, that unique thing, which we'll end up calling X, has a property, namely, for anything, if that thing is a moon of Mars, then X is larger than it. So that's, what we're schematizing. It's always good if you can walk yourself through verbally what you're about to do before you launch into it. You're less likely to make a mistake. So there's at least one thing, such that it's a moon, and it orbits Earth, so X orbits Earth. Now we got to do the unique thing. So n for all y, if y is a moon and y orbits Earth. And so you notice I added parentheses because this is going to be a complex antecedent. So if y is the moon and y orbits Earth, then x is equal to y. There are no parentheses around this because this is an atomic sentence. And remember, atomic sentences don't get parentheses. X equals y is just like saying that you have, so when we say x is equal to y, this is just like saying there's some special predicate I star, which is identity xy. And remember, whenever we had predicates with nothing else going on, these are just atomic sentences in QL. So no parentheses around this kind of thing.
Will Carnot be allowing you?
Yeah, Carnot would say that it's ungrammatical, I think. We can try that out. Or it would accept it, but you'd get it wrong. But then I, the human, I would see what you're up to, and I wouldn't take points off for that, because I just think, we naturally slip into putting parentheses around tons of stuff, because we just like parentheses, parenthetically. That's how we roll. All right, so now we've done the unique part. We're going to keep y. I guess, we can probably close y off. I don't think we'll need it again. We'll see. So, all right, so at this point we said there is a unique moon of Earth. There's exactly one moon of Earth. And now we need to say that this unique thing, is larger than all the moons of Mars. So ampersand for all z, if z is a moon and z orbits Mars, then Earth's moon is larger, so this thing x is larger than z. And we close off the z part, and we close off the x part. So for all z is a moon, z orbits Mars, then x is larger than z. Yeah. So I think this should be good. Where things get a little weird is sometimes we have to say something like if x is different than z, but I don't think we have to in this case. I'm just gonna, fingers crossed. Yeah, awesome, cool, okay. Great. So yeah, what happens if we put in this parentheses? Oh yeah, it says the formula is ungrammatical. That's cool. So yeah, so if you go,
applies to LXZ. It also cannot be in parentheses.
come again?
LXZ at the very end also needs to be.
Yeah, so you also couldn't put, great example, you couldn't put this in parentheses because this is also a term. Which is a little annoying. Because, you just might naturally, in my mind, it's like good practice if you're gonna do a conditional statement, put the antecedent in parentheses, put the consequent in parentheses. That just seems like a safe thing to do. It's a little annoying to have to remember, if my consequent is a term, then I can't, or not a term, but, if my consequent's an atomic well-formed formula, then I can't put it in parentheses. Or just, another thing for me to ask Gramm-Leach-Krauss to modify, if possible. Cool, any questions about this one? All right, let's read some Wittgenstein, and then we'll do more practice problems. But so hopefully you guys are in great shape for this problem set. I think the other ones are not that bad. And you get auto checkers, so you can try stuff out, So. Cool. All right, so Wittgenstein says some really funny stuff about identity. So part of this initially is still in the context of the rule-following paradox, where remember, we had this issue about adding. How do we know what we are to do when someone's like, just keep adding one? And in particular, the puzzle arises even if somebody said to you, I just want you to keep writing 2. So if somebody said, hey, I would like you to just write 2 after 2 after 2, blah, blah, blah. There's nothing to stop somebody from reasoning as follows. People have only ever written sequential 2s to some finite number n. That's the furthest they've ever gotten. What if that, finite number n is like the 1000th place, and so at the 1000th instance, we just start writing 3s. There's nothing in, you know, the history of humankind to say that this isn't how the direction of keep writing twos is to be interpreted. So one response you might have is, oh, you need something like an intuition. You just need to intuit that the person who said to you keep writing twos wanted you to, even at the 1000th place, write twos and not threes. So Wittgenstein's point here is, I guess really he's imagining we were counting like by 1, 2, 3, 4, you know, up. So he says, if an intuition is necessary for continuing the series 1, 2, 3, 4, ... then also an intuition is necessary for continuing this series of twos. Now you might think this series of twos has some special property that makes it easier to respond to the puzzle. You might think, well, you know, I'm just asking you to write the same thing. You know what a 2 is. You know that this 2 is the same as that 2. I'm just asking you to keep writing the same thing. And so, you know, the response here is, but isn't at least the same the same? Isn't at least the same the same? For identity, we seem to have an infallible paradigm, namely in the identity of the thing with itself. And this is the identity we're using. Everything is identical to all and only itself. That is what our identity predicate establishes. That's the functional role it plays. So Wittgenstein says, I feel like saying, here at any rate there can't be different interpretations. If someone sees a thing, he sees identity too. So we're just going around seeing identity. You know, whenever I see an object, I also see that it's identical to itself. Then are two things the same when they are what one thing is? Are two things the same when they are what one thing is? And how am I to apply what the one thing shows me to the case of two things? And here we get, you know, this totally, for us in this logic class, a gut-wrenching sentence. So the quote is, a thing is identical with itself. A thing is identical with itself. This is something I could have put on the slides. And Wittgenstein says, there is no finer example of a useless sentence. Devastating. So, you know, this entire week has been useless because we've just really been talking about the claim that a thing is identical with itself. And the sentence is allegedly useless. So we're very sad. Which nevertheless is connected with a certain play of the imagination. It is as if in our imagination we put a thing into its own shape and saw that it fitted. We might also say, everything fits into itself. Or again, everything fits into its own shape. While saying this, one looks at a thing and imagines that there was a space left for it, and that now it fits into it exactly. So, and this is kind of how you think about identity in metaphysics. You think about intrinsic duplicates. And when we imagine a world that has an identical coffee canteen, I'm really imagining a universe where I had, you know, atoms in the void that constituted an object that had exactly the same properties as this coffee canteen. You know, all the same relations between them, and then I'd say in that world there is an identical coffee canteen. Obviously it can't be this coffee canteen, because this coffee canteen is identical with only itself. But we can imagine another world where there's not, in some sense, an identical coffee canteen. You're see, you know, we play with words in this way. We do, you know, we make these kinds of imaginative statements. So that's one part of the funny stuff on identity. There's another short passage which is funny. This happens in there's another part of the investigations. This is steam text that talks about pain, and also so some notion of privacy. So there's a thought that perhaps only I can know that I'm in pain. You guys can see me wince. You can infer that I'm in pain, but I could always be faking. Every time I wince, you know, if I accidentally, you know, like cut my finger on a sharp thing and it seems like I'm in pain, I could just be faking as far as you're concerned, because you can't experience what I'm experiencing. Only I can experience my experiences. They're my private experiences. And this kind of notion is connected as well with questions about whether anybody could have a private language. Could you have a language that only you understand? So some kind of, you know, experience. Whenever I have this experience, I write down some little symbol in my diary, for this experience, and nobody else can have this experience, and nobody else can know what the symbol's referring to, and this is my own little private language. There's a question, is this conceptually possible to have a private language? So basically, yeah, this all is in the context of pain, blah, 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 but there's some funny lines about identity. So Wittgenstein says, the substitution of identical for the same is another typical expedient in philosophy, as if we were talking about shades of meaning, and all that were in question were to find words to hit on the correct nuance, which honestly is really how a lot of philosophy feels. You want a certain kind of nuance in what you're saying. And that is in question in philosophy only where we have to give a psychologically accurate account of the temptation to use a particular mode of expression. What we are tempted to say in such a case is, of course, not philosophy. And this is one of my favorite lines in the whole book. But it is its raw material. So, for example, what a mathematician is inclined to say about the objectivity and reality of mathematical facts is not a philosophy of mathematics, but something for philosophical treatment. So often you'll hear some philosophical realists and Platonists, they'll say, well, these mathematicians, they go around and they talk about numbers, and so they seem to be really committed to numbers existing, to the reality of numbers and other mathematical structures. So isn't that great evidence that numbers are real and that mathematics is in some sense objective? And Wittgenstein's point here is, what these mathematicians are saying, this is something for a philosophical treatment. You take their claims and it's evidence that we need to say something philosophically, but it's not a philosophy. Like when the mathematician says, oh yeah, 2 plus 2 is equal to 4, and I just refer to numbers, so numbers exist. That's not, they're doing math. When you're doing math, you're not giving a philosophy of math. Philosophy of math is about math. You're talking about mathematical claims. It happens just in a different context. So I think you can't establish Platonism just by saying, mathematicians talk about numbers and say they exist. That's not an argument for Platonism. It is interesting stuff that you could use as the basis for philosophy. It's not philosophy. And so this is all to say, which is really the punchline of this whole thing, the philosopher treats a question like an illness. And that's really what's going on. So that's my advice to you, to all of you, is don't go into philosophy, because to go into philosophy is really to feel that you are mentally sick. And that's, what the philosopher is doing is trying to cure you of some kind of intellectual disturbance, to a more or less degree. All right, so that was our fun Wittgenstein. There's some other really beautiful quote in here about screaming, but I couldn't find it. So if I find it in a future class, I'll let you guys know. But I would say, though, if you guys are ever bored and you wanted to read some philosophy, I really would. There's not that many books I would recommend. I really would. As a fun book, I would recommend reading parts of the Investigations. I would not, if you do that, I would not think that this is at all representative of what contemporary philosophers do. This is in just style and mode of thought, very different than what goes on in contemporary philosophy. But whereas much of contemporary philosophy is in some sense kind of bullshit, this is not bullshit. And so it's kind of fun to read, but you just don't, I wouldn't want anybody to read this and think, oh, this is what goes on in the philosophy departments. This is not, this book is very controversial methodologically, because it's in some sense criticizing much of analytic philosophy, but it's not really doing analytic philosophy. It's in a different mode, but it's fun. It's kind of like a puzzle book. There's little puzzles and you get to think about solutions to them. All right, so let's do some more practice, and then maybe we'll talk about jackasses. I don't know. Which one of these seemed good? Okay, so yeah, let's do some more definite description practice, and then we'll try this really hard one. All right, the moon of Earth is smaller than Io. So we're saying there is exactly one moon of Earth. There's a unique moon of Earth, and it's smaller than Io. Moon, and it orbits orbits Earth, and for anything else, if that thing is a moon, and that thing orbits Earth, then that thing is equal to x. And the moon of Earth is smaller than ours, so this thing x. Alright, so for this thing x, Io is larger than this thing x. So we don't have a smaller than predicate, but we have a larger than predicate. So the something is smaller than Io if and only if Io is larger than it. And check our parentheses, and they all look good. So, any complaints about this one? Did I miss anything? Well, let's try. Yeah, cool. All right, try to do the smallest planet has no atmosphere. I will also try to do this. This one, I'm gonna give myself a head start on this because it's tricky. Let's see. There we go. All right. So that I don't spoil it for you guys as you work. So the definite description here is the smallest planet, and we're saying it has no atmosphere. Not confident in this. All right. Let's try to do this. So there's some easy parts and some hard parts of this. So the easy part is to say this thing, whatever it is a planet, and it doesn't have an atmosphere. So we know we're going to say that. So let's say that at the start. We know this thing X, whatever it is a planet. It doesn't have an atmosphere. Now we need to say that it is the smallest planet. And furthermore, that it's the unique smallest planet. That's the hard part, the unique smallest planet. So just to say that it is the smallest planet, that's not that bad. We're just saying for all the y's, if y is a planet and y is different from x, then y is larger than x. So that's, and it's, I mean, whether we really need to say that y is different, this, I think, reasonable people who disagree might think nothing can be larger than itself. Purely syntactically, the larger than predicate, I guess, doesn't know about that claim that nothing can be larger than itself. So like in principle, like LYY would be, a well-formed expression. So if you want to say that you never have LYY, you have to explicitly say, well, it's not the case that y is equal to x. Now this is the tough part that I'm not confident about. We need to say that this is the unique smallest planet. So we need to say something like, for anything in our domain of discourse, if that thing's a planet, and that thing's different from the y's, and the y's are larger than that thing, then this thing z is x. So we have to check that this y is still in the scope of this universal, and I think it is. So maybe this will work, but I don't feel great. No.
Should you put parentheses around the then statement?
Oh, yeah, maybe that'll, okay. Thanks, Manny. So, is that, no.
What is the rationale between, for not making, multi-line statements, easier to do on Carnot?
Oh, I see, to have it,
I just feel like indentation would just help with scope.
yeah. No, that's a good, I should add that to the suggestions to the grammar class, if we could indent and start new lines. Yeah, no, I'd also like to get better brackets. To just have parentheses is tough.
Because this feels like writing a scheme in one line.
Mm-hmm. Yeah. No, it's a lot. It's a lot to put in. All right. So planet. It's not for all y. Any suggestions on this? Otherwise, I'm going to cheat and I'm going to look at the solutions. It's planet. It's not all y. For all z. All right. We're gonna bow. Cover your eyes. Not for mortals. I think we got close. All right, so I'll put the actual solution, or one of them, here, and let's compare what we wrote. So, thing's a planet, and it doesn't have an atmosphere for all y. If that thing is a planet, and it's different, then it's larger than x, and for all the z's, so far looking good. Z is a planet, and y is larger than z, and they're distinct. Oh, did I just miss?
An extra parenthesis.
I guess I just missed a parenthesis. All right. Hey, okay. Cool. But yeah, you see how tricky this is just to get, everything to be right. So I don't think I would ask you guys to do a problem that's tricky on the final, but I'll let you know if that changes. Okay. Let's do a neither one. So remember, the neither is saying there's exactly two things. And those two things have the property. Or in the last 3 minutes, we could talk about donkey sentences. Anyone in favor of donkeys? We got one. All right, we'll do a quick drive-by on the donkeys. We're gonna mow down these donkeys, we might say. All right, so basically what's going on is this would be an easy sentence to schematize. Every farmer who owns a donkey is happy. We're just saying for all the x's, if that thing's a farmer and there's at least one thing that's a donkey and the farmer owns that thing, then the farmer's happy. And we have no problems here. Now, what might be surprising is when we move to a similar statement, every farmer who owns a donkey beats it. We end up with a real issue, not just morally, but syntactically, we have an issue. These farmers must be stopped. So we have this, X is a farmer, and there's at least one thing that's a donkey and they own it. Now we try to put this in just like we did before, for everything. If it's a farmer and there's at least one thing that's a donkey and it owns it, then it beats it. Issue here is we we don't have this y in the scope of the existential. This is an unbound y. So we intuitively see that this y refers to it, the donkey, but our logical language is not capturing that. And so this wouldn't be a sentence of QL because we have an unbound variable, so we're like, shit, what do we do? Now, the intuitive thing would be like, well, why not just increase the scope of the existential? So we give that a try. This was our problem. A donkey lay beat and unbound. And we try to increase the scope, just pull this existential out the front. And now we have this little teal parenthesis, and our teal y is bound. So we're thinking, yeah, we got it, but we didn't. We don't have this because this is an if-then statement. Remember, material conditional has strange properties. You can make this antecedent trivially true, provided there's at least one thing that's not a donkey, because then that thing will make dy false. That'll make the entire conjunctive antecedent false. And so for any x, provided there's at least one thing in the domain that's not a donkey, presumably our farmer's not a donkey, although a farmer might be a jackass. It sounds like it, right? So this is not going to work. So instead, we step back and we try another tack. And so we think, what does it take to be false to say every farmer who owns a donkey beats it? What we're saying is, it's not the case that there is somebody who's a farmer such that they have a donkey, they own it, and they don't beat that donkey. And so this is, in some sense, what we're saying. You might quibble about this. Then you can push this negation through, and we're saying, for all the x's, for all the y's, if x is a farmer and y is a donkey, x owns that, then the farmer beats it. And so we're really saying every farmer beats every donkey they own. We can schematize this, but you might think, is this really what we wanted to schematize? Because intuitively, if someone says every farmer who owns a donkey beats it, you might think, well, that's true even if, for at least one farmer, they only beat one of their donkeys, but they have multiple donkeys. Whereas this sentence we did schematize is saying every farmer beats every donkey that they own. And so you might think there's still a problem here, and at this point we just say, yeah, we quit, and we've run up to some limitations of our predicate logic. And the linguist could do fancy things, binding theory, it's the hook. They do something, right? But you might just think that there's something, if you were thinking, I guess, about are humans computers, and if you think, quantifier logic is we've come pretty close to having a formal language that does capture what we're doing. We think, well, here's something that seems like humans are doing that quantifier logic doesn't do, or at least doesn't do well. So that's kind of cool. We are better than quantifier logic. And the human urge is always to view the humans as being superior to something else. And so here we can say, screw you, formal language. All right, so thanks so much for coming today, guys. Feel free to get in touch if you have any questions. I have office hours right now until 12, but no office hours Friday because it's break. So. Do you guys have other classes today?
I have a PE class.
Yes, sir. Committed students. I admire that.
It's still an NCAA violation if you're in college, so you can't get any prize money.
Whoa!
So,
even if you're just doing this for fun?
yeah, any
Wow.
prize money can't be.
That's wild.
Yeah, you can't take it.
Wow.
Despite the fact that NILs are now a thing, now you can't you can be sponsored as a college athlete,
Mm-hmm.
but you can't. Because then you can they consider that you're not an amateur anymore if you're making
Mhm.
money for racing. But it's weird.
Wow. That's wild. who would have thought that attendance the day before Thanksgiving break would be substantially better than after? I guess people are traveling, good for them, you know? So, it's
I
really
know that there were a lot of like delayed flights yesterday.
Oh, yeah.
I don't know if any got like canceled, but I know people that like had like 4 to 5 hour delays.
Oh, yeah.
It's kind of tough.
Yeah, no, the worst is if you're on the last flight out of an airport to a city and then it gets canceled, because then you gotta stay overnight. That's just like, what I never really understand is like if the whole flight gets canceled, and that's like, I don't know, 60 people, let's say, and they're the last flight of the day, how do they all manage to, you know, if all the planes are booked up the next day, how do the people manage? Just some people just quit and just say, yeah, I'm not gonna do it. It just, you know, somehow it always seems to work out, right? But I don't, you know. Is your guys' sense that airlines are still understaffed right now?
I heard that there's like a pilot, something still a pilot shortage,
Oh, okay, pilot shortage.
or at least an experienced pilot shortage.
We want the inexperienced pilots.
Yeah.
We want, you know, the wild ride. Why couldn't you also get a carnival ride with your flight? All right, so let's get started on this stuff. This is going to be the beginning of a buckle your seatbelt week. So today is not that bad. The soundness proof is pretty chill. The completeness proof on Wednesday is much more involved and a lot harder to hold in your head. And then we'll do it all over again next week with quantifier logic. So this week we're back to just sentential logic, and this stuff with sentential logic is basically our warm-up for the stuff for next week. So the proofs we do this week for soundness and completeness for sentential natural deduction will be really structurally analogous to the soundness and completeness proofs we'll do next week for quantifier logic. So you kind of have like, you know, these two shots to get this stuff down. And the problem set this week, none of the problems are really that hard. One of them, I think maybe the second one is a little bit tedious and involved, but everything else is pretty straightforward. So, and then, you know, if you screw it up, we'll do similar problems the following week. So, you know, hopefully you'll have opportunities to get this stuff down. But yeah, we're back to proofs, you know, so it's just easier to make mistakes in proofs. Cool, so basically we'll get you guys back up to speed on what this stuff means, the soundness and completeness results. Then today, we're hopefully going to make it through the soundness stuff. If we have time, we'll start on completeness, because who knows, completeness is so long, we might not finish on Wednesday, so hopefully we will. If we start on Wednesday, finish it. So the thing I think that, you know, remember is just like the soundness proof is really chill, not that bad, should be straightforward. Completeness has a lot going on, but the core of the idea is very simple. It's just executing one of the steps takes a lot of steps. So cool. So we've been using natural deduction systems to show that arguments are valid, and it's super great that more people showed up. Appreciate you guys all have good Thanksgiving breaks. Anybody do anything really fun? Gerardo went hiking in Colorado, so that's at the top right now. An enemy top hat. Now, you guys are all losers. No, I didn't do anything fun with Thanksgiving, so I went to some parties and that was it. I ended up being out way too late on actual Thanksgiving. That was a tale. So, you know, but we're in a professional environment, so. The one thing I can say is I had no idea that somebody could walk up to you and without really making like any kind of sudden movements, shatter an entire beer glass. Just shatter it. I don't know how it happened. Just shatter it. And then, you know, like, you know, you're out there and you're just like, yep, you're totally drenched. And somehow you're like, this whole glass shattered around me. Where is the glass? Am I okay? And we're like, whoa. So we love Thanksgiving, right? Cool. And I'll make sure I'll put you guys in the good attendance file, because yeah, for the problem set this week, so it's due at noon on Saturday. And since you're here today, if you end up being in a jam and wanting an extension, feel free to get in touch, and I will kindly find you. I think everybody's here right now. All right, so you can show that you have a valid argument if the conclusion is on the last line in the scope of the premises. Then those premises give you the valid argument for the conclusion. If you want to show something is a tautology, you just show that there is at least one sentential natural deduction derivation that has that sentence on the final line in the scope of the no premises. So just there's like the no scope line. Still in Carnap, they write an outermost vertical line, just like sectioning off the numbers. To show that two things were logically equivalent, you would either show they're biconditional as a tautology, so their biconditional appears in a derivation with no scope line, or you would just derive one sentence from the other, derive the other sentence from the other. That would show they're logically equivalent. That basically would be biconditional introduction at that point. But so one thing we never did was show our system sound. So we did show our tree system is sound, and we also showed our tree system is complete, but we never did this for sentential natural deduction. So that's what we're doing this week. So you'd only, these inferences from a syntactic thing, this derivation, to a semantic notion, a logical entailment notion, only holds if our system is actually sound, and you're only guaranteed to be able to do this kind of trick if your system is complete. So that's our, try to hold that in your head. So basically we have these three turnstiles on the table, and this week we're interested in two of them. So we're always interested in the double turnstile, which is our semantic notion. So this is logical entailment, you think semantics, you think this just comes from however you set the truth tables up. And since we're doing classical propositional logic, we have fixed truth tables, we don't mess with that, and so that's our semantics. Semantics, truth conditions, because in our very coarse-grained picture of logic, the meaning of something, the semantics of it is just the truth conditions. Of course, obviously, real meaning of sentences is much richer. It comes from the use of the sentence. There are many ways a sentence can be used that aren't really, this is controversial, but not really in the truth conditions. So we have a very coarse-grained view of semantics in logic class. So we had this single turnstile earlier in the course, the STD single turnstile. We're done with STD. This shit's disease. We're not talking about it this week. Instead, we're talking about turnstile SND, derivability in SND. So recall that with our single turnstile for trees, we said that some set of premises gamma, tree turnstile, like tree gamma, some conclusion theta, provided that the root, which was the premises and the negation of the conclusion, were tree inconsistent, meaning that they appeared with a closed, there was at least one closed tree that had this stuff in the root. So this idea is going to be important. The fact that we focus on something like this, gamma union negation theta, will matter for us as well in these proofs. So there's some connection there. So recall, if you have gamma semantically entails theta, this just means whenever the premises in gamma are true, the conclusion theta is true. Another way to put this, there's no truth value assignment that satisfies gamma, i.e. makes everything in gamma true, while theta is false. There's no TDA that does that. So if you ever were to satisfy everything in gamma, theta would have to be true. So this is where, this little thing appears, so important idea. So whenever you have gamma semantically entails theta, this just means that the set of premises in gamma union with the negation of the conclusion is unsatisfiable. It means there's no truth value assignment that can make all the gamma guys true and make not theta true. Because remember, when we're saying whenever we make all the gamma guys true, we make theta true. So if you made all the things here true, well then you couldn't make not theta true, and so this whole thing would be unsatisfiable. So you want to be comfortable moving from this double turnstile to the claim that the set of premises union with the negation of the conclusion is unsatisfiable. Because this is a kind of move that we'll often have to make in these proofs. So you want to be confident about that. Yeah. At least on the completeness proof. So when we show our derivation system sound, we show that our derivations are in some sense safe. They never lead us to fallacious arguments. And so what this really means formally, this is the formal definition of soundness, from a single turnstile in our syntactic system, you can get a double turnstile. So you can convert a single turnstile to a double turnstile, that's soundness. You can go from syntax to semantics. And then when you show that your derivation system is complete, we're basically showing we don't need truth tables. We could, if we wanted to, just get by with our derivation system, formal definition of completeness. From a double turnstile, we get to conclude a single turnstile. So whenever we have logical semantic entailment, we also have syntactic derivability. So completeness is from double to single. I think 3 of the homework questions are basically just testing your facility with these if-then claims. And remember, you'd also have the contrapositive of these claims, which contrapositive is going to be really useful. If you know that you don't have semantic entailment, then by the contrapositive of soundness, you know that you don't have derivability. And if you know that you don't have derivability, then by the contrapositive completeness, you know that you don't have semantic entailment. So you want to be comfortable moving back and forth between the contrapositives of these statements and the statements themselves. Definitely you want to have soundness and completeness, these definitions memorized if you don't have them memorized already. You just want to have them down. Cool. There's some, I don't know, maybe somewhere I might have put a really bad mnemonic. I'm trying to put it. Yeah, soundness is, this is like sound from single to double. This was I had some mnemonic with like double dollar bills or something, but I think it's really bad. So I'll have to try to, if you guys want a better mnemonic, let me know. If this isn't, easy enough to memorize already. Yeah. All right. So yeah, so this just means we have enough things in our system. And the soundness result means we have good rules. We have rules that don't lead us astray. Basically, we have rules that wherever you are in your proof system, the stuff earlier up in your proof actually logically entails the stuff lower down. So remember, with the soundness proofs, we're reasoning from the top down. And so the heuristic for does my rule preserve soundness is just when I introduce my new sentence on a lower line, is it also logically entailed by stuff earlier up? That's basically what our soundness proof is going to show. So soundness is super chill. Completeness is more oil, right? Okay. So yeah, with some contrasts. I don't know if these are oriented or not, because you probably don't remember anything about what we did for trees anyway, right? So I barely remember what we did for trees, right? It was weeks ago. We're in week 12 now. This was like week 5. So when we prove the tree methodologic stuff, we use the contrapositives. With these proofs for natural deduction, we will not use the contrapositives in our proof strategy. We're going to proceed directly. It's direct attack, as they say in chemistry class. Also with trees, so this is one more interesting difference. With trees, our premise set gamma was finite, and our proof seemingly requires that the premise set gamma is finite. Whereas here, we're going to let the premise set gamma be infinite, and our proofs are going to work for that. So you think that's kind of cool. Now one caveat, thing to keep in mind, and this matters for the proofs and maybe a couple of homework questions. Whenever we talk about a specific derivation, natural deduction, the derivation always has a finite premise set. So these deductions, the things with the scope lines, they are defined only for a finite premise set. But we can still let gamma be infinite. We'll see how that is the case. So yeah, you might worry, is there some kind of limitation here of the trees, the fact that our proof required that gamma was finite? And the answer is no, because as you'll show in one of the homework problems, and this is really, really easy homework problem, none of this stuff's really that bad, that there's no instance of a valid propositional argument that requires infinitely many premises. So whenever you have an argument from infinitely many premises, there will always be some finite subset of that infinite set that also entails the conclusion. This is bound up with the fact that sentential logic is compact. So whenever you have a set of sentences that is satisfiable, it's satisfiable if and only if every finite subset of that set is satisfiable. That's our notion of compactness, which we'll probably talk about. Well, who knows? You know, we might run out of time because these proofs are so long. But hopefully we'll talk a bit about compactness at some point. You get a very, really easy proof of compactness from soundness and completeness, but there's something you might find unsatisfying about that. Unsatisfying in the intellectual or emotional sense, because compactness is really an intrinsic property of our logical system, but the way that we'll prove it, at least initially, is relying on our syntactic system, which is just some choice of convention. You know, it's like sentential logic itself doesn't know anything about a choice of syntax. That's we make the choice of syntax. So it is kind of strange in a way. You might think there's some kind of impurity in a proof of an intrinsic property that relies on this, you know, conventional construct that we made up. Cool. So yeah, we'll see. I might on the next problem set 13, I might ask you guys to try to explain why our metalogic proof of trees required gamma to be finite. It's kind of an interesting question. Cool. All right, so how do we do the infinite stuff? So let gamma be a possibly infinite set of premises, let theta be the conclusion. So just remember, a truth value assignment, a TVA, it assigns true or false to the atomic well-formed formulas. There's an infinite number of atomic well-formed formulas. And a TVA assigns true or false to these infinitely many atomic guys. So in the case where gamma is finite, then the premises have only finitely many atomic sentences, so a TVA is basically just a row of truth table, where a truth table is a finite thing. But what we'll say in general is that an argument is semantically invalid, so you know, a lack of double entailment, a lack of double turnstile. If there's a truth value assignment that makes the sentences in gamma true, but makes the conclusion false, and in this case we'll write gamma does not semantically entail theta. And if there's no such truth value assignment, then gamma does entail theta. So basically, if gamma is infinite, and if there's no truth value assignment that is a counterexample to entailment, then you have entailment. And so yeah, this is good, even if we have infinitely many premises. So similarly, you might ask, okay, what is the analog notion when we are talking about derivability? Because the proofs, the actual deductions, are always finite. The deductions always have a finite set of premises, so what would it mean to write down gamma single turnstile theta in SND? So what would it mean to write this in SND when gamma is infinite? Because you'll never have a deduction that has an infinite number of premises. So you have just an easy definition of derivable. So it is SND derivable from gamma, provided there's some finite subset delta, some proper subset of gamma, call that delta, this is finite. And where you again have the conclusion on the final line, and you have the conclusion directly next to the main scope line. So basically you have something like this thing. You have all your delta guys up here. These would be justified by a bunch of colon PRs. You know, one colon PR for every guy in delta. And then on the final line, you would have your conclusion, theta. And it'd be justified by something. So, provided there's something like that, then we get to write that gamma single turnstile theta. Of course, we can also write delta single turnstile theta. And if there isn't any such derivation, if there's no finite subset of the gamma premises with, you know, this structural property, then you would say that the conclusion theta is not SND derivable from gamma, and we'd write gamma slash SND theta. So basically, the gist of why our proof doesn't work for trees for infinitely many premises is we don't have an analogous definition of single turnstile from infinite guys, and it's really, it's a consequence of how we define tree validity and tree invalidity. Where remember, tree validity was actually not the negation of tree invalidity and vice versa, and so that's basically what screws it up. Cool, all right, you guys ready to do soundness? This was all a way to kill time in case people showed up, right, before we get into the actual thing. So this is basically our proof idea. So whenever we have some line in a natural deduction, we just want to show that the sentence on that line is entailed by the premises or assumptions that are accessible from that line. We just want to show this property holds at every line. That basically no matter where you are in your proof, so we have, doing some stuff with these lines, and then you might be at some line K, and there'll be some sentence on line K, PK, and that would be justified by something. PK will be in the scope of some assumptions up here, that will be justified by colon PR, and we're basically just going to call the set of assumptions that PK is in the scope of, we'll say PK in scope of these assumptions, which we'll call gamma K. And basically what one could conclude at this point, just from the thing is, well, we clearly have clearly gamma K, single turnstile PK. That's just, what it means to be able to write a deduction like this. So we definitely have gamma K, single turnstile NS and D aren't having PK. And we just want to show, so from this we want to show, question mark, can we also convert this to a double turnstile? And if you can do this at every line in your deduction, then you're good, because it'll also hold for the final line. And then we would have, the final line be the thing we want. It'd be the gammas, whatever they are, single turnstile or conclusion data. That entails that the gammas, whatever they are double turnstile or conclusion data. And that is soundness. So really simple proof idea. So let P sub K be the sentence on line K. So it's the kth sentence in our derivation. And let gamma K be the set of premises or assumptions that are accessible on line K. Basically that the sentence PK is in the scope of. And I say premises or assumptions just to maintain this little syntactic difference in Carnap between the stuff that we justify with a colon PR, and whenever you start a subproof, you write a colon AS. So premise, but if you want, you can just call them all premises, or you can call them all assumptions. It doesn't make a difference. Cool. So this is our sub goal. Given some sentence P sub K on a line K, show that gamma K double turnstiles PK. Where basically, if you have this kind of thing, you already have single turnstile gamma K, single turnstile PK. You just want to show you can convert this to double turnstile. So reasoning from the top down. Are there any questions about the proof idea? So the proof idea manifested. Cool. If any questions arise, feel free to ask them. So the whole trick here, we're going to do an induction, obviously. That's our one proof, strategy in this class is do inductions because our logical systems have recursive structure. And so you might recall we briefly talked about maybe on one slide how natural deductions also have a recursive structure. So when you have a possibly empty set of premises and you have a finite number of rules to add a line, that finite number of rules is basically the recursion clause of giving a recursive definition of a natural deduction. And so these, ways of adding a line, they include our 11 rules for iteration, and then we have an intro and elimination rule for each of our 5 connectives. And so basically, we just have to show that no matter how we add a new line, it preserves this property, that from a single turnstile for a sentence on that line, we get a double turnstile. We just have to show this for every single one of our ways of adding a rule, adding a sentence to our induction. So we're basically just gonna do induction on the number of lines in a natural induction. So we'll show the base case has this property. The base case just is line number 1. We love line number 1. That'd be a great t-shirt. I took logic and I love line number 1. And then we do an induction hypothesis, so we assume the property holds for all the lines that are less than or equal to k. So, we're basically doing a strong induction. So I guess really we're assuming the property holds for all the lines from 2 up to k. Because we have shown the base case, we will have. And then we'll just show the property holds for the next line, the line at k plus 1. And we'll do this by considering all the possible ways that the line k plus 1 could arise. And then, this is it. So again, any questions on the proof strategy? This is the kind of thing, when you're induction pro, you can write this down and you can be like, this is what I'm going to do. And then it's just a matter of going through the base case and then going through each of the induction steps, which we're probably not going to do each induction step in this class because that would be really boring. Because a lot of them are really similar, so you'll get the idea. So just really to save some words, you can always introduce these properties for the shit you care about in deduction. So we're going to call this property righteous. So this property here, going from a single to a double on a given line, this means the line is righteous. This line k is a righteous line. So we care about righteousness in this class. We are justice warriors, we might say, in logic. We are fighting for truth, and truth is justice. So this is our property. We'll say that a line is righteous, just in case the set of assumptions or premises that are accessible from the line I semantically entail the WFF on that line, not the WTF. And we'll call a derivation righteous if each of its lines is righteous. So basically our goal is just to prove that all of our natural deductions are righteous. And if we have done that, then we have shown soundness. So, cool. So basically let gamma be any set of these SL sentences, possibly infinite. And if we're able to show that gamma single turnstiles some conclusion P, then by definition there'd be a derivation that has finitely many premises, because it's a derivation deduction. And these premises delta would be a subset of gamma. P would occur on the final line and would be in the scope of delta. And so you'd have delta single turnstile P, and if our thing is righteous, then we'll have double turnstile. So from the righteousness that we've shown, this property that we've developed in logical reality, we could conclude that the finite delta set logically entails the conclusion P. And so any truth value assignment that made the delta guys true would have to make the P true. So in particular, the no truth value assignment that makes all the sentences in gamma true while making P false. Because if you make all the sentences in gamma true, you have to also make all the sentences in delta true, because delta is a subset of gamma. So if you've shown the finite delta semantically entails P, you also have shown the infinite gamma semantically entails P. And then that's what we wanted to show, soundness. So we went from a single turnstile to a double turnstile. So we're all good. So yeah, any questions on the proof idea? Cool. All right, so here's our base case. We just have to show that gamma 1, which is so now the gamma 1 basically just means the set of premises or assumptions accessible at line 1. So clearly when you're at line 1, you're right, you're chilling up here. We can call this sentence P1, and in this case, gamma 1 just equals P1. Gamma 1 equals the set P1. The set of assumptions or premises that are accessible at the first line just is whatever it is on the first line. And the first line is either a premise, or if you started your proof with an assumption, which you could do. Sometimes you start a proof This is what you do if you want to show something that is a tautology. You start a proof by starting a subderivation. So in Carnap, what that would look like, right, is if you had, so Carnap always puts some line out here for the numbers, but on line 1, you would start a subproof, assume something P1, you might assume it for like negation introduction, or negation intro, and then you would carry it along and blah, blah, blah. So again, in this case, gamma 1 would be the set P1. Cool. So, yeah, something should probably be obvious. Every premise lies in its own scope. Every premise is accessible by its own lengths. So, these premises be getting high off their own supply. And I was having a good time writing this shit. All right, so you definitely have the sentence P1, whatever it is, double entails P1, that's clearly true. Whenever P1 is true, P1 is true, right? So again, what is sameness? What is identity? We get to say this. So of course, the set P1 semantically entails P1. So line number 1 is righteous. Gamma 1, the set of premises accessible to line 1, semantically entail P1. So again, this is really obvious that the base case is satisfied. The key is just to be able to write this precisely to, make sure you're showing what you need to show in terms of the gamma 1, even though it is the case that gamma 1 literally just is the set P1. But you want to be able to do this accurately. So then we go to the induction step. So we assume that every line I for 1 less than I less than equal to k is righteous. So all the lines from 2 up until k assume that they're righteous, which just means the set of assumptions or premises accessible at line I semantically entail the sentence on line I, pi. And then we consider the line k plus 1, and we show that it is also righteous. And we have 12 cases to consider. 11 of these come from our S&D rules, and so question, what is our 12th case we have to consider? Yeah.
Like just reiteration.
No, so that's in there, yeah. So we have 10 rules from intro and elimination plus reiterations, that's 11. But there's a 12th case. What is the 12th case? We could have said that there could be 13 cases, but I didn't say that because we don't like the number 13. I'm a little leery about week 13. A part of me is like, maybe we should have just renumbered week 13. Made it week 4, it just skipped over. Who needs a week 13, right? It just sounds dark. So yeah, so what's our 12th case? The 12th way, yeah, Alan?
Another premise or assumption?
Exactly, yeah. So we've only done the starting line with our base case, line 1. And so of course you could have many other premises, some other large finite number, and also assumptions. So you can think premises is case 12 and subproof assumptions is case 13, but you can just combine them. So alternatively, right, one could have modified the inductive proof and built this 12th case into the base case and just done a more general base case. You could have done that instead. So here's our case 1 is let p k plus 1 be a premise or assumption. So imagine, you're going along your premises, you've done like 10, and now you have an 11th premise. And so that line 11 is justified by PR. Alternatively, you could be doing stuff where you're like, you're going along your proof, and somewhere down here, you start another assumption, pk plus 1, colon AS. Maybe we assume this for negation intro as well, on line k. Then again, this would be our k plus 1 line. We have to show that it's righteous. We have to show that the set of premises that are accessible at line k plus 1 entail the sentence on line k plus 1. So basically we get to say, regardless of whether it's a premise or assumption, the sentence on the k plus 1 line belongs to the set gamma k plus 1. Because again, every premise or assumption is in its own scope. So this line pk plus 1, the sentence pk plus 1 is in the scope of itself. It's also in the scope of anything accessible to, from this leftmost scope line. Cool. And so basically, yeah, if we had any truth value assignment that made all the gamma k plus 1 guys true, it would have to make pk plus 1 true, because pk plus 1 is, in this case, one of those guys in gamma k plus 1. And so, of course, we would have gamma k plus 1 semantically entails pk plus 1. Again, basically just because pk plus 1 semantically entails pk plus 1. So this case is also righteous. Any questions on our case 1? Cool. So reiteration, we're going to have. Great. Yeah, we might actually get to start completeness today. So that's cool, because then we'll definitely finish it on Wednesday, I hope. So, right, something to look forward to, right? Toward the end of the class, we're all kind of like, oh my God, why is this still happening to me? We'll start a new proof. All right, so in this case, the k plus 1 line comes from rule R. And so this just means we have some well-formed formula pk plus 1 that's appearing on an earlier line. So for each one of these things, you can always draw a picture for each of the cases, and so you might find that helpful. Basically, what's going on here is we're on line k plus 1, and we have pk plus 1. We've justified it by reiterating some earlier line, perhaps m. So on line m, you also have the same sentence. You have pm, which just is, in this case, pk plus 1. So this is our little deduction picture. And if you're reading, if you have to read about the relationship between the various premise sets on the different lines, it's often very helpful to draw these pictures. And the book draws them as well. Okay, I use line time, so I should be consistent. So shit. So, all right. See, this is why. Well, I tried in the slides to use the same indices as the book in case you ended up looking at the book concurrently with the slides. I tried to be consistent with the notation to just make it easier on the mind. Cool. So yeah, we let it be I. So we definitely, we're doing induction, right? So I is less than k plus 1, so we definitely have up here that gamma sub I semantically entails p sub I, because we're assuming line I is righteous, has this property. And so we also have that gamma I semantically entails pk plus I, because again, pi just is in this case pk plus I. They're just the same sentence. They're equal, and we know what equal means because we've done quantifier logic with identity. So, but even if, we can, in our meta language, we still have a notion of equality. So when we talk about natural reduction in our meta language, we have a notion of sameness, even though sentential logic does not have an identity. Our proof is in the meta language. So when we apply the rule R, one of the restrictions is that this line pk plus 1, it has to be to the right of line number i's rightmost scope line. So like another way to put it, you can't apply reiteration if you're not in the scope of the earlier line. So for instance, if we had here, for instance, line I was starting some subproof, and down here we tried to write pi and justify it by reiteration, you couldn't do this. This would be illegal because this piece of I is not in the scope of this piece of I. And remember, our scope lines help us keep track of what we're in the scope of, and it's kind of confusing to state, but it's like, yeah, this is one way to state it. This piece of I has to be to the right of the rightmost scope line for the thing you're reiterating. So it's always clear in the picture, it's just hard to verbally say this stuff. But so, given that you've met this constraint, which, if you're doing a legitimate deduction, you must have followed the rules. As we've seen, it's hard to follow the rules, but that's okay. But if you have followed the rules, then it must be the case that the gamma sub i's are a subset, not necessarily a proper subset. It could be the same, but it could be, a proper subset of the assumptions open at the k plus 1 line. So basically, you need to be case that all of the premises and assumptions that are accessible at line I are also accessible at line k plus 1. Now, you could have additional things be accessible. So, for instance, the following would be fine if we had line I, and this had pi, and then we on line k plus 1 were in some subgroup. So imagine here on line m, we assume something pm, and now on line k plus 1, let's say, we have our pk plus 1. Now it's the case that the set of assumptions that are accessible at line k plus 1 is actually greater than the set of assumptions accessible at line I, because PM is accessible at line k plus 1. PM is not accessible at line I, but it's still the case that gamma I is a subset of gamma k plus 1. So in this case, if pk plus 1 were pi, we'd be good. We could write reiteration, cite line I, and this is because we filed this restriction that pk plus 1 is to the right of line I's rightmost scope line. It's chilling here, so we're good. Any questions on this? Who knew reiteration would be so complicated? I mean, this is really a warm-up just to make sure you guys are comfortable with this scope line business, accessibility. Because what we're doing here, we do the same thing for all the other rules, all the other cases. So this is, the key step. Since we know that line I is righteous, and line I semantically tells pi, and pi is pk plus 1, and we know that the set of assumptions accessible at I is a subset of the set of assumptions accessible at line k plus 1, we also have to have the k plus 1 assumptions semantically entail pk plus 1. So this, basically the thought here is whenever you make all of the guys in gamma k plus 1 true, of course you're making all the guys in gamma I true, because gamma I is a subset. And so whenever you've made all the gamma I guys true, you've made pk plus 1 true, then of course whenever you make all of these guys true, which there could be more, since you've also made these ones true, again, pk plus 1 has to be true on that interpretation, on the truth value assignment. And so you have double entitlement. Questions about this? So this is the key kind of move you'll make over and over again in these cases. Probably matters on this one homework problem. If you have some set of premises that's a subset of the premises open at line k plus 1, then whenever you make all the k plus 1 guys true, of course you have to make all the gamma sub I guys true. And so then any double turnstile you have from gamma i's, you also get an equivalent double turnstile with gamma k plus 1. So the book probably writes this down as some little lemma or something, but it's like, this is really clear, right? So if it's not clear, then think about it and prove it, because it's super important idea. So, oh yeah, and we've done a schematic derivation to hopefully better understand this. Here's our little picture. In this case, we have gamma I is a proper subset of gamma k plus 1. Because here gamma k plus 1 includes PM, whereas gamma I, whatever it is, all the stuff that's accessible above line I, does not include PM. Cool. All right, so let's do conjunction introductions. Now we're doing, the more interesting rules, still, super chill. So we probably want to draw a little picture for this one too. All right, and I'll try to use the same notation as what's on the things. So we definitely know that on the k plus 1 line, shown k plus 1, we have some q ampersand r, where again, these could be any sentences. So these are the meta language q and the meta language r. They could stand for any sentence. All right, so h and j. All right, so chilling above on line h, we got our q, and shown above on line J, we have our R. Now, of course, you could have these in, the opposite order. You could have J above H, you could have R above Q. Without loss of generality, assume that it's like this. Again, similarly, you could have, R and Q rather than Q and R. But our schematic picture stands in for these different cases. So by the induction hypothesis, since it's the case that H is less than K plus 1 and J is less than K plus 1, lines H and K are in the scope of our induction. And so lines H and J are righteous. And so for each of them, we have a double entailment relation. The set of assumptions that are open at line H semantically entail Q. The set of assumptions open at line J semantically entail R. And so our goal is just to show from this information that the set of assumptions open at line K plus 1 entail the sentence on line K plus 1. So when we do the and intro rule, it has to be the case, if we're going to justify this by H comma J and introduction, it has to be the case that both these lines are accessible at the K plus 1 line. If they weren't, if the Q, for instance, was in an assumption thing like this, then the Q wouldn't be accessible, we wouldn't be able to do that. So if we apply the rule correctly, then it has to be the case that this stuff is accessible. And so what this means, again, clear from the picture, is that the union of the gamma H and the gamma J is a subset of gamma K plus 1. So another way to write this is, from the picture, we can see that gamma H is a subset possibly equal to gamma K plus 1. And also we have gamma J is a subset of gamma K plus 1. So at this point, we're kind of like, all right, the key claim is whenever we make the guys in gamma H true, then Q has to be true. Whenever we make the guys in gamma J true, R has to be true. Now, if both these things are subsets of gamma K plus 1, then whenever we make the stuff in gamma K plus 1 true, we also have to make true everything in these subsets. And so we also have to make true Q, and we also have to make true R. But that just means we have to make true Q ampersand R. And that's what we wanted to show. We wanted to show that whenever all the guys in gamma K plus 1 are true, the sentence Q ampersand R is also true. So that's our proof in this case. So any truth value assignment that satisfies gamma K plus 1, where this is just shorthand for saying makes true all the sentences in gamma K plus 1, also has to satisfy gamma H and gamma J, and hence it has to satisfy by these relations Q, and it has to satisfy R. And so that just means that whenever you satisfy everything in gamma K plus 1, you also have to satisfy, i.e. make true, Q ampersand R. So that's so then we get to write this thing that we want to write, gamma K plus 1 double turnstile PK plus 1, and that shows that line K plus 1 is in this case also righteous. And so we finish this case. Any questions about this? So basically, for all these cases, the trick is just to figure out what is the right subset relationship between other lines, set of open assumptions, and the set of open assumptions on line K plus 1. You figure that out, often by the Hadronic picture, and then you just, reason the stuff. So we're basically, in all these proofs, the key thing to ask is, so if we satisfy, so maybe we'll put it like this, be more precise. So if a truth value assignment satisfies gamma K plus 1, then show it satisfies, i.e. makes true, satisfies PK plus 1. The key thing to do in all these cases. Cool, all right, conjunction elimination. So now we do and elimination for our proof. So maybe I'll erase what I just wrote so I can just type a little proof here. That seems structurally more elegant, right? So we're going to have pk plus 1. So k plus 1. We again have pk plus 1. Now it's coming from some earlier line whose name will get and bullet point and elimination. So we call this line, all right, I still haven't, line H. All right. So there's some line H that has something, some meta Q and a pk plus 1, or it has pk plus 1 ampersand Q. Again, there's no loss of generality here. So you could, at this point, you could say, without loss of generality, assume that the sentence on line H, which you could call, if you wanted to, pH, this pH, you could say, assume without loss of generality that pH is Q ampersand pk plus 1. You just pick one if you wanted to be concrete. So by our induction hypothesis, line H is righteous, and so we have a double turnstile from the gamma H's to the sentence pH. And so since the line H has to be accessible at line k plus 1 in order to do this rule, again, if this thing were not accessible, if it were in some subproof, then you couldn't write line H and elimination. So it has to be the case, do this rule, that Q and pk plus 1 is accessible. Cool. So again, this is our subset relation here. The gamma H's are a subset of the gamma k plus 1s. So all the assumptions that are open at line H are also assumptions that are open at line k plus 1. Or again, it's kind of intuitive. Like in this picture, for instance, like they share the same scope line. So there's some premises up here that constitute the gamma H's, whatever gamma H is in the scope of. And yeah, in this case, gamma k plus 1 just is gamma H. By the lights of how we drew it. Cool. So whenever you satisfy the gamma k plus 1 guys, you also have to satisfy the gamma H guys. That makes pH true, and pH is pk plus 1 ampersand Q. Now at this point, you just say, by the truth conditions, by the truth table for ampersand. Whenever you make true pk plus 1 ampersand Q or Q ampersand pk plus 1, you also have to make true each of the conjuncts. And so in particular, you would make true the conjunct pk plus 1. And so again, the set of assumptions open at line k plus 1 with semantically endowed pk plus 1. And so line k plus 1 is righteous. So this completes this case. Any questions about this? Cool. Unfortunately, we're not really about to eliminate the proof because there's still many more cases. But I think at this point, I think maybe we do 2 more cases and then we say we're good on this stuff. They all basically go like this. The next one that's interesting, I guess, is conditional introduction, because this involves a subproof. So this is like a new kind of case, since you have the subproof stuff popping up. So here are the pictures, probably particularly helpful. So PS12, do noon. We'll erase that. I'm saying noon because if I said 12, it'd be ambiguous, right? Everybody's like, 12, is that like 12 p.m. or 12 a.m.? And like you forget sometimes, like, what is 12 p.m.? Is 12 p.m. noon or is 12 p.m. midnight? 12 p.m. is noon, but you might forget that. And like, you guys have noticed I'm kind of a night person, so if I just said 12, you might assume, oh, he means midnight, but I don't mean midnight. So because basically my hopes and dreams are, which could be dash, I'm going to a Christmas party on that Saturday. My hope is if stuff is turned in by noon, I could start grading it. And then I could go to this Christmas party. I'm probably not going to finish grading it. It's going to be proofs and so it'll be long. And, people write insane things and I'll have to think really carefully. Because sometimes the stuff really is like, whoa, no, that's not going to work. But other times it's like, it initially seems to me like this is just totally wild. And then I'm like, no, actually this is a totally legitimate way of going on. Like that's how I had to really focus for the grading the quantifier logic identity statements, because people came up with schematizations that initially I was like, yeah, this just looks like ludicrous. And then I was like, oh no, they just had another way of writing this thing that was logically equivalent, but that Carnap didn't, because Carnap's just not that good with logical equivalences for quantifier logic. Probably because quantifier logic's not decidable. That's my guess on why it doesn't work that well. So I couldn't be like, oh, this is wrong, because it's not, the thing that I wrote in the solution. I'd be like, oh no, this means the same thing, so. Cool. Why are we talking about my hopes and dreams? We should be talking about conditional introduction. All right, so pk plus 1. So put that on line k plus 1. And then we're gonna have a subproof. Let's lose blue. I feel like these cases are taking long enough that maybe we won't get it completed. We'll see. Maybe we'll be sad. We won't start to be completed today. So, okay, so pk plus 1 has to be the form give q then r. So let's write that in there. So we definitely have q then r. And so, oh yeah, some line h and some line j. So up above, we got some line h, some line j, and on h we have q, and on j we have r, and this stuff is in a subproof. So q would have been assumed for conditional introduction, and we would justify line pk plus 1 by citing h hyphen j conditional intro. So this is our structural situation for dealing with this rule. And I think, yeah, so basically on the problem set, it might be the first problem. You guys have to do the case negation elimination. I'm asking you, I'm imploring you, please draw a picture because that will define your terms, essentially. If you don't draw the picture, it's just harder to define your terms. So draw the diagram, the schematic diagram, then it'll be very clear to me, what your line numbers are and what the relevant sentences are. So by the induction hypothesis, we have gamma h double entails q and gamma j double entails r, just because again, h is less than k plus 1, j is less than k plus 1. So they're righteous by assumption. So basically, we're just going to go by cases to do this one. So either gamma k plus 1 satisfies q or it doesn't, because any truth value assignment has to either make a given sentence true or make that given sentence false, because any truth value assignment assigns true or false to every atomic sentence, and the truth or falsity of a given sentence is just a function of the truth and falsity of its atomic guys. That's our recursive structure for SL. So if it's the case that gamma k plus 1 doesn't satisfy q, then it trivially satisfies the conditional q and r. Because if it doesn't satisfy q, then it makes q false. And whenever q is false, the conditional of q then r is true. So you just reason by the truth table on that. So that's our first case. Otherwise, gamma k plus 1 does satisfy q. Then we notice the following. So again, we have one of these subset relationships. We notice that gamma j, the set of assumptions that are open at line r, this is a subset of the set of assumptions open at line k plus 1 union with q. So the thought here is gamma k plus 1 doesn't have q in it, but if we just union these guys together, so if we have gamma j, then this is contained in the gamma k plus 1's union with q. Because basically it's like, if you covered up this stuff, then by the way we've been reasoning before, the gamma j guys would be contained in gamma k plus 1. But here at gamma j, there's an additional assumption available, q. And q is not available at gamma k plus 1, at least not as far as we know. So in order to get the earlier thing to be a subset of a later thing, we have to tack on the additional thing that we added. So this is, I guess the new idea in this case. the new little wrinkle that arises, is to be able to justify this fact that gamma j is a subset of gamma k plus 1 union q. So, okay, so if gamma j, so whenever we satisfy all the guys in gamma k plus 1 and we satisfy q, then that means we've satisfied everything on the right-hand side, the bigger guy. And if you've satisfied all the sentences in the bigger guy, then you also have to satisfy all the sentences in the smaller guy. And so in this case, not necessarily in this earlier case, but at least in the second case, you've also satisfied all the gamma j guys. And we know that line j is righteous, and so since gamma j semantically entails R, it must be the case that this bigger guy, gamma k plus 1 union q, also semantically entails R. So whenever you make all the things in gamma k plus 1 and all the thing, and you make q true, you make R true, well that just means whenever you make gamma k plus 1 true, in this case, you're also satisfying if q then R. Because q would be true, and R would be true, and whenever the antecedent and the consequent are both true, the conditional is true. So you couldn't, the stuff in this bullet point, you couldn't say this in general. It wouldn't hold in this earlier case where gamma k plus 1 doesn't satisfy q. But at least in the second case where gamma k plus 1 does satisfy q, then if you satisfied everything in gamma k plus 1, you satisfied everything here. And so q would be true. We've just shown that R would also have to be true. And so this conditional would have to be true. And so then we're like, okay, in either case, whenever we satisfy all the stuff in gamma k plus 1, we also satisfy if q then R, which is bk plus 1. And so this line is righteous. So this proof, is definitely more subtle to reason through this case. It may be true that in this slide, I left some stuff unsaid that in principle I would prefer was written explicitly. Some of the stuff I said verbally. So in your proofs, feel free to write some of that stuff. You don't have to go overkill, The key thing is if you rely on some subset relationship, you have to note that and at least say something like, I don't know, by the derivation drawing. There's more involved ways you could, if I really wanted to justify the subset relationship, I'd have to write a sentence involving referencing the scope lines and being in the scope of blah, 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 and it's the book does stuff like that, you can do stuff like that, maybe it's good practice. Cool. So other thing you can do, so this is, I guess, what the book does at this point, they again just prove some little lemma. They prove that, I think what they prove is when you have this relationship thing, and I should have little braces here around Q. So when you have this thing, and it entails this R, then this set entails the conditional. So we've just basically proved their little lemma in this little step, rather than, have to clutter our minds with a lemma. Well, in the completeness, our mind will be cluttered with many lemmas in the completeness group. But here at Soundness, we're trying to be lemma-free on this. All right, so we have negation intro. This one's super analogous to the homework problem. So basically, if you can do negation introduction, you can do the negation elimination homework problem. You're just going to do the same steps. So let's draw another little picture. So on line k plus 1, we're going to have pk plus I, and pk plus I is going to have the form of some negated earlier sentence whose line number is, we're just going to set Q. All right, so what line number did we give Q? All right, set H again. All right, so we put some meta Q on H where we started line H with a subproof. So we assumed Q or negation introduction. So you assume the unnegated thing in the hopes of deriving some contradictory pair of sentences, and then you'll pop out of your subproof, introduce not Q, cite the subproof. What other line? Oh, you just H and M. Okay. oh wait, no, we already, H, oh, J now, okay, J now. Alright, so, somewhere in our subproof on line J we have R, somewhere in our subproof on line M we have not R. These are our contradictory sentences. So this is what we need in order to apply negation intro. Then you set whole subproof H hyphen M, and you write negation introduction. So this, diagram just comes from the fact we're assuming we're doing some legitimate instance of negation intro. And given our induction hypothesis, we have all these double turn styles. Just like in this proof, really the one that mattered was this double turn style from gamma J. We didn't actually really use this one. In this proof, we're really just going to use these two double turn styles. Like gamma J semantically entails R, and gamma M semantically entails not R. By the induction hypothesis, because again, we're assuming all of the earlier lines are righteous. And so this is our righteousness property. So, and we're trying to show, so NTS you just need to show. Always feel free to write NTS just to clarify to yourself what you need to show, given what you have. So here we notice that gamma J and gamma M, they're both subsets of gamma K plus 1 union Q. So similar proof idea. Gamma K plus 1 itself doesn't necessarily have Q in it. But if you add in Q by unioning, then it's the case that the gamma J guy is contained in gamma K plus 1 union Q. And likewise for gamma M. So since these guys are both subsets and they both entail R and not R, that means if you make everything in gamma K plus 1 true and you make Q true, so you make this union, everything in it true, then that would have to entail R and not R as well. Questions about this so far? Okay. So again, this is just meaning, given a truth value assignment that made everything in gamma K plus 1 true and made Q true, since these guys are smaller than this thing, that would mean you made gamma J true and you made all the things in gamma M true. That would mean from these double turn styles you've made R true and also that you've made not R true. So any truth value assignment that satisfies this bigger guy, gamma K plus 1 union Q, it has to make both R and not R true. But that's impossible. You can't do that. You can't make R and not R true in classical logic. Maybe there's a sense you could do it in paraconsistent logic, but we're not doing paraconsistent logic. So paraconsistent sounds like supernatural. We're very normal. This is a very vanilla class. So this is impossible. There can't be any such truth value assignment. And so this just means that this bigger thing, gamma K plus 1 union Q, it has to be unsatisfiable. It has to be the case that there's no truth value assignment that satisfies gamma K plus 1 union Q. And so again, this was the key fact that we used a bunch for trees, and that we're using here as well. If this thing is unsatisfiable, that just means that whenever you make all the things in gamma K plus 1 true, you can't make Q true as well. So that means Q would have to be false. And if Q is false, then not Q is true. So whenever you are in a position to write this bigger thing is unsatisfiable, so some set unions some sentence, that means if you make all these guys true, this one can't be true, it has to be false, and so its negation has to be true. And that just means making all the gamma guys true means that not Q has to be true. And so you get to move from this thing being unsatisfiable to a statement about a double turn style. So again, you want to be comfortable making this kind of move from big things unsatisfiable to slightly smaller but still big things semantically entails the negation of the sentence. So, any questions about this case? So you got, so homework problem, one of them, it's basically this, you're just gonna modify some negation symbols and stuff, right? So just draw the picture in the homework problem, draw just like I drew a derivation here. Draw something to define all your things, and try to reason precisely. Again, if the book has some lemma that essentially does what we've just done here. If you wanted to, you could appeal to that lemma, you just have to cite it. You know, the book gives some name for it. All of the lemmas have names. What would be a nameless lemma? I wonder if there's a lemma called the nameless lemma. But if you call a lemma the nameless lemma, you've given it a name, and so it's not really the nameless lemma. Could there be a nameless lemma? All right, let's start completeness. So we're not gonna finish this monstrosity today, but we're gonna introduce some of the key concepts, and we might even get to the proof sketch. The proof sketch itself is really easy. So in some sense, the proof is like, really not that complicated. There's just one step that takes many, okay, this was good, that was bad. Bad kids, they will not get extensions on their problem sets, barring extenuating circumstances, you know, which I'd have to trust them about. So, the thing that could be a little confusing in the completeness proof is we will have two notions of consistency running around. I'm going to try to use different words to keep them separate. The book uses consistent in SND versus truth functionally consistent. For the semantic thing, we're going to use satisfiable, because satisfiable sounds very different from consistent. Now the idea here is really similar again to what we did with trees. With trees, we had a syntactic notion of consistency, which was basically having a complete open branch. If you had a tree with a complete open branch, we've said that the tree was tree consistent, and we basically were like, okay, using the complete open branch, we could construct a truth value assignment that satisfied all the sentences on the tree. We're going to do a similar thing here. We're going to have a notion of consistent in natural deduction, which basically is really similar to the complete open branch. It basically means you never have a sentence and its negation appearing in the deduction. You never have a contradictory sentence pair. We're going to show whenever that happens, we could use our syntactic thing, the derivation, to construct a truth value assignment that satisfies all of the premises and the conclusion. So the proof idea in some sense is really similar, just like we moved from complete open branch, which was consistent for trees, to a truth value assignment. Here we move from consistent in our sentential natural deduction, which means you don't have a contradictory sentence appearing, to a truth value assignment that satisfies everything, that shows that the sentences on that deduction, at least the assumption ones, are satisfiable. So that's the basic proof strategy is we want to get to a truth functional notion of consistency, namely satisfiability. We're going to piggyback on a syntactic notion of consistency in order to do that. But you got to keep them separate, these two notions. So, the semantic one we know and love. There's a truth value assignment that satisfies every sentence in the set. Now we have the syntactic notion of consistency, which we haven't talked about before. So this is a completely new thing that we're defining. But it is, in many ways, analogous to tree consistency. So if you remember anything about that, then, if you probably don't, but maybe you do, then this is, similar. So a set of sentential logic sentences is SND consistent. This is what we landed on. It doesn't sound great, SND consistent, better than STD consistent, we might say. We're grateful for that. So provided you can't derive contradictory sentences. So essentially what we're meaning by SND consistent is, come to me, board. I guess you can't go. All right, never mind. You can't get to that one. We can get to this one. We'll use the boards we have. So a set of these guys is S and D, yeah. So if you had some set delta, so put these guys, some delta 1 and some delta 2 up to delta n, we're basically saying if you never have in the scope of these deltas some sentence R and not R, so if this never happens, then we would say delta is SND consistent. In contrast, delta is S and D inconsistent if there is at least one derivation from the delta guys that results in contradictory sentence pairs. So our basic idea, which right now maybe it's not obvious how this would matter for proving completeness, but it will become clear, is we'll show that if a set of sentences is consistent in S and D, then it's also semantically consistent, i.e. satisfiable. And so I have contrapositive, if a set's unsatisfiable, then it is inconsistent in S and D. And this will be our major lemma that we'll have to prove, some notion of a consistency lemma that basically says, if you have the syntactic notion of consistency, you can infer the semantic notion of consistency. This will be the main thing to show, which, you know, is kind of similar to what we did with trees. So recall a set of SL sentences is satisfiable, provided there is a truth value assignment that makes them all true. So the book uses truth functionally consistent here, but then it just seems like there's the word consistent is just running around too much. So we're going to use satisfiable for this. And this is better too because when we do this all over again next week, we don't have truth functional consistency for quantifier logic, but we do have satisfiability. Satisfiability is the more general notion. We never really talked about it in lecture because it seemed too tedious, but we technically define the truth conditions for our quantifier logic using satisfiability semantics, and we will use that in our proof. So satisfiable is the more general notion anyway. So this is semantic, has to do with truth. Book says truth functionally consistent. And the thing is just to contrast this with consistent and SND. They mean totally different things. They both involve the word consistent. Don't mix them up. So to define this thing, consistent in SND or inconsistent in SND, we basically say, let gamma be possibly infinite set of these SL sentences. Something is inconsistent in SD, provided the following. From premises in gamma, a finite number of them, you can derive contradictory formulas R and not R that are in the scope of the main scope line, i.e. in the scope of these premises. So you have inconsistency, S and D inconsistent, so S and D inconsistent, provided there is some, basically, there exists an S and D derivation that has the following form from these guys, delta 1 to delta n, whatever they are, you derive somewhere in the scope of these guys an R and an R. So this is what it means for these to be S and D inconsistent. And this is kind of like going to be one of the main proof ideas. So you want to basically when you're doing a proof with this stuff and you encounter a set of premises that are S and D inconsistent, you want to say immediately to yourself, okay, cool, this shit's S and D inconsistent. That means I could write down a derivation that has an R and a not R. And you might recall that's really powerful because from an R and a not R, you can derive anything from negation introduction or negation elimination. And so often in these proofs, there'll be a step where you're like, oh, okay, I have a set of premises that are S and D inconsistent, therefore I could derive an R and a not R from them. That means I could do negation introduction or negation elimination, and that will be the linchpin in carrying on. So that's the key thing to hold in your head about this. This definition is very important, and to have this picture in mind. So in contrast, if you have something that is consistent S and D, that just means it's not S and D consistent. So there's no derivation from premises in gamma resulting in contradictory formulas. Where again, really the reason that our proof is working for the infinite case here is because this notion of consistency is the negation of the inconsistency, whereas for trees, tree inconsistent was not the negation of tree consistent. And so this is really why we can handle the infinite case here. So that's cool. So some other words which we could say, I think I settled on S and D inconsistent. It seemed clear and short enough, but you could say derivationally consistent. Sometimes we'll say, yeah, consistent S and D, but I think I ended up reverting to these S and D hyphen consistent things, because they're slightly shorter. So, yeah, so remember, syntactic notion, not do with truth value assignments. All right, so I guess we'll start the proof sketch on Wednesday. And the proof sketch really just takes like 2 slides. So in a sense, I could spoil it right now, you know, but I don't think I can do it in a minute. So, cool. Thank you guys for focusing through this. On Wednesday, it's going to be, you know, even more of a whoa, what's happening? Super chill. This is the straightforward part. And then the last part is also straightforward, but it's tedious. And so that's what takes the most effort. And the homework problems 2 and 3 are basically throwing you into the last stage of the proof, where you do the 2 kinds of tedium that arise. So, and by the end of everything, we'll have proved it, but we'll have totally forgotten what the actual proof idea is. We'll be so lost in this lemma. We'll be like, why were we doing this again? So, just to recap the key terminology that we'll use here. So you just want to keep separate these 2 notions of consistency. One is syntactic, and the syntactic notion involves not being able to derive contradictory sentences. So if you're consistent in S and D, if from this set, there's no way to derive some sentence R and its negation. Now the semantic notion of consistency, we'll just call it satisfiability so that we don't use the word consistent twice, because that would be more confusing. So we'll say satisfiable. This just means semantically consistent. And this is what the book calls truth functionally consistent. So this has to do with truth value assignments. It has to do with there existing at least one truth value assignment. You know, what next week we'll call an interpretation when we generalize that to quantifier logic. One interpretation, at least one, that makes all of the sentences in the premise set true. So that'll be the semantic notion. And the key thing we'll do today is to prove this lemma that you can go from the syntactic consistency notion to the semantic one, and so by the contrapositive, you can go from unsatisfiability, so a lack of the semantic notion, to a lack of the syntactic notion. So this is the key thing. So this is semantic notion, satisfiable, truth functional consistent. And then we contrasted this with the syntactic notion, where the key thing is in pink here. This is the useful bit. Whenever you have some set of premises that are inconsistent in your derivation system, that just means you can start with a finite subset of them at the top of the proof, and you can derive in that proof R and not R. So the thing that you'll use in parts of the proof, and I guess at least one of the problems, is when you have these guys. So you know that gamma, S and D inconsistent. This just means there exists delta finite subset of the gammas such that you got these delta guys, delta 1 through delta n, these would be your premises, and somewhere along the line in your proof, you'd be able to derive some sentence R and its negation from some rule, you know, not necessarily what, but if the thing is S and D consistent, I'll tell you this is possible. There's some finite subset, could be multiple ones, but there's at least one, and you can get R and not R. And so that's useful because, as you'll recall from the rule schemas for negation, elimination, and negation introduction, whenever you have R and not R, you can derive anything using negation intro or negation elimination. So that's where the R and not R will be useful. So in contrast, you're consistent in S and D if you're not S and D inconsistent, namely if it's impossible to do this. So when you see the syntactic notion, think about proofs. Think, oh yeah, this is telling me there exists a kind of derivation with a certain property. All right, so let's go back to slide land. All right, and you haven't missed anything, Daniel. We just reviewed terminology, so now we'll go to the proof sketch. All right, so this is our goal. We're just going to prove it directly. We want to go from a double turnstile to a single turnstile. Make sure you guys are in a good file. So we want to do this. So we're going to assume that our set gamma, which could be infinite, semantically entails P. We're going to try to get to the claim that, okay, we could derive P from some finite subset of the things in gamma. So we'll assume this. And recall, so this is, key fact that we used over and over again, that we use with trees as well. Whenever you have gamma semantically entailing P, that means whenever you make all the gamma guys true, you have to make P true. And so if you made all the gamma guys true, you couldn't make not P true. So if you union the gamma guys with not P, this bigger set has to be unsatisfiable. So from gamma double turnstile P, you get to conclude gamma union not P is unsatisfiable. Are there any questions on that? This is a key fact. You could always rederive. We just rederive it verbally. So hopefully it's intuitive. So now what we do is this consistency lemma that we're going to spend a lot of time on. So when we have a set that is S and D consistent, the syntactic notion of consistency, then we can go to the semantic notion. That set is satisfiable. So basically we're going to use the contrapositive of this thing, because now we've seen right here that we have this unsatisfiable set, so we'll feed that into the contrapositive of the consistency lemma. So here's our lemma. Any S and D consistent set of SL sentences is satisfiable. And so contrapositive, if you have a set that's unsatisfiable, so it's not semantically consistent, then it's not syntactically consistent. It is S and D inconsistent. And so we just saw that from the thing we're assuming, we have this unsatisfiable set of gamma union not P, and so this set is itself S and D inconsistent by this contrapositive. And so in virtue of this thing being S and D inconsistent, that means we're going to be able to do this. Get an R and a not R. And we're like, whoa, why would this be useful? Because you could assume P right above the R for a negation intro. And then you could assume not P. Assume not P for negation elimination. Yeah, because we want to get P. We want to convert this double turnstile to a single turnstile. So by this contrapositive, we see that gamma union not P is S and D inconsistent. And so that means that we can get some contradictory R and not R from gamma union not P, so we can just use negation elimination. Basically, we're just saying we can slip in so we can slip in a P right here, a not P. So assume a not P. Assume this for negation elimination. And then you get your R and your not R from the fact that we have this gamma union not P is S and D inconsistent. So again, there's some finite subset of the gamma guys, the deltas, such that when union with not P, when not P is accessible, you can get these contradictory guys. And then we can pop out of our derivation and we can write P, and we justify this by negation elimination on whatever lines are these subgroups. We can give them arbitrary lines m through n. So we write m hyphen n, negation elimination, and we got P. And so this would just mean at this point that we had delta single turnstile P. Since delta is a subset of the possibly infinite gamma, this would also mean that gamma single turnstile P And so we will have completed the completeness proof. So, yeah, okay. So this is just refresher on negation elimination, basically what I just said. You have this thing, set that's S and D inconsistent, then you can get P. So we start with these delta guys, we introduce not P as a subproof, and then since the gamma guys with not P is S and D inconsistent, we can get our R and not R within the scope of this finite delta and the not P. That's what we did for our little yellow subproof. And discharge this assumption not P. Now the P that we want is just in the scope of the delta guys. We're no longer using the not P. It's just in the scope of the delta guys, and so we can write delta single terms out P. Delta derives P. And since delta is a subset of gamma, we have gamma single turns out P. So yeah, so that's what we want. So that's the whole proof. That's the whole thing. And you think like, wow, you know, what else is there to talk about? And the whole thing is we gotta do the consistency lemma. Yeah. So we just gotta prove this. You know, it's just telling us we can go from the syntactic notion to the semantic notion. And you think, you know, how could this be this bad? And it is. It kind of sucks, you know. And it's like, whoa, what a bummer. So we're gonna do three proof stages, and the first two are pretty chill. So this is basically our idea is we're not going to directly show that any possibly infinite set that is S and D consistent is satisfiable. We're going to use a crutch. We're going to construct some bigger S and D set. So we're going to construct something, you know, gamma might already be infinite. We're going to construct a superset that obviously could also be infinite, but contain our, in this sense, smaller gamma. So our size here is given by subset relationship. So gamma star is bigger in the sense of being a superset, and it's going to have this property being maximally S and D consistent. So define a new thing with a new property, and this notion of maximal S and D consistency, this will be what we use to get the satisfiability. It'll just be easier to construct a truth value assignment that satisfies a maximally S and D consistent set. And the intuition here, which might be on one of these slides, is this maximal notion. It's very analogous to a complete open tree. Complete open tree, you know, you've resolved everything, there's nothing else you could add, and so when you have a complete open tree, and you saw there were no inconsistent sentences, no contradictions, you were like, oh great, I can construct a truth value assignment. With the maximal thing, you've made it so big, you can't add anything else to it without breaking consistency. And so it's very analogous to a complete open branch. And for that reason, it'll be fairly straightforward but tedious to construct some truth value assignment that makes true every sentence in the gamma star. And clearly, if you make every sentence true in the bigger guy gamma star, you've made every sentence true in the smaller guy gamma. So if you can show that your superset gamma star is satisfiable, you'll have shown gamma satisfiable just from assuming that gamma is syntactically consistent. So that's what we want to show. So yeah, so since gamma is a subset of gamma star, then this truth value assignment can satisfy gamma as well. Yeah, okay. So this is the little analogy, which could be totally useless if you don't remember anything about trees. So trees, we have these complete open branches, and here we'll have maximal S and D consistency. The maximal notion is kind of like the complete notion. There's nothing else really to add, you know, to it. And the S and D consistency is like openness. Openness was there weren't any contradictory pairs occurring. That's really what S and D consistency is. There's never any contradictory sentences are and not are occurring in any derivation. Cool. So the third stage, we got this lemma that sucks, and we have induction. So this is problems 2 and 3 are the things, you know, that practices. Problem 2 is for this tedious lemma. Problem 2 is the one that really sucks on the problem set. Everything else is really chill on the problem. Problem 2 is the one that's going to take you probably the same amount of time as like 3 or 4 other problems, you know, possibly. So, and problem 3 is chill, because the induction part, the actual induction step is not that bad once you solve problem 2. So here's our definition, which, you'll probably want to memorize this or just have this, in RAM, at least for the problems. Maximal S&D consistency is just S&D consistency plus some further property, like the maximal property. So to be maximally S&D consistent, you gotta be S&D consistent. So remember what that means. It just means you can't derive these contradictory sentences from any derivation, starting with premises and gamma. That's the first thing. And the second thing is, if you're gonna add something to gamma star, then it's gonna make the resulting set S&D inconsistent. So basically, gamma star is as big as it could possibly be without becoming inconsistent. If you were to try to make gamma star any bigger, then you would break syntactic consistency. So any other thing you add to gamma star would make it S&D inconsistent. So, and this will be the useful proof idea. You'll often do a proof by contradiction. You'll consider, well, imagine, that I could add this thing to gamma star, blah, blah, blah. Well, then it'd be S&D inconsistent. We could derive stuff then, from this R not R, and boom. Cool. So this just means for any P that's not in gamma star, the union of the set P with gamma star is S&D inconsistent. So our thought here, the reason we're doing this is it's fairly straightforward to show that from maximal S&D consistency, you can get satisfiability. And of course, as we'll show, every S&D consistent set is a subset of a maximally consistent set. We'll show this really by the fact that when we construct a maximally S&D consistent set, we don't assume anything special about our starting S&D consistent set. We start with some arbitrary gamma, that's S&D consistent, don't assume anything special about it, and then we construct a maximally S&D consistent set from that gamma. And we didn't assume anything special about that gamma, so you could always do this. So really the proof idea here is just like a universal introduction. Remember the restriction on universal introduction, your proof rule is you can't have already assumed really anything about the constant A. You prove some sentence PA, where you didn't say anything special about little a, and then you can say, okay, for all the things, P, everything's P. So we're doing the same thing here. And then we piggyback on this maximally S&D consistent set to show that any arbitrary S&D consistent set is also satisfiable. Any questions about this definition or why we're doing this? Why you came to class this morning? Why any of us are here right now? What is the meaning of life? Cool. Glad we solved that. So now we go into these stages. So stage one, we're just going to construct this gamma star. So here's our arbitrary S&D consistent set. It's constantly infinite. It's gamma. So this gamma could already be gamma star, for all we know. It already could. So it's not the case that gamma is necessarily a proper subset of gamma star. Typically it would be. So we're going to do this thing of enumerating the well-formed formulas of sentential logic. We basically just want to set up a map between the sentences of SL, there's infinitely many sentences of SL, and natural numbers. So that every sentence of SL has its own number. So, and then when we've enumerated these SL sentences, then we can actually talk precisely about adding any given sentence to our set gamma to form a bigger set. We'll just have an enumeration of stages of adding these sentences to gamma. So you think, how are we going to do this? It's really kind of just like the dictionary. So I think probably on the next slide I'll explain how we do the enumeration, but just take for granted right now that you could enumerate. It's probably pretty intuitive. Then what we would do is we would take the first sentence in our enumeration. It'll turn out, based on the conventions we choose, it'll be A. So the atomic sentence A is our first sentence in this enumeration. Now, if we can add the sentence A to gamma without the resulting set becoming syntactically inconsistent, then we'll let gamma sub 1 be the union of gamma with A. Now, if instead when we add A to gamma, we would get syntactic inconsistency, then we won't add A. And so if that were to happen, we would just let gamma 1 be gamma. So that either way, gamma 1 is going to be S and D consistent, given that gamma is S and D consistent. So then we do this again, so we go to the second guy. The second guy is going to be the sentence letter B, and if we can add B to gamma 1 without the new thing becoming inconsistent, we'll do that. And we'll let gamma 2 be gamma 1 union B. Otherwise, if adding B would make the resulting thing inconsistent, then we'll just let gamma 2 be gamma 1. And then we'll just move to the next sentence. And so, assuming we can enumerate our sentences, we'll just do this for every sentence of SL. Now this is in scare quotes because clearly this is an infinite procedure. You couldn't actually do this. This is not a thing you could construct in finite time. But mathematically, if you're on board with infinity, then this is a well-defined set. Gamma star is defined as the infinite union of each of these gamma k's. So there's infinitely many gamma k's. There's one gamma k for every number, every natural number. Really not for every, as we'll see in our enumeration, it's not. Yeah, but this is fine. And then the gamma stars just take the unions. And so you can do this. It's all good. So now we're like, okay, what's this enumeration business? Really simple idea. We're really just relying on an analogy with words. So you could take all the words in the dictionary and you could enumerate them by their length. And if you have two words that have the same length, you would just look at the alphabet. And you would say, okay, well, a 5-letter word that starts with A comes before a 5-letter word that starts with B, because A comes before B in the alphabet. That's pretty intuitive, right? So we're just going to impose an alphabet on our symbols. So SL sentences, they just consist of a finite number of symbols. We're just going to arbitrarily impose an alphabet on the symbols so that one of our symbols we say is the first in the alphabet, like the letter A. We could have let the letter A be the last letter in the alphabet. It ended up being the first one. That's an arbitrary convention. We are, because we're positive people, we're going to let the negation sign be the first thing in our alphabet. And then we'll go through our connectives, and then we'll hit the numbers, because remember we can use numbers as subscripts of sentence letters. So, we often don't talk about these subscripted sentence letters, but they're there. So, we have things like A1, B52. These are all atomic sentences. And similarly, when we go back to quantifier logic, remember we can label our constants, our terms, with subscripts as 1 as well. So we can have things like A101. So we have our 10 digits in there, and then we have the capital letters from A to Z, where these are all atomic sentences. Cool. So we're just gonna pick some numbers, and we're gonna index these guys. So negation sign is 10. The letter Z is 55. In our convention, we skip a couple numbers, and we send 0 to 20, and we send A to 30. So I'm just following what the book does here to be consistent. You could do anything else you wanted, as long as each one of these symbols was ordered and indexed with some number. So, and clearly you don't want to use, it'd be confusing to use 0 through 9 again. So that's why we start at 10. So then, if I give you a sentence of sentential logic, it's going to have a unique positive integer that you would read off just by going from left to right, and you replace every symbol you encounter with its index from left to right. So since A gets assigned 30, and A is A is of these symbols, A is the first thing we hit that by itself is a sentence. So even though negation sign has a lower index, negation is not a sentence. So, you want to start at sentences and then find the sentence that has the smallest index. That's going to be A. And then B would be the next smallest. We go up to Z, and then at that point, now we can start adding connectives. So you get not A, and not A would just be 10 for the negation and 30 for the A. Not B would be 10 for the negation and 31 for the B. And then, we would just proceed in this fashion. So every sentence you could write would have its own number, and the numbers would be ordered numerically. So this is our enumeration scheme. Any questions about this? Cool. And again, it's like the idea here is really intuitive. It's like, given you can enumerate this stuff, then of course we can construct the maximal superset in this way. We can just ask at any stage, is the kth sentence something that, when added to gamma, would remain consistent syntactically, or is the kth sentence something that, when added to gamma, would make it inconsistent? And if it's the latter, then we don't add it, and we just let the new gamma k be the same as gamma k minus 1. Cool. So now this is stage 1. We've defined our gamma star, and it's pretty obvious at this point gamma star is also S and D consistent. We basically defined gamma star so that it's S and D consistent. But we probably, so we have to, so we basically just shown this, we'll probably reset it. And now we have to show, in particular, the maximal part. We have to show that gamma star is maximally S and D consistent, where, remember, you just recall the definition of this thing that I'll abbreviate sometimes, M, S and D, C. So M, S and D, C means it's got to be consistent in S and D, so you can't derive contradictions. And additionally, if you add any other sentence to gamma star that's not already in gamma star, it would make the resulting set syntactically inconsistent. So that's the main thing you have to think through. So we'll just prove these two things. Assume for contradiction that gamma star were inconsistent in S and D, well then you'd be able to derive, some contradictory guys. So we have some finite set of sentences, delta, that derive some contradictory pair, R and not R. And this delta would be finite, so there'd be some k, remember the naturals, such that delta were contained in a gamma k. Because the finite delta is contained in gamma star, and we form gamma star just by this iterative procedure of adding sentences. So if you have a finite guy, delta, it's going to have to be contained in one of these gamma k's, as we went along from gamma 1, there was gamma 50 to gamma 100, to gamma 1,000,000, to gamma star. At some point, delta would have to be in this gamma k, and so gamma k would also have to be S and D inconsistent. Are there any questions on this so far? Just clear, just train of thought. I understand this is not the most exciting stuff. I don't really know how to make this more exciting. We're doing our best, right? All right, so, we, by definition, gamma k had to be S and D consistent, basically. When we were constructing gamma k, we wouldn't have added the kth sentence to it if it would have made it inconsistent. So, this is our general definition of gamma k. If we had, p sub k is our kth sentence in our enumeration, then gamma k plus 1 is either gamma k union this sentence pk, provided that the union thing is syntactically consistent, or gamma k plus 1 just stays put at gamma k and equals that. And so either way, gamma k, or in this case gamma k plus 1, has to be S and D consistent. So, we have some contradiction here, because we're saying gamma k is syntactically inconsistent, but we know from construction it is syntactically consistent, so that's impossible. So the thing that we assume for contradiction must be false. It has to be the case that gamma star is S and D consistent. So the book does an induction here. I spared you at least one induction in this class because I just don't think it's necessary to do induction to show this. This proof seems fine. So the book's doing some even more tedious shit than what's necessary, so. But you can, you know, if you want to read the induction, you can read all about it, you know, on the page. So. All right, so now I have to show the maximum part, and I see, okay, blue and black do not show up well together on that, so that's good to know. All right, this little blur is maximally. So again, we'll just do a reductio. So assume that our gamma star was not maximally S and D consistent, despite the fact that it is S and D consistent. And so this is a little trickier to state what exactly this means. So we'll walk through this. So we're assuming that, you know, to do this reductio, we're assuming it is not the case that for all of the additional sentences, adding it to gamma star would result in an S and D consistent set. So remember, the second part of maximal S and D consistent was this thing not in red. It was the claim that for any additional sentence, if you add the gamma star, you'd make it S and D inconsistent. So if you're contradicting this, you're assuming it's not the case that this second thing. And we're not going to contradict the consistency part, we just show the consistency part. So we only want to do a reductio on the remaining second part of the definition of maximally S and D consistent. So that's what we're doing here. We're assuming it's not the case that the second part holds, where the second part is, if I were to add any additional sentence, it would make it inconsistent. So remember, if you negate a for all, you get an existential. So the negation of for all is this means there exists at least one sentence such that you could add it to gamma star, and the resulting bigger set would be consistent still. So what we're assuming for a contradiction is that actually we missed something. We're assuming in our enumeration we missed some sentence, Q, such that we could add Q to gamma star, and the union thing, gamma star union Q, would still be consistent. This is what it means to assume for contradiction, that this consistent gamma isn't maximally consistent. Questions about this? Logic happening? We're happy to be here and not the screaming baby, right? So by the end of this class, you will all be screaming babies, at least on the inside. So, cool. Yeah, so, you know, we would have considered Q at some stage. You know, again, considered in script, scare quotes, because, you know, a finite mind like us is not doing this considering, because it's an infinite, you know, it's a super task. We can't do it in finite time. So, if this Q, you know, were not a gamma star, then that would have to mean that, you know, if we would have, you know, if we added it, it would have made it to the gamma K S and D inconsistent, because Q just is piece of K. We're mentioning, you know, Q has some number in our enumeration. So if we didn't, you know, already put Q in gamma star, that means when we considered Q, we saw, oh shit, it would have made the thing, you know, inconsistent. So Q union gamma star has to be S and D inconsistent, but that contradicts the thing we just had said here, namely that there exists some sentence Q, such that you could add it to gamma star and make it S and D consistent. So again, we have a contradiction from this assumption, you know, assume it's not the case that this thing's maximally S and D consistent, and so it has to be maximally S and D consistent. So you can't add any Q to gamma star while preserving S and D consistency, and that just is the second condition. Any questions about this? Cool. So this is the end of stage 1 and 2, and so now we hit the shitty part. We go to stage 3. So this is our consistency lemma, and we got 40 minutes, and so we might, I don't know, we might get through this with time to spare, and then if we have time to spare, I'll give some hints on the homework question perhaps. So, whew. All right. So we got to prove this thing. So remember, our ultimate goal is to show the consistency lemma, and the consistency lemma is basically this thing, but without the maximal part. So consistency lemma, which is what we really want, is if you have S and D consistent, then you have satisfiable. We're going to prove a less general case of this. We're going to prove the maximal consistency lemma, which is any set that is maximally S and D consistent is satisfiable. And then we'll just note, well, hey, we showed that any S&D consistent set is a subset of the maximally consistent one. That's how we constructed our gamma star. And so once we've proven this, the thing we actually want, the consistency lemma, just falls right out. Because given a consistent S&D set, it is a subset of the maximally consistent one. That maximally consistent one is satisfiable, and so the regular gamma that's not necessarily maximally consistent is also satisfiable. Is that clear? Do I make myself clear? All right, so yeah, so we're just trying to show that there is some truth value assignment that satisfies every sentence in gamma star, and we're just going to construct this truth value assignment. So again, this is just like what we did in the completeness proof for trees. At this point, we had a complete open branch. We constructed a truth value assignment that satisfied every sentence on the branch. Here we have something very much like a complete open branch. We have a maximally consistent set of sentences, which basically means no matter what derivations you write down, you're never going to have a contradiction appear. And given that state of affairs, which is a purely syntactic state of affairs, we will construct a truth value assignment. And remember, for the trees, our truth value assignment relied on this idea: make an atomic sentence true if and only if it appears on the complete open branch. Here we're going to have a really similar idea: make an atomic sentence true if and only if it belongs to gamma star, if and only if it belongs to the maximally consistent set. So any atomic sentence that isn't gamma star, our interpretation I will assign it true. And any atomic sentence that's not in gamma star, which is analogous to not being on complete open branch, that will be assigned false. So, cool. So this is our proof idea for any, so since we have this thing that's M, S, and D, C, for any sentence Q, not necessarily a comma, just any sentence Q, either Q is in gamma star or not Q is in gamma star. You're either in the club or your enemy is in the club. It's basically the state of affairs. So we'll think about gamma star as being a club. It's the club that everybody wants to belong to and go to, party hard in the club gamma star. And if your enemy, not Q, is in the club, then you, Q, cannot be in the club. So this is a key fact about this club, where again, this makes sense, right? Because imagine that you and your enemy were in the club. Well, then you and your enemy would be the R and the not R. You would be the contradictory pair, and so the club would be inconsistent, and the club would collapse and go bankrupt, and everybody would run out screaming, and we'd call the police, right? And that'd be a bad night out. But these things happen, you have to be prepared. So. But we're trying to avoid that. We're trying to keep this club stable. So in particular, this is true for the atomic guys, and so we'll define our truth value assignment by focusing on the atomic guys, where, remember, that's always sufficient because by the recursive structure of our SL sentences, if you give a truth value assignment to every atomic sentence, of which there are infinitely many, then that will recursively entail the truth values of every more complex SL sentence. So to define an interpretation, to define a truth value assignment, you just have to assign every atomic guy true or false, and we'll assign an atomic guy B true if and only if that atomic guy is in the club, if it's in gamma star. So any atomic guy that's not in the club gets assigned false. And then by recursive structure, the evaluation of Q, any sentence Q, is true if and only if Q is in gamma star. This is the key thing to show. So this is what to prove this part, we'll have this lemma, which will basically tell us constraints on what gets into the club and what does not get into the club. And then we'll do a little induction. So this is the basic idea is figure out how to preserve S&D consistency. The membership of the club is constrained, and then do an induction on an SL, because SL has this recursive structure. So, any questions about the proof idea? Who is running this club? I want to meet this man. All right, so this is our membership lemma. So this is book 6.411. I'm trying to make this more memorable by giving it a name. So that's what we do to make things memorable. So we'll call it the membership lemma. This is where you pay your club dues. So to deduct on SL, we show these constraints. So here's our metaphor, our magical metaphor on this otherwise very dreary Wednesday morning. Gamma Star is this club. There's a bouncer, you know. This is a bad dude, this bouncer. And he keeps it the case that Gamma Star is maximally consistent. Obviously, this is all very metaphorical. Gamma Star is a timeless, eternal mathematical entity. There's no notion of time anywhere here, or bouncers. Bouncers do not exist in Platonic space. But in our metaphor, they do. And our bouncer lets some sentence into the club if and only if he checks who else is in the club and certain conditions are met. So we'll call this membership lemma. So if you have P and Q in their sentences, then this was our thing about your nemesis, your enemy. So your enemy is in the club if and only if you're not in the club. So not P is in the club if and only if P is not in the club. So that's the first one. And the second one is for conjunction. So you can see we're going to have one for every connective. So P and Q are in the club if and only if P is in the club and Q is in the club. And you can start to see how this is mirroring the truth conditions. This is a syntactic constraint on membership, but it mirrors the truth conditions. What does it take for P and Q to be true? P has to be true, and Q has to be true. We, are going to construct this evaluation that satisfies everything in the club. So of course you could only satisfy P and Q if the things that satisfy P obtain and things that satisfy Q obtain. So for that you'd also have to have P in the club and Q in the club. So P or Q is in the club if and only if either P is in the club or Q is in the club. Again, this is just like our truth conditions. So at this point, you might wonder, what does it take for if P and Q to be in the club? So P and Q is a member of Gamma Star, if and only if. A brave soul from our illustrious Pentagon. On the next bullet point, what will bullet point D say? Is our question. Where again, our intuition here is we're recreating the truth conditions, but doing so syntactically. Yeah.
Not P is in Gamma Star, or Q is in Gamma Star?
Yeah, great. It's either not P is a member of Gamma Star, or Q is a member of Gamma Star. And remember, this Q is inclusive, so both of these things could be the case. And from our, nemesis clause A, not P is in the club. This is if and only if P is not in the club. So that would be an equivalent thing to say. Questions about this? So Owen is now a bouncer, honorary bouncer status. You did a shift, So this is our thing. So we can do the same thing for the last one, P if and only if Q. What will P if and only if Q require? Who else wants to be a bouncer? And of course, technically, we should have parentheses, outer parentheses around this stuff, but we're being chill. So P if and only if Q is in the club if and only if. This one's more complicated to state. Again, we're just mirroring the truth conditions of the biconditional. So we're like, what does it take for the biconditional to be true? We're going to call Gerardo. What's one condition for P if and only if Q to be true?
They were both false.
Yeah, they're both false. And so what would our syntactic analog of both of them being false be?
Not P in the club and not Q in the club.
Yeah, great. Yeah. So one of these will be this one, so if and only if both negations are in the club, and that's just to say that P is not in the club, is not in the club, and Q is not in the club. P is not club and Q is not in the club. So that'd be, equivalent to saying not P's in the club and not Q's in the club. We could also just say P's not in the club and Q's not in the club. Or, that's another thing, or they're both in the club. P's in the club and Q is in the club. Club should be Gamma star. Or positive star people. Reach for the stars, not drugs. That's what Gamma star says. So this is our second thing. So there's two possibilities here, and these aren't mutually exclusive, by the earlier thing, by part A. So either both the biconditional things are in the club, or neither of them is the club, and this would mean they're now C's, so both in the club, not P's and not Q's. Yeah, so we've gone through, we're mirroring truth conditions, and this is our moral. We all want to be in the club, but sometimes our enemies get in the way, and they prevent us. And when that happens, you have to be the better person, and by that I mean you have to kick your enemy. We don't do that. We practice nonviolence in Washington, right? All right. Any questions about this or why we're doing this? So you guys have to show this case C on problem 2, and that is the tedious involved thing to do. I could have been mean and also asked you to show case E, which sucks even more than case C because it's more complicated with these two conditions. So I don't, there might be an analog of this kind of thing on the final that would just be not one of these 5 sentences, but some other simple sentence like if not P then Q, and then you would again just rely on analog of the truth conditions and then show this thing. So based on how the problem set goes this week, we might end up spending some more time practicing proving these kinds of things, since there's a good chance the final will have an analog of one of these cases on it. So this is a thing to definitely practice and know how to prove. So we'll do at least one case. So to do these cases, so to prove the membership lemma, we rely on another lemma. And where we've been trying not to introduce more lemmas than necessary, but this would be more annoying than it's worth to prove in every case, as you go on the fly. So we're gonna make this one a privilege lemma. We're gonna call it the door. This is the door lemma. So again, we're just trying to have a memorable name here. The book calls it 6.4.9. Who the hell's gonna remember 6.4.9? So we're gonna call it the door. And we see, it's lemmas all the way down. It's where does it hit bottom? So it hits bottom when you hit bottom, right? And when you hit bottom, you need a lemma to get yourself back up again. So this is our door lemma. If gamma single turnstiles P, so if from the gamma guys you can derive P, and if gamma star is maximally S&D consistent superset of gamma, so basically gamma is contained within gamma star, then the sentence P that you could prove from the gamma guys is in gamma star. So we're basically saying with our door lemma, where did the chalk lemma go? Here it is. What chalk lemma? So this is our door. We'll write because we'll probably refer to. So we're saying if gamma single turnstiles some sentence P, so the plus sign, which is bad, not that positive today. So if gamma single turnstiles P and gamma is a subset of some gamma star that is maximally SND consistent, then we have P is a member of gamma star. So basically we're going from derivability to something being in the club. So it's all syntax. And the mnemonic here is something like when you have gamma single turnstile P and the gamma guy is a subset of your maximally consistent set, then this derivation pushes P through the door of the club, and P ends up being in the club. So this is like, the bouncer's giving you a hard time, and your buddy's just like, screw this, and they just, they get you in there, So gamma's like your buddy getting you into the club. Everybody wants a friend like that, right? Get you past the boundary. So, all right, so I would prove this. So yeah, we'll assume that gamma, proves P, and we'll use this later on. And then just assume for contradiction that P is not in the club. Then since gamma star is maximally S&D consistent by assumption, remember the second condition was anything that's not in gamma star, if you were to add it to gamma star, would make the resulting thing inconsistent. So if it's the case that P is not in gamma star, then gamma star union P would have to be inconsistent in S&D, and so we could derive some contradictory guys, R and not R, now assuming P. So we can now assume P for negation intro, get an R not R, and then we could introduce a negation. So by negation introduction, we could derive not P from gamma star. But now we're like, oh shit, this looks bad, because if you can get not P from gamma star, and gamma is a subset of gamma star, then you could get not P from gamma. But we assume that gamma star is maximally S&D consistent. We would have just shown that gamma is inconsistent, but gamma is a subset of gamma star. So we would have shown that gamma star is S&D inconsistent. Well, that's a contradiction. So by this assumption up here, gamma pushes P, proves P. So also gamma star proves P, since gamma is a subset of gamma star, and so gamma star would then derive both P and not P, and that's reductive because gamma star is maximally S&D consistent, so it has to at least be S&D consistent. So it just can't derive contradictory sentences. And so this means that P has to be in the club. So if gamma proves P, gamma derives P, and gamma is a subset of a maximally consistent set gamma star, then P has to be in gamma star. So very simple. Questions about the door? Hold the door. It's the right thing to do, right? Unless you're really in a rush, then it's morally okay. I was explaining the notion of the subrogatory to some computer scientists recently. The subrogatory is kind of the polar opposite of the supererogatory. Supererogatory is being a hero. It's kind of above and beyond. It's like, I'm not a firefighter, but if I save somebody from a burning building, it'd be like, this guy's a fucking hero, right? So subrogatory is doing something that's not good, but it's not wrong. And I think often when somebody doesn't hold the door open for you, it's not like they did something wrong. They didn't have to hold the door open for you, but it's not good what they did. So it's subrogatory. They were like, it's kind of like the opposite of, well, it's you might think the opposite of being a hero is like being a villain. This is like, you're not a villain, but you're not a hero either, and you're not like, okay, you're kind of like a bad guy, but not because you did anything morally wrong, it's just like, you dropped the ball. So it's kind of a cool, sub-erogation. Tell your friends, it's a cool idea, right? All right, so we're gonna prove one of these membership cases. We'll do case A, at least. And so case A is to show your enemy is in the club if and only if you're not in the club. That's case A. So the key thing here of these cases is they have two directions. So you have to prove two directions. On the problem set question 2, you have to prove the forwards and backwards direction. On the problem set question 3, you also have to prove the forwards and backwards direction. So just don't forget to prove both directions. So we'll first assume the forward direction will go from the antecedent to the consequent. We'll do this little forward arrow. So we'll assume that your enemy is in the club. Then if it were the case that P were in the club, then you could derive contradictory sentences. But gamma star is S&D consistent, so that's impossible, so we have to have P not in the club. So this direction, super chill. Cool. So now we do backwards direction, so now we assume the consequent, we're going to show the antecedent. So we'll assume that you're not in the club. Now if we added you to the club, then we would have an inconsistent set, and this is just, I guess, coming from the definition of the fact that gamma is maximally S&D consistent. So anything we add results in an inconsistent set. So that would mean there'd be some finite subset delta, such that delta union P is S&D inconsistent, derives from contradictory sentence pair, and then we can just do this negation intro thing that we just used, previously, where we have our delta guys. We would assume P for a negation intro, and then we pop out with not P. And so this is what would happen in the backwards direction. If P weren't already in the club and we added P, it would make it S&D inconsistent by the definition of gamma star being maximally S&D consistent, which we're assuming that it is. Then we could get not P, and then by the door. So this is where we use the door. So given that we've derived not P from a subset of, so here gamma derives P, and gamma is a subset of gamma star. Here what we've done using our door is we've had delta, this finite thing, single turnstiles P, and delta is a subset of gamma star, which is maximally consistent. So by door, we have P is a member of gamma star. So this is how in the homework question you'll prove this membership clause for the disjunction. You'll use the door at least twice. I think in both directions you use the door. And in one of the directions you have to do a somewhat non-trivial natural deduction where you'll have to actually write the natural deduction. It's like at least 11 lines, I think. Maybe there's a faster way to do it. You can do it in 11 lines. You could probably do it in longer lines, more lines too. But at least 11 is possible to do it in. So in this case, this is so simple. I mean, here technically, if this were a homework problem here where I say by negation introduction, the thing to do would be to write what I've written here, but for a negation intro. So that would be the thing to write. So in your book, in your homework question, you're gonna have to derive, I think, Q from Q or R. So starting from Q or R and some arbitrary assumptions gamma, you'll have to derive Q, one of the disjunction. And that is, a little non-trivial to show. It's like a reductive proof in your natural reduction system. Cool. So the book does cases P and Q, and if P then Q, you do P or Q on this problem. And then we skip this case E, the P if and only if Q, because YOLO, YOLO, so yeah, it did occur to me, right? This is something we don't talk about this enough, but every time an instructor asks you to do something on a problem set, they're taking away time from your finite life. That's time that you could have spent on something else. It really when you think about it that way, it really kind of hits you like, this is a big responsibility. Like if somebody assigns bullshit questions, they're literally wasting your life. You're not gonna get that time back, And that's, so it's kind of like, if you have somebody who just gives you questions that are totally awful, you could be like, why are they doing this to me? And so we could have you do this case and it could take you like 20 minutes, but it's like, is that really what life is all about? To show the P if and only if Q clause of the membership level? It's not but who knows, maybe it's good practice. If you really want to practice, you can try to do this one. If you can do this one, then definitely you could do whatever analog question would be on the final, I think, because I don't think I would ask you guys to do this case on the final. I think it'd be too mean. So, even though probably, because this is MIT, everything would be cool and it'd all go well, but like, I want to have a final exam that I can use in the future, and in the future, when I don't have people like you, it would not go well. So, it is true, to be fair, what we're doing this week is something that, with a typical logic audience, we would spend at least 2 weeks on. So we would have spent a week on soundness and a week on completeness, if not more. So we're just doing this, and you guys can handle this because you're like, yeah, math, you know. So cool. All right, so that was the first part of stage 3. We, did this membership lemma. Now we have the membership lemma. Now we actually want to do the actual induction. So we want to construct this truth value assignment. We want to show that when we define this truth value assignment such that an atomic sentence is true if and only if it's in the club, then it follows that any arbitrary sentence Q is true on the assignment if and only if it's in the club. And so we have an assignment that made true everything that's in the club. And so we would have shown that the club gamma star is satisfiable, which is what we want to show. Assuming that it's maximally consistent in S and D, we want to construct a truth value assignment that satisfies it. That's the whole game. So I'm going to get this guy, and it suffices to construct this thing I of Q, such that I of Q is true if only Q is in the club for everything SL. So we can do these bizarre properties, right? We're gonna call this clubbing. So this is we're gonna say a WFF is clubbing whenever it meets this property. So Q is clubbing because Q is true on I if and only if Q is in the club. Okay. So here we just define I. This I think is probably as interesting as you could make this proof, right? Can you imagine making this any more interesting than I can? So, but if you think of any ways, let me know, because we're trying to hold the eyeballs and keep the attention, and it's not easy on completeness day. So base case will be super chill. We just have to show that any atomic sentence is true on I if and only if it belongs to the club. And then we'll do strong induction. So we'll assume that every SL sentence that has anywhere from 1 to k connectives is clubbing. So the base case is 0 connectives. The atomics have 0 connectives, they're clubbing. And then we'll assume anything with 1 to k connectives is clubbing. And then we'll show that an arbitrary sentence that is k plus 1 connectives is clubbing. And then we'll have done our induction, we'll have shown everything in SL is clubbing. And that just means that this interpretation I, which we define here, does what we want it to do. It shows that our maximally consistent S and D set is satisfiable. Any questions about the structure of this proof? This is the proof idea schematically. Is it clear how once we've done this, we will have achieved our goal and all of our goals in life? Not most of our goals in life. Yeah, we're holding out hope for them. That's why there's more life. So base case, you got to show these 2 directions again, even though it's trivial. So we have this if and only if here. So don't forget that. So we're trying to show that each atomic sentence is true on I if and only if it belongs to gamma star. That's just what it means to be clubbing. We're trying to show each atomic is clubbing. So by definition, we constructed our interpretation I such that I if B is true if and only if an atomic I is in the club. So we met both directions by construction. We defined I this way. We basically defined I such that the atomics are clubbing. So of course the atomics are clubbing. The base case is totally straightforward. Any questions about it though? Cool. All right, so now we do our induction. So we're going to consider an arbitrary sentence P, that is k plus 1 many connectives, and because of the recursive structure of SL, then there's only 5 possible forms that the sentence P could have from our 5 connectives. We're just going to show in each one of those 5 cases that the resulting sentence P has this property of it's true on I if and only if it belongs to the club. So in case 1, P has the form not Q, where since Q has k connectives, which is within the scope of our induction hypothesis, the sentence Q is clubbing. And so call that just means I if Q is 1. So remember, if you don't want to write true, you could just write 1 for true, if and only if Q is in the club. So we got to show two directions. Forward direction is to show that if the interpretation I assigns true to P, then P's in the club, and the backwards direction is to show if P's in the club, then the interpretation assigns P true. Or again, in this case 1, the sentence P is not Q. So if you wanted to, you could just write not Q here and not Q there. You wouldn't have to write P. And maybe that would be more clear for you, and it might even be more clear for me as the grader. So I might regret the way that I constructed this slide as an analog, but we looked at that. So an alternative, which in some cases could be easier, I think often it probably won't make a difference, but sometimes, if you get stuck in the backwards direction, you might try the contrapositive. So the contrapositive of the backwards direction is negate this consequent, put that first, and negate the antecedent, put that second. So we'd be saying, if the interpretation assigns not Q false, namely 0, then not Q is not in the club. That would be the contrapositive. So, you just have to pick one way to show the backwards direction. Either way is fine, because they're logically equivalent. Cool. So we'll do the forward one. So assume that I assigns not Q 1, then I has to assign Q 0, just by the truth conditions for negation. So if it's the case that not Q is true on a truth value assignment, Q has to be false. And then since Q is in the club, since Q is assigned false, since Q is not in the club, since Q is clubbed, maybe this becomes a little confusing, hopefully not. Since Q is clubbed and it's got this property, since we see here that Q is assigned false, Q is not in gamma star. And then we appeal to our membership lemma. So this is when we do this induction, in every one of these 5 cases with our 5 connectives, we'll appeal to the corresponding case from the membership lemma at a point in the proof. So at this point, we've shown that Q is not in the club, and by the membership lemma, that means the enemy of Q is in the club, not Q is in the club. And in this case, P is not Q. And so by showing that not Q is in the club, we have shown that P is in the club. And that's what we wanted to show. So again, it's like we didn't have this lemma. At this point, we have to just argue straightforwardly from Q not being in gamma star, then that means if we added Q to gamma star, we'd have an S and D inconsistent set, and then we could derive R and not R, and so we could assume Q for negation intro, and then we could derive Q, and then we'd basically be reproving the door lemma. We would reprove the door, and then we'd say now Q is in gamma star. But essentially, we just bundle all that work into proving the door lemma, and then proving the membership lemma, so that when we get to this point, it's really easy. If we hadn't done those lemmas, then once we'd shown this easy thing, Q is not a gamma star, we would just have to run through the reasoning for each case, which you could do. And I don't know, maybe you might prefer to do that, but it would be, to do many of these problems would be more work to do that. So that's why we section off the little ones. In many ways, this kind of, the choice of when to make something a lemma is an aesthetic question in mathematics. People have different views about this and endorse different sets of norms on, when to, approach something as a lemma. Or even, what is the distinction between a lemma and a theorem? That's like a neat part of mathematical practice that people have very strong views on. Like, sometimes you can call something a theorem and a mathematician will be like, no, that's too trivial. You shouldn't call that a theorem. That is at most a lemma. You think like, what is the thought process behind that? Cool. All right. So back to direction. If P is in gamma star, then not Q is in gamma star, because P just again is not Q in this case. So by the membership lemma part A, we see that Q is not in the club, and we're trying to show that the interpretation I assigns not Q true. Now, if Q is not in the club, since Q is clubbing, that means the interpretation must assign Q false. And if the interpretation assigns Q false, it has to assign not Q true, which is what we want to show right there. So since Q is clubbing, we have the interpretation assigns false to Q, and then by the truth conditions for negation. the interpretation assigns not Q true. So in these kinds of proofs, you appeal to the truth conditions, at a certain point. So you appeal to membership lemma, typically in both directions, and also truth conditions. So any questions about this case one? Cool. All right. So what remains is to do the remaining cases. And again, this is what we're trying to show in every case. A sentence is clubbing, i.e. it's true on I if and only if the sentence belongs to gamma star. And our induction hypothesis, we've assumed that every sentence with one that k many connectors is clubbing. Case 2, P is a conjunction. In case 3, which is your promise set question, P has the form of a disjunction. In case 4, P is a conditional, and the book does this proof. So if you get stuck on case 3, I'd look, I guess, at this proof, which will probably be the most analogous to the case for keyword or. So if you understand this proof, you'll probably be in good shape to do this keyword or case. This problem, number 3, is way easier than problem number 2. Way more straightforward. You just apply the membership lemma, which you will have shown in problem 2, and then reason about truth conditions. So, and in final case 5, we have biconditional. So, which we'll probably not do. All right, so here, I reminded myself something. So here we are with 9 minutes left. So we can either give hints on this question with, I guess I'll have to see if I wrote it with RQ or Q or Q. Yeah, maybe I wrote it with RQ. Now, if you don't want these hints, then you must be already complete. So in the event you don't want the hints, then we will agree that the customer is always right, and our problem will be to schematize the sentence in quantifier logic. So who is in favor of hints on this completeness question? Raise your hand. I have at least one person. 2 people. Okay, who's in favor of schematizing the customer is always right? No. Oh, no. Both. All right. So everybody else is neutral. All right. Well, I guess I'll do. I might say, if the customer is neutral, I might say let's do the hints because I'm grading these bad boys. So if 5 of them go better than they otherwise might have, then that seems good, right? So let me flip to slow guy. Get the same notation. Oh, cool. So we want to show this thing. So we're trying to show this part. If gamma star is maximally consistent, we have this arbitrary P or Q, then P or Q is in the club if and only if either P is in the club or Q is in the club. So just do some schematic hints, which if you fill in the dots, then you should be good to go. So the first thing, remember, is there's 2 directions. So in the first direction, the forward direction, we are assuming that P or Q is a member of gamma star, and what we need to show is that I need to show that P is in gamma star or Q is in gamma star. So that's right. So the trick in the first direction is note, so note that either P is in gamma star or P is not in gamma star because gamma star is maximally, really considered because gamma star is S and D consistent. It's also maximally S and D consistent, but the S and D consistency is what rules out having both P, this is just a logical fact, right? You're either in the club or you're not in the club. You don't even need it yet. This is, this is like P or not P. So, don't even have to appeal to something. If we were gonna say either P is in the club or not P is in the club, then we would be appealing to. So this is really just at this point to say we're doing a proof by cases. So case 1, P is in the club. Case 2, P is not in the club. Now, if P is in the club, then we're good. Because that's what we want to show. We're going to show that P is in the club or Q is in the club. So the hard part, at least harder part, is case 2. Okay, assume that P is not in gamma star. Now what you need to show from this is that Q is in gamma star. And so this is where you're going to have to construct this derivation, use the Dor lemma. So the key thing to note is if P is not in gamma star, then since gamma star is maximally SMD consistent, if you were to add anything to gamma star that's not in it, you would have an inconsistent set. You'd have an SMD inconsistent set. So the union of P with gamma star is SMD inconsistent. So basically, what's going to happen is you're going to have to, because the one thing we've assumed is that P or Q is in the club, so we know that there's, some random things, we could call them, delta 1 through delta n, and we have if P or Q. We basically know from the fact that P union gamma star is SMD inconsistent, that if somewhere in a proof, if you assume, so basically, let's see, okay. This will be mega hint for this, because this is the annoying thing to write down is just, we're gonna have to derive Q. We're gonna have to show that there's some, I see, I'm writing gamma to avoid notation class, there's some gamma, a subset of gamma star, such that gamma derives Q, then by the Dor, we would have Q is in gamma star, because gamma is a subset of the maximally consistent set gamma star, gamma proves Q, so by the Dor, Q is in gamma star. So we want to have some derivation that gets us Q. We have P or Q is in gamma star. This is our key thing, occurring on line M. So we know that P or Q is in gamma star by assumption. So whenever you have a disjunction, you think, do a proof by elimination, do disjunction elimination. One part's easy, right? Assume Q, and then you can reiterate Q. This is assume or elimination. This is reiteration on the previous line. Now you have your little breaks. Now the harder part, right, is you assume P, and you have to get Q. But we know that P union gamma star is SMD inconsistent. So at this point we have P, these are guys from gamma star, choose the deltas such that the delta guys with P or Q and P is SMD inconsistent, then you could write an R not R in here. And so basically within this little key part, you want to assume not Q for negation. So inside here, so another subproof, assume not Q for negation elimination. And then you can justify your R and your not R. You can pop out of this negation elimination with Q. And then in both cases, from Q you got Q, from P you got Q. So you could pop out the whole thing in rank Q by order elimination. So, and that's the harder direction. The second direction should be chill. You just figure out basically how to derive P or Q from P, which is orange direction. Similarly, you can derive P or Q from Q, which is orange direction. So that's the second direction, should be easier. So that's our mega hint on the first direction. Just make sure to take a picture of the baddies. Alright, cool. So yeah, thanks for coming to class today, guys. We'll do it all over again next week with quantifier logic. So something to look forward to. And I have office hours today, right after class, and on Friday from 1:30 to 2:30.
The slides like posted or something?
I will post them probably during office hours. Yeah.
So they're like in the files of campus or something?
Yeah, I always put the slides in the files and also in the module. So it'll be probably at the top of module 12. You should see a link to the file. We had tried as long as we could this semester to avoid satisfaction semantics. And we came to the point where we can't avoid satisfaction semantics any longer. And so it hurts my brain. It might not hurt your brain, in which case, God bless you. But basically, the long story short is the following, which is, there's a sense in which what we're doing today is super simple, mind-blowingly obvious. So we have these derivation schemas for proving the soundness of Q and D. And these are the only new 4 rules that we've added to our system. And so basically, all of the previous rules that we showed, were sound in for S and D. Those proofs basically go through. You just change the truth functional notions to quantificational notions. Truth functional entailment becomes entailment for quantifier logic. Now we have these 4 new cases to add to our induction. The 2 elimination rules and the 2 intro rules for the quantifiers. And all we're doing in each of these 4 cases is the same thing. We're showing that the k+1 line is righteous. We're showing that the k+1 line is semantically entailed by the set of open parentheses on that line. So we're just showing organic k+1 is the set of open parentheses or assumptions on line k+1. We're just showing that this semantically entails the k+1 sentence. And so basically it just amounts to looking at these rules and saying, oh, okay, if I have the earlier sentence semantically entails the later sentence. So really all we're showing today is that if everything's a Q, then C is a Q. That's universal elimination. And we're showing if there's something that's a Q, concrete thing's Q, then yeah, it is true that there's at least one thing that is a Q. So we're just showing stuff like that. So it's really obvious what we're doing. But to do it formally, we need to use something like satisfaction semantics. There's other ways you could do it, but they all suck in equally sucky ways. And so it's just, if there's one moral from the day, we're really by the end we'll be searching for something, grasp on some kind of moral for why are we doing this. It might be that sometimes in life, or at least in mathematics and logic, things can be blitzingly obvious, but very tedious to show rigorously. Maybe there's something surprising about this. I don't know. It just, so that's where we're at. So we're gonna do some satisfaction semantics so that we can do these proofs. And this is stuff that we pretty much glazed over in chapter 9 with formal semantics for QL because it's like really obvious, what the truth conditions are for these models. So when we did our model stuff in problem set 9, we didn't really need to explicitly think in terms of satisfaction semantics. We just thought in terms of what does it take to satisfy a set of sentences? What do we have to add into the extensions of the predicates? What do we need the constants to refer to make these sentences true? And it was clear incarnate how to do that. But we're, now we have to be precise, and so we'll do this beast. Something like it. We're still going to try to be as intuitive as possible, but as you'll see, that might not be that intuitive. So bear with me. I'm very happy to have an audience, but another part of me is like, oh man, maybe this class, unlike previous classes, is actually like, disk utility. Like, all right, so, this is really high level. So we're doing soundness and completeness. Remember when we're doing the soundness proof, we're just showing that we have truth preservation. So we're converting a single turnstile now in Q and D into a double turnstile. And when we're doing completeness, which we'll do on Wednesday, hopefully we'll finish this today, or something, close to finish it. When we do completeness, we'll be converting a double turnstile semantic entailment into the single turnstile Q and D. Okay. So just to give some recap, so this is the top of the satisfaction semantics things. Oh yeah, I guess Henry, Manny, Daniel, did you guys get a handout or no? I feel like there's too much to hold in the brain today, so yeah. So yeah, the top of the satisfaction semantics thing, we have this definition of a model. We're just going to be a little bit more fine-grained than the book today because it's convenient. So consider any first-order language, specifically we're considering QL. Then we have the atomic sentences or zero-place predicates. So they're bundled into k-place predicates, as a kind of degenerate case. So a model for this language is just a domain and an interpretation function. So the domain is not empty, it has some objects. The objects are like things. So we're being little Platonists, and so we're thinking if our domain is the natural numbers, the objects are these numbers, and we think we could reach out and touch them. And the map, I, is the interpretation. It takes the vocabulary of our language, so the symbols in our language, the symbols are constants and predicates, and it maps the constants to objects or to ordered pairs from the domain in the following way. So given a constant, I of C, the interpretation function applied to that constant, is just an object. It's something in the domain, it's the referent of that thing. So for instance, if I had the name, so if I had a constant A, then I of A might be something like a number 5, which is in the domain if my domain is the natural numbers. So A is the constant, it's a name, it's a symbol. 5 is like a thing, an object. 5 is what the constant A refers to. And for the predicates, we're just mapping a predicate symbol to a set of ordered pairs. So if you had something like the relation of being taller than, you're just mapping, people in this room, for instance, to the ordered pairs of the first thing in the ordered pair is taller than the other thing, And that's what the extension of the predicate would be. So our book uses models interpretations, to be synonymous. So does the logic book. But, this is convenient to think about the model as being a thing that has a domain and an interpretation. Any questions about this? Yeah.
What does first order language mean? Because
yeah, it's just like a generalization of QL. So you can think about QL as being an instance of a first order language where, in general, any first order language has predicates that are properties of things but not properties of properties. So a second order language you'd be able to quantify over predicates. Now we often, in natural language, will quantify over predicates, but in a first order language you're not allowed to do that. And we're not doing second order logic because a lot of the nice properties of first order logic fail. So second order logic is not as well behaved as first order logic. So it's controversial in philosophy whether you need anything beyond first order logic. So Quine, for instance, in the 60s, 70s, he was arguing that really all you needed was first order logic, you didn't need this other stuff. But it's like, people, the more like real logic people, they love, second order logic. And so, yeah. Cool. Any other questions? All right, we go into the beast. So, just to, as a warm-up, we have some simple examples of what it means to be true. So here's a simple language that just has one, a single one-place predicate P, a single two-place predicate R, these constants A and B. So when we fix the model, we pick some domain, could be the natural numbers. I, this interpretation function, is just what we would punch in the Carnap. It's what we would assign to the constants A and B, and it's what we would assign to the predicates P as the extension, and so for R, we'd be assigning pairs of things to be in the extension of R. So that's what we were doing on problem set 9. So PA, the sentence PA is true in our model, provided that the object that I maps A to has the property I of P, namely lies in the extension of P. So, and then if that's true, then you can write the model double turnstile PA. So this is just notational convenience to say PA is true in this model now. M, has specific domain and interpretation function, and provided there is something in the model that is a P, and namely that something is what A refers to, then PA is true. So very intuitive. And RAB is true in the model provided that whatever A gets mapped to and whatever the constant B gets mapped to, they stand in relation R, so that their ordered pair thing lies in the extension of the relation R, and then in this case we would again write RAB is true in M. Obstructing anybody's view of our, I don't know what's going on this day. Oh, I see. Someone really wants this thing to stay over there, and they're upset with me if I keep doing it. They can eat shit. So. The other person who's doing this, they're responsible, I think, for opening up this hole in the ground, and the guy after me is very upset that this hole is open most of the time, and then he blames me, and I'm like, yo, bro, I didn't open the hole in the ground, okay? I'm with you. I don't want the hole in the ground to be open. It's scary. All right. So the whole reason we're doing satisfaction semantics is we have to talk about free sentences. We have to talk about things that have free variables. Well, I guess they're really called open sentences. Open sentences have free variables, and I really shouldn't even call them a sentence because they're not a sentence. We're trying to remember sentences are things that are true or false. Something like this that has a free variable, it's not true or false because X is a variable, X isn't naming any particular thing. X has the ability to stand in for a variety of things. And so this is a well-formed formula of QL, but it's not a sentence. So we need some way of talking about these objects because they feature recursively in things that are sentences. So, for instance, if we have the expression for all x px, this is a sentence because there aren't any free variables, everything's bound. And this thing recursively comes from a px. So if we want something like recursive truth conditions, we need a recursive structure that will apply to these things as well, and that's what satisfaction semantics does. It gives you recursive structure that's more general than truth. But that ultimately is functioning to give us truth conditions for sentences, which is what we're after. It's what we all want out of life. Cool. So very simple idea is for a given object R in the domain, so I'm typically going to use R to refer to objects. And you think R is like a referent. So the R's are not constants typically in these slides. The R's are like real things in the domain. So for any object R, we would know whether Px is true. We would just have to replace R for X, namely if X stood for R. If X was a name of the object R, and if R were a P, then Px would be true for that thing. And we know the extension of P whenever we have a model because the model gives you the extension of P. That's what the interpretation function does. So very simple shorthand, if PC is true in the model, then whatever the name C refers to satisfies Px and M. So the shorthand is something like the objects satisfy open formula. The longhand is we have these variable assignments. So this is where we go down notational disaster. Yeah, what's up, Tim? Tim, there's a handout today to help our brains follow along. So yeah, so the longhand is we're going to have these variable assignments D sub I. They map variables to objects. And so really a variable assignment is just a choice of, you have all these variables running around, that you could refer to. You've got X, Y, and Z, you got subscripts of these things, and a variable assignment just takes these variables and it maps them to objects. So, and it's where it maps them to objects, not to constants, but it maps them to things in the domain. And so for any given variable assignment, we'll say it satisfies an open formula thing with free variables, provided that what di of x, so the thing that x is being mapped to, has the property I of p. So if we were mapping x to 5, and if the property p was interpreted as prime, so if we had this predicate p, we interpreted p as prime number, a prime thing, then this variable assignment would satisfy px, because x is mapped to 5, 5 is prime, and so this thing will lie the extension of the thing. You have a handout. Any questions about this variable assignment stuff? So this is our formal technique that we'll be using to prove sounds. We'll be talking about these things. Again, so you guys missed the preamble, but basically the short answer is today sucks. This is really a disaster day, but we're doing it because we have to eat our vegetables, and we're in favor of vegetables. Cool. So try to, it might help. Try to hold in mind the shorthand, which is objects are satisfying these open things, and whenever an object satisfies something, that means there's some variable assignment in the background. The variable assignment is just taking that variable to an object, such that when you plug in that object, the resulting sentence is true. Cool. So to illustrate this, because maybe it helps to see some examples. If you had an atomic, well-formed formula, then for predicate logic, these are the regular atomic sentences from sentential logic. Those are zero-place predicates. We also have the one-place predicates with any kind of term after it, that, a constant or a name. So we have things like, px, pa. We also have things like rab, things like rxa. So these are all atomic formulas. We have a three-place thing t. Those would be like txyz. So if we're asking, what does it take to satisfy one of these things, we're really just asking, is there some variable assignment that maps the variables in here to objects such that those objects stand in the given relation, like stand in the relation t, for instance. So we have constants and variables, and our interpretation function I, this thing on its own, it already takes care of all the constants. I is defined as something that assigns constants to objects. So the constants here, like the A and the A and the B, these are taken care of by I. In order to handle the variables, we have these variable assignments. So the DI is mapping these variables to objects. And here we just have some general notation, let the object of things map to be denoted T sub I, capital D. So capital D up there is telling you, I'm in the domain, I'm a thing, a real thing, like numbers. And so the book uses this more involved notation, the denotation of under I or DI of the constant or the variable, the term. So denotation, again, is just referent, just a synonym for referent, what a thing denotes. So we'll say that a variable assignment D sub I satisfies this kind of atomic sentence Q, provided that the resulting K-tuple of the objects, the things in the domain, so just all the things that these terms, the constants or variables, get mapped to, provided that they stand in the extension of Q. So provided this ordered thing is a Q. So the idea here is just, what would it mean to satisfy TXYZ? It would mean I had some variable assignment that mapped these three variables to things, maybe ABC, such that TABC is true. And what does it mean for TABC to be true? It just means that the ordered triple ABC is a member of the extension of of t. So t could be something like a relation of betweenness, and this would be saying something like the Stata Center is between the Lord Hobo and the Charles River. And so, D would be the Stata Center, and our variable assignment would be mapping variable y to the Stata Center. Oh wait, I just made a boo-boo. I did the bad thing. A, B, C are constants. These are supposed to be the things ultimately that stand in the extension are things in the domain. So I shouldn't write A, B, C. I should write the things in the extension. So if these were numbers, I'd have to write numbers, so it might be numbers like 1, 2, 3. If they were buildings, I'd have to write things like the Lord Hobo, the Stata Center, and the Charles River. Where, this is bad notation, but these are just illustrative examples. Any questions about this example, or this example of an example? Cool. You guys are witnessing an example right now of a disaster. It's going to get worse. All right, so for any given object R in our domain, we can now write a different kind of variable assignment, which is a variation on the variable assignment di. So di is a variable assignment. We have this notation di of R for x, which basically means we're taking the variable assignment di, we're keeping everything exactly the same, except we are enforcing that we're going to send the variable x to the object R. So this variable assignment di of R for x, it does exactly what di does, except it necessarily sends x to R. So maybe di sent x to some other object. That's cool. When we write this thing, we do everything di did, but we take x and we definitely send it to R. So it's just a way of enforcing that. And we'll sometimes call these kinds of things invariants. So that's how they're defined on this sheet. A variant of a variable assignment is itself a variable assignment. So, cool. So now we have, the whole reason we're doing this really is to get a grip on what does it mean to make an existential or a universal statement true, because these are the things we need to reason about to prove the soundness of our system. We have to show that going from a certain universal statement, we get instances. Going from instances, we get existentials, etc. So these are our satisfaction conditions for existentially quantified statements, and from satisfaction conditions, we'll get truth conditions. And truth conditions is what ultimately we need, to do the soundness proof. So if we have a formula of the form, there's an x such that q, where, if this is a sentence, then there's going to be some x's in the q thing. Then some variable assignment d sub I satisfies there is an x such that q, provided that there's some object r such that the variable assignment of sending x to r satisfies q. So the intuition here is just, provided there's something that's a q. That's the intuition. We have this convoluted way of writing that intuition, saying, provided there's some object such that this variable assignment, the variant of this variable assignment, satisfies q. So, again, try to hold on to the intuition, provided there's at least one thing we can plug in for x such that q comes out true. If that's the case, then this variable assignment d sub I satisfies the existential. Cool. And then universally quantified, if we have a well-formed formula of the form for all x q, then a variable assignment d sub I satisfies for all x q, provided the variant di of R for x satisfies q for each object R and D. So this is saying no matter which R we choose, if we send x to that R for each R, then this variable assignment, the variant, satisfies q, satisfies the thing that doesn't have the universal in it. So the intuition here is just, no matter what you plug in for x, q comes out true. That's what it means for a variable assignment to satisfy the universal. It means no matter how I, decide to send the variable x to an object R, then the q thing's true. And if the q thing if we're satisfied. If the Q thing is satisfied no matter what I send X to, then this, original variable assignment satisfies the universal, satisfies everything as a Q. Any questions about this? In case you forget what I just said, it's written on the sheet so you can refer back to it, because otherwise you probably would forget. I kept forgetting while I was writing these slides, so I was like, shit, we're gonna need a sheet for this. So now we go from satisfaction to truth conditions, which is our ultimate goal in doing all this. So yeah, all right. So we have this lemma, which we're not going to prove. It's an inductive proof. It's in chapter 11 of the logic book. It's chill, but we're probably honestly going to run out of time as it stands. So we have to pick our battles here. So what the lemma says is, if you have some model, domain, and an interpretation function, and a sentence of P, so a sentence, no free variables. Sentence, any variables bound. So a sentence can be true or false. Then the lemma says either all of the variable assignments di satisfy this sentence, or none of them do. And so I've called this the all or nothing lemma on the sheet. And what the all or nothing lemma lets you do is define truth conditions for sentences. Because there's a couple ways to do this. The way the logic book does it is they say, okay, well, a sentence P is true then, provided all the variable assignments di satisfy it, and it's false if none of the variable assignments satisfy it. The way our for all x book defines truth is the sentence is true provided there's at least one variable assignment that satisfies it. And you can do that because of this lemma, because this lemma is telling me, oh, well, if there's at least one variable assignment that satisfies the sentence, then all of them do. And so you would never have an instance where you had a sentence that was satisfied by some variable assignments, but was not satisfied by some variable assignments as well. That would mess you up in defining truth or falsity, because you need these to be incompatible things. They have to be completely, excluded. Being true has to exclude being false. And so you need a condition such that when that condition obtains, the condition for being false, whatever it is, can't obtain it. It's logically excluded. So in virtue of this lemma, we can define a sentence P of QL is true on some model. So remember, truth is always relative to a model. Truth, just like in sentential logic, truth is relative to a truth value assignment. Here, truth is relative to a model and interpretation. So sentence P is true on some model M, if and only if there's at least one variable assignment that satisfies P. By this lemma, that would mean all the variable assignments satisfy P. It's false, sentence is false on a model otherwise. So i.e. if there's no variable assignment that satisfies P. So basically when we're reasoning about these sentences and the soundness proof, and we get to assume that some earlier sentence is true in the model, we basically get to assume there's at least one variable assignment that satisfies that sentence. The variable assignments in satisfaction, they have a recursive structure that applies even to the open formula, and then we can use that recursive structure to basically construct variable assignments that will satisfy the stuff lower down in the proof. And then since we'll have shown, oh, there's at least one variable assignment that satisfies the stuff lower down, that will tell us from this truth condition, oh, well, if there's at least one variable assignment that satisfies the lower sentence, then that lower sentence is true. And all we did in proving that was to assume that an earlier sentence was true, and so we will have shown that our new rules are truth preserving. So again, the idea is really simple. It's just, it's kind of a bummer maybe that it's so syntactically complicated to set this up. But the idea is hopefully simple. We have to go beyond truth because we need a recursive structure. We need that recursive structure to apply to formula that are not true or false, that are open things that have unbound variables. And so it seems circuitous, but this is where we're at. There are little tricks we could have done to make this a little bit better, but they would have involved even more notation. And so there's like a trade-off of like, if you want to do the trick and have more notation. So yeah. All right. I hope you're satisfied. I'm not satisfied. But all right. So some examples of this. If you have something like there's at least an x such that ax, this is true if and only if ax is satisfied by at least one object in D. So this is the intuitive thing we were thinking about for chapter 9. This is like how we thought about it for problem set 9, which is this notion. And so some object R, which is whatever constant C is referring to in this interpretation, satisfies AX in the model if and only if AC is true enough. So the object R satisfies this open formula if the thing that R is named by C, is true in the model. So if there's at least one object in the domain that is an A, referring to. So formally, that's what we're saying now, our fancy pants variable assignment stuff, provided there is a variable assignment d sub I with at least one variant, di of R for x, such that di of R for x satisfies AX. So this bullet point is a convoluted way of saying this very simple idea, provided there's at least one object in the domain that is an A. That means there's some variable assignment di that's satisfying this thing. What does it mean to satisfy this existential? It means there's a variant that satisfies the smaller piece, satisfies the earlier structure. That's what our satisfaction condition for existential quantified stuff says on the sheet. Are there questions about this? Cool. So similarly, for all x, AX is true if and only if AX is satisfied by every object in the domain, very intuitive, i.e. everything in the domain's an A. So this is the level we operated at for problem set 9. Today, the level we operated at is provided there's a variable assigned di that satisfies this universal. That happens if and only if, for each object in the domain, the variant di of R for x. So when we keep di the same, but we necessarily set x to R, if each one of these variants, no matter what we have for R, the object, satisfies the smaller piece AX. And again, that's just our condition for satisfying the universally quantified thing. Cool. So, yeah, maybe I'll do one of these examples. So if you had something like there's an AX and BX, this is true if and only if some object satisfies AX and BX. Cool. All right. So we just did the satisfaction stuff. Now we can more precisely say what are the relevant semantic notions in QL. Basically, what's our double turnstile in QL? And we need to understand our double turnstile because we need to understand what does it take to show that some set of QL sentences semantically entails a given QL sentence. You know, this is where this is our consequent, basically, in the soundness proof. So we need to know what the symbol means. So here's our notion of entailment. So some premise set where the premises now are sentences, because premises in argument, they have to be true or false. And so you're only interested in gammas that have sentences. So you'll never have a gamma that has something like px. Px is not a sentence, and so you'll never have an argument that just says px, because px is not true or false in a model. So the gamma guys are sentences, and they entail in QL some other sentence Q, provided there is no QL model M where all of the gammas are true, but the sentence Q is false. And whenever this happens, we write gamma semantically entails Q. So notice the structural similarity of truth value assignments. Truth value assignments, the claim was you have semantic entailment provided there's no truth value assignment. That makes all the gamma guys true and the Q, the conclusion, false. Here, rather than say truth value assignments, we're saying models. So models now is our generalization of truth value assignments. Because the interpretation function, it contains within it a truth value assignment. The zero place predicates are sentences. And the interpretation function assigns the zero place predicates, the SL sentences, to true or false. So model, the QL model really is just a generalization of a truth value assignment. Cool. So similarly, we'll have a semantic notion of satisfiability, and we'll say some set of sentences gamma are jointly satisfiable, and we'll often just say satisfiable, provided there is at least one model M on which each of them is true. Or again, really similar truth value assignments, set of sentences was satisfiable, provided there was at least one truth value assignment that made all the sentences true. Now, a thing that could get a little confusing is this notion of satisfiable has nothing intrinsically to do with satisfaction semantics. So just watch out for that. We're using things that sound like satisfied in two different senses. But so this semantic satisfiability it's what we would call QL consistent, but then, when we go to do the completeness proof, hopefully on Wednesday, we'll have a syntactic notion of consistency. We'll have consistent in QND, consistent in our derivation system. And so to try to avoid that ambiguity, I'll use satisfiable for the semantic notion. So basically we're running out of words, as happens in life. There's just not enough good words to go around. Questions about the semantic notion? All right, I will take that to QL and tail that we can proceed. Ho, ho, ho. All right, so now we have some more notational disaster, substitution instances, which we talked about, I think, one time in week 10, and the question was, is this really worth it to do this? And it is worth it to prove soundness. So it's to have this notation around is worth it to write these little schemas. So you'll notice these little schemas have this bracket stuff, like Q bracket C for X, or C for chi, that's different than the way they were written on your other rule sheet, where I wrote everything out very explicitly, where you just had C, like C's, dot, 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 C's, and like X's, dot, dot, dots. Here we have this more condensed notation of substitution instances, which, we'll see. It has some advantages. It's definitely, more streamlined to write. So when you see a symbol like this, Q bracket script C for chi, this is the sentence that you get from some quantified thing by, you drop the quantifier, so you eliminate the for all, you eliminate the existential, and you just place a C everywhere you see a chi. So we read this as C for chi. So we're like, C for, here's like bracket C for X. This means substitute a C for every X. That's what this notation means. So the little slash is like a for, C for X. And the key thing is for every. So every place in Q where there is a chi, in the substitution instance, you've replaced all those chi's with C's and you've dropped the quantifier. So it's like, substitution instance of for all x px would just be PC, where you drop this and you put a C for the x, and then you get PC. That would be a substitution instance. And you don't touch any of the other variables. So in that sense, it's kind of similar to the bracket for the variance of the variable assignments, where you don't touch anything else, you just do what the bracket tells you to do. Key difference, which can be a little confusing because we'll have both these brackets running around, variable assignments and these substitution instances. Here, this C is always a constant, it's a name. So we're substituting a name for a variable, whereas with the variable assignments, the thing that we're substituting, the R, is an object. So different categories of things. So in a sense, we should have a different notation for that, but that would be, annoying. So you just have the brackets for the sentences, for the substitution instances, are technically a different kind of thing than the brackets for the variable assignments. So here's some examples of instances that we talked about in the previous week. So there's a Z such a HAZ. You could replace, the Z with something, and then you get instances of them. And yeah, here, so remember you have to replace every occurrence of Z with the same constant. So these are instances HC and FCC, but these are not. If you only replace some of the Z's, then these would not be substitution instances. Cool. So then we have a notion of partial substitution instances, which is really relevant for just one rule. It's relevant for existential introduction. So this is an innovation the logic book doesn't have. They don't use partial substitution instances, but we do because we're cool on them. So this thing, if you don't close the bracket at the bottom, then this means you're replacing some of the C's with chi's, but not necessarily all of the C's. So you get to pick and choose which C's you want to replace. So some examples of this, using existential introduction, which is the rule where this really matters. Here's our instance, RDD, and RDD is it's a substitution instances of all these things. So basically, here we're looking at substitution instances of Q. That's what this thing is. Q of partial bracket chi for C is is a partial substitution instance of Q. Forget about the existential thing. So what this is saying is you could replace all the D's with the same variable, or you could pick or choose. You could replace, the first D with an X, but leave the second one okay. You could replace the second D with a Z, and leave the first D unchanged. So RDZ, forget about the existential part, RDZ is a partial substitution instance of RDD. Questions about this? Cool. All right, so we have a lemma, the substitution lemma, and we use this in a bunch of the proofs, and it's also, the meaning of it is very intuitive. The notation, again, is a disaster. And so it's written on our sheet so that we can refer back to it and verify that we're actually following it. So again, this is like some inductive proof. You could prove this. It's, we've limited time in this class. We want to get the bigger and better things, like in life. So we'll take this for granted. So first to give, I have a running illustration, because otherwise it might just seem too abstract. So if we have some sentence Q, which let's let be fxx, then here's a full substitution instance of Q. We've replaced the x's with c's, we get FCC. So when we say something like a variant di of I of c for x, so I of c is whatever the interpretation I maps the name c to. So I of c is some object in our domain. It could be something like the number 5. So I of c is like the number 5. So here R is whatever C gets mapped to, and R is an object. So di of R for x satisfies fxx. This means that when we assign x to the object R, FCC is true, i.e. FCC is in the extension of f. And see, I made a boo-boo again. This should be, I really should, rather than write FCC is in the extension of f, I should write something like R comma R. R comma R is an extension. So I'll try to remember to fix that. It's on 13B5, our beautiful naming convention. All right. So similarly, if we have something like this variable assignment di satisfies the substitution instance Q of C for x, this means whatever objects di assigns to the variables, the result is going to lie in the extension of Q. There's not really a clean way to write this because ultimately it's some kind of like recursive structure. It just depends on, what kind of sentence Q is. So when you're looking at FCC, you see, okay, well there aren't any x's in FCC, so the variable assignment di, it's going to treat FCC just like the variant di of I of c for x treats fxx. This is like the guiding thought here. And so once you notice this, you notice, oh, okay, well FCC doesn't have any x's, and so the variable assignment di, it's going to handle FCC just like the variant would treat fxx. Then you notice, this is the kind of like intuition. The variable assignment is treating the substitution instance exactly like the variant is treating the original sentence. So one way to remember this relation is on both sides you have one of these bracket things. Now remember, the brackets technically are different brackets, but they structurally look similar. So when you have a variable assignment with no brackets, it handles the substitution instance. When you have a variant which has the brackets, it handles the thing that doesn't have the brackets, namely the thing that's not the substitution instance. And so if you believe this, and you can prove it with induction, then you get substitution lemma. Consider any well-formed formula of QL. So Q doesn't have to be a sentence. The whole reason we're doing this is we need to be able to recursively handle things that might not be sentences. So Q be any well-formed formula, then the variable assignment di satisfies a substitution instance of Q if and only if the related variant, where we're focused on whatever C is the name of, satisfies the original sentence, or not the original well-formed formula. Q. So basically, this is just a way of moving back and forth between variable assignments and variants, and if you have satisfied some substitution instance, you know, okay, there's some variant that satisfies the original sentence and vice versa. If there's some variant that satisfies this non-substitution thing, then you know the variable assignment satisfies the substitution instance. And this will be useful for us because, again, in our soundness proof, you notice that basically in every one of these rules, there is an earlier thing that is related to a later thing that's a substitution instance. And when we assume the earlier thing is true, we're assuming there's some variable assignment that satisfies it. We then have to construct a variable assignment that satisfies the lower thing. And this lemma is, in many cases, our bridge that lets us go from the thing that's not a substitution instance to there being some variable assignment that satisfies the substitution instance. So that's the reason we're going to rely on this. This really does suck, right? All right. So now I think, yeah, we're approaching actually doing the proof. So yeah, hopefully we get through one case of sounds today. You know, we'll probably just start on completeness anyway on Wednesday, no matter what happens to get us out of this disaster. But yeah, all right. So we have a recap of our rules, which I won't belabor because they're on the sheet. And our goal is just to show each one of these rules is sound. And really to go back to morals, one moral today, which maybe has something of philosophical interest, is you might have wondered, if you're a curious creature, why did we have these provided that clauses in some of the rules? Why did we have these stipulations, which are sometimes hard to remember, about the conditions that have to be met in order to apply these rules? And we have these conditions precisely to ensure soundness, precisely to ensure truth preservation. Without these conditions, for universal introduction, for instance, if it were the case that the instantiating constant C appeared earlier in some undischarged assumption, then C wouldn't be like a dummy variable, and you wouldn't be able to infer everything as a Q from this instance of Q. And so you wouldn't have truth preservation. So you can only prove that this is a sound rule, that the schema is sound, if this condition is met, and this condition plays a really important semantic function in the proof. Similarly, for existential elimination, we have these three conditions, which are on your sheet. So C can't occur in any other undischarged assumption. So here you have a free C. We take an existential, and we sub in a C for the chi, and we drop the existential, so this becomes a full substitution instance. This C, it can occur in any assumption up here that's undischarged. The C can occur in psi, and it can't occur there. And if you did have some C that you'd already appealed to, then you just wouldn't have truth preservation. So again, these conditions, we'll use them in our proof. And some of the, this condition, provided that chi does not occur already in Q, some of these conditions we wrote, they're actually trivially satisfied by the way we define well-formed formulas and the nature of sentences. And so that's kind of like a cool aspect of our rules. So for instance, this one, for universal introduction, chi does not occur already in Q. We wrote this, just like, so you don't forget, but technically so Q is a sentence, and so Q can't have any free variables. So if there's a chi in Q, that chi has to be bound. Now, from our recursive definition, we set things up so that you could never use the same variable, you could never bind the same variable twice. So if you already had a for all chi quantifier in Q, you couldn't then tack on another for all chi quantifier. We'll never have a sentence that has two for all chi's. That's how we define well-formed formula. So this second condition too is technically always satisfied. So we wrote it kind of just like a, hey, don't screw up. But if you knew what you were doing in our system, this would always be satisfied. So that's some advantage of this way of setting it up, which is a little different from the logic book. So maybe we like this better. We'll see. All right. So we're going to motivate these restrictions on the rules. And for Q and D to be sound, we got to show from single turn style to double turn style. That's what we're trying to prove. And so we're going to prove this by showing the set of open assumptions gamma k on some line k semantically entail the sentence pk on that line for all the lines. So we're going to show every line is righteous. Every line has its property. That will show every derivation is righteous, and that will show that whenever we have a single turnstile, we have a double turnstile. Cool. All right, so we're into the proof. Woo! Yeah. All right. We got like close to 30 minutes. So we'll do some damage in this. We only have 4 cases, right? But the thing you're going to see is each case again, it's going to be very obvious what has to be done, and then there'll be a lemma for each case. And the lemma will be arguing about these variable assignments. And some of the lemmas are okay, and some of the lemmas really suck. And so that's really where the battle's won or lost. It is funny because like a part of me was like, oh yeah, soundness, we'll wipe that out really fast. It's just 4 new cases. Well, it's like, wow, man, you're really down a rabbit hole to handle these new 4 cases. So just to recap on entailment. Gamma is now infinite set of sentences. So we're focused on sentences, no free variables. And an argument is semantically invalid if there's some model M that makes true each of the sentences in gamma, but which makes theta false. And so in this case, we would write gamma, slash double turnstile theta. And so otherwise, if there is no such QL model that makes the gamma guys true and theta false, then we have semantic entailment, gamma double turnstile theta. And some shorthand we'll use, gamma would be true in the model, and so we write the model entails gamma, and theta would be true in the model, and so in this case, this were true. So you kind of can think about this double turnstile as a kind of like transitive relation. You can leapfrog from, hey, the gamma guys are true in the model, and whenever the gamma guys are true, the theta guys are true. So hey, the theta is true in the model as well. Cool. Derivability for infinitely many premises. So this is completely parallel to what we did for SND. We'll say some conclusion is QND derivable from a gamma set, possibly infinite, provided that there is some finite subset of gamma such that you get theta on the last line, and theta is directly in the scope of the delta premises. And then in this case, you'd write gamma single turnstile in QND theta. You also have delta, the finite guy single turnstile theta in QND. And if there is no such derivation, if there is no finite premise set delta from which to get theta using our syntactic rules, then you don't have derivability in QND. Cool. So just to very quickly recap our proof idea, in case any of you have not really been paying attention to sounds at all, or have already forgotten, we're constantly forgetting things. So we're just trying to show that this should really be sentence. The sentence on that line is entailed by the premises or assumptions accessible from the line. So we'll let PK be whatever sentence is on line K. So I should fix this to P3. So yeah. We only care about sentences now. WTF for the WFFs. And gamma K, this notation, is the set of premises or assumptions that are accessible on line K. It's all the stuff that we could refer to, to do our rules. Specifically, it's the open assumptions or premises, so the things that were introduced either by :PR or :AS in our proof system. So our sub-goal is just to show, given some sentence PK on line K, show that gamma K is single turnstile PK. Double turnstile PK. Show that we have semantic entailment. All right, so this was our proof strategy. It's the same proof strategy. We're just going to show that no matter what rule we use, we preserve truth. So we've handled the S&D rules. Now we have these 4 new rules. We do induction on the number of lines, and we show the base case has the property. That's just line number 1. And then our induction hypothesis is to assume the property holds for all the lines less than or equal to k. And in the induction step, we show that the property holds for the k plus 1 line by considering all the possible ways k plus 1 could arise. Any questions about the proof strategy? All right. So yeah, so we're remaining righteous. And we have this little shorthand, any line I in our derivation is righteous provided the set of open assumptions for that line semantically entail the sentence on that line. And the derivation is righteous if every line is righteous, and our goal is to prove that every derivation is righteous. That's sufficient to prove soundness. Yeah. So that's what this says. Sufficient to prove soundness. Okay. Cool. All right, so base case is exactly the same. You know, you have gamma 1. Gamma 1 is just the set of premises that are accessible on line 1. The set of premises that are accessible on line 1 is line 1. So the sentence on line 1 is P1, and P1 clearly entails itself. And so line number 1 is righteous. So exactly the same thing. So now we can state our induction step, assume that every line up to K is righteous. So the set of open assumptions for that line semantically entail PI. This again now for QL, the double turnstile, the way to read the double turnstile is, this is saying, for any model that makes all the gamma i's true, PI is true in that model. So they're basically saying, no matter how I interpret the constants or the predicates that occur in these sentences, if that interpretation makes the gamma i's true, then that interpretation makes the PI's true. Cool. So on the induction step, we consider the K+1 line, and we have now 16 cases to consider. We basically have done 12. For some, you know, it is true to be really rigorous, you'd have to modify the original 12 cases for S&D now to use this new semantic notion of model entailment, of entailment for models. But basically, you're just going to take what we did last week, replace truth value assignments with QL models, and then replace truth functional entailment with things like quantificational entailment, replace anywhere you appeal to jointly satisfiable, that's now jointly satisfiable in QL. So, yeah. So this double turnstile now means the sentence PK+1 is true in all the models that make true the premise set gamma K+1. So equivalent way to say this would be, this idea will matter a lot for the completeness proof. Whenever you have semantic entailment, the gamma guy's union with the negation of the conclusion is unsatisfiable. Because whenever these gamma guys are true, P has to be true, and so you'll never have a model that makes true gamma K+1 and the negation of P. Won't be any model that makes this union true, and so that's what it means to be unsatisfiable. But there's no model where the things are all true. Cool, all right, whoa, we hit a case. All right, we're doing one. Super, all right. So case 13, not good, bad luck. We are deriving the PK+1 sentence by universal elimination. And our goal is to show that the set of open assumptions relative to this line semantically entail PK+1. So, to save myself the hassle of drawing the pictures for every case, we have the derivation schemas. So we're now decidedly on looking at these pictures, and the pictures define the lines. And so, we'll hold this in our mind's eye. So the initial thing, it's really easy to state for all these. So it's like, what we have to do is just super clear. We just note, okay, form that the final sentence has, it is a substitution instance of Q. It's Q of C for X, C for chi. So again, this just means we've taken anywhere there was a chi on line H, we've replaced that chi with a C, and we've dropped the universal. So by our induction hypothesis, line H is righteous, and so we know that gamma sub H semantically entails for all chi Q. And since every assumption that's accessible at line H is also accessible at line K+1, we have one of these subset relationships. So we're just saying, all right, the gamma H guys, they are contained in gamma K+1. Often, they'll be the same. In this picture, since we don't have any other subgroups going on, they are the same. But gamma K+1 could be bigger than gamma H. So basically, if you make all the gamma K+1 guys true, then you have to make the gamma H guys true, and whenever the gamma H guys are true, for all chi Q is true. And so that means that this semantic entailment relation holds. So whenever we have a subset and we know that the subset semantically entails something, we know the superset semantically entails something. Any questions about that? That's what we were doing this last week, but maybe it didn't make sense last week. It still doesn't make sense now. All right. So lemma. A universally quantified sentence entails each of its substitution instances. And again, this is blitzingly obvious, this lemma. Blitzingly obvious, but we have to prove it. So basically, we're just saying any model that makes true for all chi q also makes true any substitution instance anytime we've stripped off the quantifier and we've replaced all the chi's with c's. And so given this lemma, now, so we know that the gamma k plus 1 semantically entails the universally quantified sentence. The lemma says whenever this thing is true, the substitution instance is true, and so gamma k plus 1 semantically entails q of c for chi. That's what we wanted to show. And so again, really obvious, what we're doing here. But now we have to prove this lemma. And to prove this lemma, we reason through satisfaction semantics. Now we go back to what we were talking about at the beginning of class. It becomes relevant at this point. Whole motivation to do this stuff. So we just consider an arbitrary model, M, that makes true the universally quantified thing, and then we ask ourselves, okay, what does it mean for that universally quantified thing to be true? And we look at truth in QL on the sheet, and it says, a sentence P of QL is true on a model M if and only if there's some variable assignment that satisfies it. And we're like, okay, great. So this thing for all chi is Q. This is true if there's at least one variable assignment d sub I that satisfies it. And now we look at the satisfaction conditions, because we're like, what the hell does satisfaction mean? So we look at satisfaction conditions for universally quantified well-formed formula, and that tells us a variable assignment d sub I satisfies for all xq, provided that the variant di of r for x satisfies q for each object r and d. So basically, when we assume that there's some model that makes this thing true, what we're assuming is that every single variant di of r for x satisfies q for each of the objects r. That's basically what we get to write at this point. And that's all just coming from the definitions. So it's a lot to hold in your head. And so we didn't hold it in our heads. We held it in our hands. All right, so by true in QL, some variable assigned to di that satisfies the universal. And then by the satisfaction conditions for the universally quantified sentences, this means that for each object in the domain, the variant di of sending the variable x to that object satisfies q, the non-universally quantified thing. So for each of our named c, for each constant c, I has to assign c some object and some object r, and we basically know at this point, well, whatever name c gets assigned to, it'll be assigned to some object whose variant satisfies q. And so this is just a way of rewriting this variant. I of c is the same as r, because c is the name of r. R is the referent, or the denotation of c. And so this thing satisfies q. Now we use our substitution lemma, and we get to say, okay, I have some variant that's satisfying q, so that here's my bracket on this side. Now I get to say, okay, the variable assignment di satisfies the substitution instance. So I just, I have it's biconditional in the substitution lemma. Given a variant satisfying the unsubstituted thing, the variable assignment satisfies the substitution instance, provided that the I of c and c are set up properly. So basically, provided that r is what c is a name of. Cool. And now I'm like, great, this is what I wanted. I wanted to show that this substitution instance is true. What does it mean to show it's true? It means that there's at least one variable assignment that satisfies it. Well, here it is, a variable assignment that satisfies this thing. And so we've done it. So for each of the constant c, no matter what constant it is, the substitution instance c for chi is true in the model. It'll be satisfied by this d sub I. Cool. Questions about this? honestly, guys, this is going better than I thought it would go. So, you know, I'm like, wow, okay, cool. You know, even if we don't finish all the cases, I think, you know, we did at least one, and we said all the words, you know, in a way that, you know, perhaps we could follow with our little thing. And so all the other cases are just like this one. They just get more complicated. Cool. All right, so we do existential introduction. So again, you know, first part's really easy. We're just basically noting the structure on our derivation schema. So the pk+1 sentence has this form of existentially quantified thing of a partial substitution instance, where we have replaced some but not necessarily all of the c's in our earlier q with chi's. So the earlier line h has a q on it, and again, this is implicit, but there has to be some constant c in the q. Otherwise, if there wasn't any constant c in the q, this substitution instance thing wouldn't make any sense, you know. So somewhere in the q there's a c. Could be multiple c's. Could be all the c's of the world, we might say, of which there are infinitely many because you get all the subscripts, you know, so you know that those are different things. C sub 1 is a different constant than c. C sub 22. All right, so again, we have the subset relationship. The open assumptions for line H are a subset of the open assumptions on the k+1 line. And so the gamma k+1, these open assumptions, they also semantically entail q. So now we have a lemma that takes us where we want to go. A sentence q entails any existentially quantified substitution instance. So entails anything of the form, there's a chi such that this partial substitution instance. And so given that, given gamma k+1 semantically entails q, and q semantically entails this thing, gamma k+1 semantically entails this thing, which is what we want to show. We want to show the k+1 line is righteous. And so if we prove this lemma, then we've done it, and we've shown the line is righteous. So we just have to show that given a sentence q, whenever this sentence q is true, any one of these existentially quantified partial substitution instances is also true. And again, this is really obvious. I mean, the thought here is just like, you know, we might say something like, Johnny is a little boy. And then we could say, there is at least one thing that is a little boy. That's what this lemma is saying. That's all it's saying. You know, it's very obvious. Why are we doing this? So again, we're going to consider any model, arbitrary model M that makes true Q. So here I'm just making explicit there's some C's in the Q. So this is some new meta language notation. C occurs somewhere in Q. And so by the definition of true in QL, that means there's some variable assignment d sub I that satisfies Q of C in M. And let R be the object in D that C stands for. C has to be a name of something. Our interpretation function sends constants to objects, and so there's some R that stands for this thing. Cool. So then the variant di of R for chi, this satisfies this partial substitution instance. So this is the open sentence we would get by replacing some of the C's with chi's. It would be satisfied by the object R. So, cool. And now we're like, okay, what does it mean to satisfy an existentially quantified thing? This is definition of satisfaction conditions for existentially quantified formula. So some variable assignment di satisfies an existentially quantified thing, provided there's at least some object R, such that the variant di of R for chi satisfies, in this case, the partial substitution instance, Q of chi for C. And we're like, hey, we just argued that there is such a thing, right there. And so, since this variant exists, this di satisfies this existentially quantified thing, and so this existentially quantified thing is true in the model. And so that's what we wanted to show. Any questions about this? Yeah. All right. So cool. We'll at least do existential elimination, and then we might skirt through the universal introduction and wave our hands wildly. We might say. All right. So again, the initial thing is super chill. We just want to say what's going on, and our picture tells us what's going on. and we just want to, pick out the right subset relationships, apply the induction hypothesis. So you want to make sure you do that. Cool. So we have this restriction, so this restriction really matters. The constant C can't occur in the sentence, there's a chi that Q, it can't occur in the final sentence, the one on line k plus 1, and it can't occur, we've written it on the rule sheet, C does not occur in any other undischarged assumptions that line J is in the scope of. Basically, since line J is a subset of, gamma J is a subset of gamma k plus 1 union the thing on line J, we can also basically say that our first restriction means the constant C can occur in any open premise in the gamma k plus 1 as well. And that'll just be an easier way to write it for purposes of our lemma. Cool. So by induction hypothesis, lines H and J are righteous, and so gamma H semantically entails there's a chi to Q, and gamma M semantically entails pk plus 1. And again, that's just coming from the sheet. So, cool. All right, so now we try to find our subset relations, and we notice, okay, everything that's accessible at line H is also accessible at line k plus 1, so the gamma H's are contained in gamma k plus 1. The gamma H semantically entails the existential, and so gamma k plus 1 semantically entails the existential. And this thing in green will feed into a lemma down below, so this is an important thing. So now we know that everything that's in gamma M, so gamma M also has a pk plus 1, but it's in the scope of a subproof. So gamma M is, subproofed in. So we notice that all those guys are accessible to k plus 1 except the assumption on line J that starts the subproof. And so gamma M is contained within gamma k plus 1 union the thing on line J, which is the substitution instance, Q of C for M. Questions about this? All right. So since we know that gamma M semantically entails pk plus 1, and gamma M is a subset of this thing, this union, we know the union thing semantically entails pk plus 1. And that will also be another fact that we use in our lemma. So here's our lemma. This one's more complicated because it involves these restrictions, which you appeal to in the proof. So the lemma says, if constant C does not occur in this existentially quantified thing, there's a chi to Q, doesn't occur in some sentence P, or in a set gamma, and if, secondly, gamma semantically entails the existential, and thirdly, the gamma union, the substitution instance semantically entails P, then gamma entails P, for any P. Because remember, the cool thing about this rule, existential elimination, is pk plus 1 can really be anything that doesn't have a C in it. So whereas in the other rules, the thing at the bottom is related to the Q, it's all some kind of like substitutions into the Q. Here, this pk plus 1, this is just some, it could be basically anything that doesn't have a C in it. So this lemma is, a lot more general. We just have some arbitrary key, and we're showing that gamma set guys entail the P, provided that these three conditions are met. So it's kind of like an intricate interlocking relation. And that's exactly what this, rule thing is showing. There's some intricate relationship between these conditions. Cool. And so then, apply the lemma we will have shown, gamma k plus 1, semantically entails pk plus 1, so this p is just, going to be our pk plus 1. This gamma is going to be our gamma k plus 1. And we just feed in the stuff we have on this page in the lemma, and then we have it. So the thing is just to show the lemma. And this lemma is not, oh shit, I forgot about this. Yeah, all right, so, well, totally forgot, yeah. So to prove the last two cases, you need another lemma. And this lemma is actually interesting. So, and again, we're not going to prove this, it's another induction, super chill induction, but this lemma actually does have some philosophical interest. So this would be, even if this is the last thing we talk about today, that's not that sad. So what this locality lemma tells you is, if you have interpretations that locally agree on how they're handling symbols, so basically you have two interpretations that are interpreting a finite subset of symbols in exactly the same way, then those models agree on what's entailed. So if one of those models entails a sentence, the other model that locally agrees with on interpreting the syntax also has to entail the same sentence. And that's intuitive, but it's kind of cool, you know, to have that formally shown. It basically means these two models, they agree on, you know, maybe like all the names of any object in this room. They might radically disagree about all the other names. But at least when it comes to claims about things in this room, those two models will entail the exact same claims. They locally agree. Cool. So this is our setup, you know, to make this precise. So really intuitive idea, kind of a cool one. And we can make it precise with our language. So we're going to focus on some given sentence P, and we consider two models, M1, which is domain, and an interpretation function, and another model which has the same domain, same P, but a different interpretation function. And the assumption here is that the interpretation functions I1 and I2, they are exactly the same for any constants or predicates that appear in the sentence P. So when it comes to interpreting P, I1 and I2 say exactly the same thing, even though I1 and I2 can disagree on how to interpret other sentences besides P. So they locally agree on P. So local agreement on how to interpret P, then the upshot is if model 1 entails P, then model 2 entails P, and vice versa. So if P is true in the first model, P is true in the second, and vice versa. Which again, you think this, you know, this should make a lot of sense because when you're showing P is true, it should only really matter. What's relevant is the stuff in P. Other stuff's not relevant. So this locality lemma is capturing this idea. Cool. So we use this lemma in the cases of for all I and existential. We have 2 minutes. Maybe we'll do the lemma for case 16, which is not that bad, even though it seems like it'd be pretty bad, but it's really not that awful. So we just have to show in some model, if you make all the gamma guys true, then you make P true. So we're just trying to show there's some model, you know, given any model that makes the gamma guys true, the model makes P true. So we're assuming gamma makes true, there's something that's a Q, and this just means basically there's some object in the domain that satisfies Q. Again, formally, there's some variable assignment such that di of r for chi satisfies Q. That's the formal condition. So since the constant C doesn't occur in any of these things, we can just define some new model M prime. And this model M prime is just like M, except that it sends C to R. It sends C to R, where R is the thing that makes true, you know, the relevant sentences. And so since this variant, di of r for chi, satisfies Q, we'll know that the variant di prime, now this is in, you know, our different model M prime, this variant satisfies Q as well. And so by this substitution lemma, the variant is satisfying Q, and so di prime, the thing in our second model, satisfies the substitution instance. And so the substitution instance is true in the model M prime. And now we're like, the model M prime is just like the model M. They only disagreed about C. And so we get to apply locality. So since M semantically entails gamma, we have that M prime semantically entails gamma as well. And so M prime has to semantically entail the gamma guys and this, you know, thing here. So it entails the union. And by assumption, this union entails P, and so M prime entails P. And then again by locality, it's right at the bottom. Again by locality, our original model has to semantically entail P, and so that's just to say the gamma guys entail P. So we did it. So all right, so we didn't do the final case, but it's in the slides, and we'll start on completeness on Wednesday. Let me just make sure I got everybody who's here in the good pile. Gerardo, Tim, Sue Daniels, and Danny. Did you grab your name tag, Danny? Oh, great. Okay, cool. All right, thank you guys for bearing with me on that. I think that's like the limits of what the human brain can handle in 8 minutes, right? I know, like what for another person, another sucker, we might say. I just put you in the good pile, yeah. So if you had this lemma, the consistency lemma, that let you convert syntactic consistency in your derivation system to satisfiability, then the proof is like, a page, one slide, super chill. So then the whole struggle is to prove this consistency lemma for predicate logic, and we're going to do the same thing we did for sentential logic. We're going to build up a maximal set, and the maximal set will contain every single sentence now with predicate logic that it can, such that you maintain syntactic consistency. And the only wrinkle we'll have to add, well, two wrinkles. One, we'll need an additional property called existential completeness, where you throw in substitution instances for any existential. And so we'll construct this thing, gamma star. We'll show it has these two properties, that it's maximally consistent in QND. Yeah, more people. Great, we're running through what we're doing today, which is another disaster, but hopefully not as bad as Monday. We don't have to do nitty-gritty satisfaction semantics, so that's good. So we construct this guy, we show it has these two properties, and then using the fact that we have this thing that's maximal, and no worries, dude, I don't care. Honestly, we should just have music playing in the background for the whole class, right? We should have like Eye of the Tiger for this shit, probably. So once we have this maximal thing that's also existentially complete, we'll then use it to construct a model that satisfies every sentence in gamma star. Our initial thing, gamma, which is just consistent in QND, that'll be a subset of gamma star, and so by satisfying gamma star, we will have satisfied the thing we wanted, and so then we'll have shown that any set that is syntactically consistent is also satisfiable. That's the major lemma proof, and then the whole proof is super chill. And yeah, in the model construction, we'll do the same thing. We'll have a membership lemma, which will extend to include the quantifiers. We'll construct the model, being clever, and then we'll do an induction to show basically that any sentence is true in the model if and only if that sentence is in the flow, if it's in the maximal then. And there'll be one little wrinkle, because you see this little prime here, QL prime. What is QL prime? We will see. So we're doing a trick. So the proof in the book is long, this is long, but one thing that I was able to do to save all of us a little bit of a headache was to eliminate about 2 pages. How's it going? Eliminated about 2 or 3 pages from the proof in the book using a cool idea where we'll extend our language QL to a slightly bigger language QL prime. We'll be working in QL prime, and that avoids some tedium. And this is why they're paying me the big bucks, right? Paying me the big bucks so I can think how to save you guys 2 pages of a proof. Bam! So it's like every single step in here is simple. There's nothing really that complicated. It's just long. It's just a long series of, this is what we might call an elementary proof in a way. Every idea is elementary. It's just the whole thing together is kind of overwhelming. But it's structurally, the same as what we did for sentential logic. So, yeah, let's go ahead. Oh yeah, and I should remark, why am I wearing this ridiculous sweater today? So, late last night, once I finished working, I went down to check my mail, and there was a big box that could only be from one person, my kind of crazy Aunt Marilyn, there's a long history of Aunt Marilyn. But anyways, Aunt Marilyn, bless her heart, she knits me a sweater almost every Christmas. And so this is a hand-knitted sweater, and unlike every other sweater she's knitted me, this one has 2 special properties. One, it kind of fits me. Normally they don't. 2, because she uses my uncle as a model, but my uncle's not the same size as me. So somehow she nailed it this year, I think. One arm is normally a little bit longer than the other. So that's a property of my uncle, I think. I measure my I'm good. And the other thing, normally they're very drab colors, but this is a very vibrant. So I was like, all right, this is kind of hilarious. I'll wear this one time probably in my life, so.
Oh, very nice.
All right, so you guys ready for this? We plunge in. So I'm just gonna, really we're proving completeness, we're proving from a double turnstile, we can get to a single turnstile in QND. That's the whole goal, and so this just means anytime you have a valid argument in QL, you can use your derivation system. The cash value of this is you don't have to reason about models to show validity. You can rely on the derivation system. So you think, wow, cool, that's what we say. All right, so we have the semantic notion. Remember, gamma double turnstiles P just means there's no QL model M such that gamma is satisfied while the sentence is false. That's our notion of entailment in QL. So equivalent to this means gamma union not P is unsatisfiable. There's no QL model that makes true the gamma guys and makes true the negation conclusion. And we'll use this fact in our proof. Cool. So we have a syntactic notion that we just went over. This is the notion of satisfiability. You have a model that makes true everything. Just like with SND, we have a syntactic notion of consistency, which just means a set of QL sentences is consistent in QND, consistent in our derivation system, provided you can't derive a contradictory sentence back from it. So just remember to keep these two notions separate. The syntactic one, this is the semantic one, which we'll just call satisfiability. And then we have the syntactic one, so inconsistent in QND means from the premises in gamma you could derive contradictory formulas within the scope of those gamma guys. So consistent in QND means you can't do that. There's no derivation that has the contradictory guys. Cool. Any questions on these definitions? We're just extending them to QL and QND. All right, so proof sketch, we do the proof in 2 slides, and then we're kind of like, yeah, we did the whole thing, modulo this lemma. So we want to prove from double turnstile we go to single, so we assume that the set gamma semantically entails P. So this would mean that gamma union the negation of the conclusion is unsatisfiable, so that means there's no QL model that satisfies this set. This set is semantically inconsistent, it's unsatisfiable. So now we appeal to this consistency lemma, which we'll spend all of today proving, if we finish it even. So this says any QND consistent set is satisfiable, and so by the contrapositive of this thing, if you have a set that's unsatisfiable, then it's inconsistent in QND. And this thing is unsatisfiable, and so this thing is inconsistent in QND. And then we're like, cool, what's the value of that? So here's our contrapositive. If you are unsatisfiable, then you are syntactically inconsistent. And we know this thing's unsatisfiable. So we see by contrapositive, this thing is inconsistent. And now we can do negation elimination. So we can prove gamma single turnstile P by negation elimination. Because we can get from this set an R and not R, so we can assume not P for negation elimination and derive P, and then we have what we wanted, which is gamma single turnstile P. So that's the whole proof. That's the whole thing. So super easy. And the hard thing is just to prove this lemma that from syntactic consistency we can go to satisfiability. And this just means if I tell you this thing's syntactically consistent, you have to give me a model. You have to give me a model that satisfies all the sentences. And we're going to do that by this trick of constructing a model for this mega set of sentences that's maximally complete and also has this additional property. This is just how to do negation elimination. I assume you guys know how to do that. So we're going to prove this consistency lemma in, again, 3 stages, maybe 4 stages. How do we count stages? A little arbitrary, right? So in the first stage, we construct the superset gamma star that's maximally QND consistent, and this means just what it did in the SND context. But now we have this additional property of existential completeness, which sounds great. We all want to be existentially complete, right? That's what we're striving for. This is like self-actualization, basically. We're saying that this gamma star is now not just maximally QND consistent, it is self-actualized, and we're very happy for it. So once we have this thing, then we show that any such existentially complete, maximally syntactically consistent set is satisfiable, and we do that by constructing a model. that satisfies everything in gamma star. The wrinkle is we're working in an extended language of QL prime, which at some slide in the future I will define for you. Until then, it is undefined. What is this mysterious QL prime? And so gamma will be in gamma star, and so the QL prime model will satisfy gamma in QL prime, and then we think, okay, well, we're not happy with the QL prime model, we need a QL model. So we have to go from QL prime model to QL model, but we set everything up well so that that is trivial, and it will fall out right away. And then we're like, yeah, good shit. So this part, using QL prime, this is what it makes what we're doing a little bit less convoluted than what the book does. So that's cool. And the other thing that's cool about doing it this way is you really see that there's nothing special about QL, the specific way we define QL. The proof we construct would work for any first order language. So any language that had our connectives, our quantifiers, and had sentences and predicates, but not necessarily the names that we have, in QL, the constants we have and the predicates we have. Could have other names and other predicates, and this proof idea would apply to any such first order language. So that's, that's kind of cool, right? We're really showing a more general thing that any first order language is complete in a derivation system like ours. Cool. All right, so we go in. Oh yeah, stage 0. Yeah, see, I lied. There's a stage 0. Defining these terms, which seems important. So this one hopefully is familiar because it's the same as for S and D. We have maximal Q and D consistency provided you are Q and D consistent. Can't direct contradict your sentences. And this maximal property, if you were to add any additional sentence to a maximally consistent thing, you'd get a Q and D inconsistent set. So gamma star is as big as it can be while maintaining syntactic consistency. Cool. So unlike with SL, this is no longer enough to ensure that we could construct a model that satisfies everything in gamma star. And basically the issue is, remember we have this membership lemma. It's motivated by something is in the club if and only if the relevant truth conditions are in the club. So it's purely syntactic, the membership lemma, but it's motivated by truth conditions. And what's the truth condition for an existential? An existential, something like there exists an X, P, an existential like this. There exists an X such that P, this is true provided there is something that is a P. So provided that there is a true substitution instance, some name sub in for the variable. The existential is true provided some substitution instance of it is true. So this is just we have a very concrete example. There is something such that f(x), then this requires something like FCC to be true for some constant c. So we basically, in order for the membership lemma to work out in this context, we have to require that every existential sentence in the club has a substitution instance in the club. And so we're just going to define a new property, to keep track of this condition. And we'll call it existential completeness. So a set of gamma of QL or QL prime sentences is existentially complete just in case for every sentence in gamma of this existential form, there's at least one substitution instance in gamma. Are there questions on what this means? Cool. So again, everything's elementary. This is chill idea. So our motivation is just this thing's true in a model if there's some object that's P. So we need recourse. Oh yeah, so this is where we hit a wrinkle at this point because in order to maintain consistency as we're adding sentences, remember we build things up. We enumerate the sentences and we build things up in stages, adding sentences into gamma star. If we want to avoid hitting a contradiction while preserving existential completeness, we're going to need an infinity of unused constants. Because otherwise you might add in a sentence that would contradict an earlier sentence when you try to add a substitution instance. So when we add in these substitution instances, you need to add one in that uses a constant that's never been used before. And the issue is that our initial set gamma might itself be countably infinite. So the initial set gamma might use every single constant possible in QL. So the constants in QL, remember, are constants. They're things like A, B, up to V, and also index versions of these, so things like A11 and B55. So we have a countable infinity of constants, but gamma could use every single one of them. And so we need some way to get new constants so that we can avoid this possible issue of a substitution instance contradicting a sentence that's already in gamma. Basically, it's like in gamma you could already have not FCC. And so when you want to add in a substitution instance, well, if you reused a C, this thing you added in could contradict something already in gamma, and then you wouldn't be able to add in a substitution instance for this thing. And then you wouldn't be able to build up something that's existentially complete. But if you can always introduce a new constant, well, then there won't be any problem with that. So this is our issue. Gamma might be infinite, and so we might have already used the thing. So what are we to do? So the book does this thing where they say, well, hey, we could just move from gamma to a set that only ever uses even constants, evenly indexed constants, then show that whatever properties that thing has or original thing has, then when we build up our maximal thing, we'll have recourse to all the odd index constants. Then at the end of the proof, you just have to show, okay, now showing that the evenly indexed thing is satisfiable, you have to show the original thing is satisfiable, you have to use that locality lemma to do that. So you could do it that way, but it kind of sucks. And it's more confusing like how to motivate it, I think. So what we're gonna do is we're just gonna add in new constants. Why not? We can do that. This is a language, the constants really aren't that important, right? I mean, they are really important, but it's very conventional. So we're just gonna add in new ones. So we introduced QL prime, which is just like QL. Everything's exactly the same, except now we allow subscripted constants to have prime indices. So we're throwing in things like C11 prime, B234 prime, G2 prime, and the prime symbol we stipulate is always at the end of the numbers. So we never have things like 1 prime 1, but we can have 11 prime. And the unsubscripted constants are the same, A through D, totally chill. So we're just adding in one new symbol. Alternatively, you can think about it, we're adding in 10 new symbols. We're adding in 0 prime, 1 prime, 2 prime, 3 prime, think about it either way. And we recursively define truth in QL prime exactly the same recursive definition. Satisfaction semantics is in there, but we try to be quiet about that. So we don't like satisfaction semantics. And we do not allow prime indices on the predicates. So remember, predicates can be indexed, but we're just going to say, yeah, we don't need to add in an infinity of new predicates. So, we'll keep it clean. So yeah, this is the moral. We should start after us. Questions about QL prime? Cool. So now the rest of the proof until the very end is basically we're working in QL prime. And so we have now entailment in QL prime. And so, there is something a little, deviant we're doing here. It's like technically entailment in QL prime is a different double turnstile. So this thing comes with a different double turnstile than QL. But they're so similar that it's all going to work out. Cool. So we construct gamma star in QL prime. So we have to enumerate the QL prime sentences, and this is chill. Basically, if you could enumerate stuff in S and D, you can, in SL, you can enumerate stuff in QL prime. So we just stipulate an alphabetical order for our symbols. This part is what we had for SL. Now we tack on the constants and the variables, W through Z, and our two new operators, universal existential and our new symbol prime. So we just tack these on. We give each one of these an index. So before we had like 10 to like 55 or something. Now we have 10 through 84. So the prime symbol gets assigned index 84. And so now each QL prime sentence has its own number, which you just get, like before, by looking at the symbol and assigning the number. So A ends up being 30 in this index scheme. The negation sign is 10, so not A, it's just 1030. You just go from left to right, replace every symbol with its index. And then every single QL prime sentence, you know, the countable infinity of them, they each have their own number. Questions about enumeration? Cool. All right, so to form this thing to make it maximally S&D consistent, we're just doing a variation on what we did for the case of SL, where we're just going to go through stages for the case sentence. We will consider adding it to a smaller set, and if it preserves consistency, we'll throw it in. If it doesn't preserve consistency, we won't throw it in. And now we have this wrinkle with the existential completeness thing. And so we have basically a new case to consider. So this is what we did for SL. You know, if A could be added to gamma, then we threw it in. Otherwise, we just let gamma sub 1 be gamma, and then we move to the next sentence. And gamma star resulted from just doing this for every SL sentence. Now we have to handle these existential things. We want to ensure, in the way we construct gamma star, that it will be existentially complete. So we want to ensure that whenever the case sentence has this form, it's an existential, we also throw in a substitution instance of this sentence if we could put this existential in with our earlier gamma while preserving consistency. That's our motivation. Questions on motivation? Cool. All right. So we're going to let gamma 0 be our initial gamma, where really all we're assuming about gamma is that it is consistent in QND. We're just assuming gamma is consistent in QND, so gamma 0 is consistent in QND. Now we consider the case sentence pk in our enumeration, and we define gamma k plus 1 basically like piecewise as follows. So in the first condition, if throwing in pk to the earlier gamma k would be QND inconsistent, then we don't throw it in. We just let gamma k plus 1 stay what it was at the earlier stage gamma k. So that makes sense, right? Second case, this is just like what we did for SL. If pk is not an existential and gamma k union pk is consistent, then gamma k plus 1 becomes this bigger thing where we throw in pk. This is just like what we did for SL. Now we have this third thing. Okay, what happens if pk does have the form of an existential? Now, if it has the form of an existential and gamma k union pk is inconsistent, well then we're in this case 1. So we're only interested in what happens if it's existential and throwing it in would be consistent. Now we want to ensure existential completeness, and so we also want to add in a substitution instance. So here's the substitution instance, Q of C for chi, and we, to form the substitution instance we throw in, we use the alphabetically earliest constant that has never appeared in gamma k, and it's not in pk. So we use a constant that has not been used before, and this is to avoid accidentally contradicting an earlier sentence, which would spoil syntactic consistency. Cool. So we're guaranteed to have this constant C that's never been used before because gamma 0 is in QL, and so we have this countable infinity of subscripted constants from QL prime at each stage. So gamma 0, the thing we start with, is a QL thing. It could have infinitely many unprimed constants, but it can't have all the the new infinity of prime constants we've thrown in. So all of those are available at every single stage, because at the kth stage, we're guaranteed to have a kth constant that has never been used before, because QL prime is giving us another countable infinity of constants. Cool. And then just like in the SL case, once we've stipulated these conditions, this maximally consistent set is formally defined as the infinite union over all these gamma k's. So of course, you know, we speak metaphorically when we talk about adding things in at a stage. Yeah?
Why does 3 need to be a special case? Like, why can't we just say that we'll eventually get to PK dagger? You know, when.
Yeah. No, so it's a great question. I was thinking about this as well. Why this has to be a special case, and I had some glimmers at points when we were using the existential completeness thing, but I say that unless I had a thought that I then forgot, I don't think I felt satisfied by why we consider this a special case. So honestly, to you guys, as we go through this proof, if at any point it seems to you, oh shit, this is why we have this as a special case, and couldn't just you know, leave it to, well, hey, we're gonna hit the substitution instance eventually because it is, you know, has some number. It's in the enumeration. Let me know. The closest I got was the thought, try to construct a minimal counterexample where you have something that is consistent, but then if you didn't add in a substitution instance right away, when you add in some existential thing, then you could. This would be a scenario where this really was needed. A scenario where you could form a consistent set such that as you went along, every time you hit a substitution instance of a thing. So yeah, let me try to make this more concrete, because this is as far as I got on it. And it seems possible that this would happen, in which case we would need this thing. So imagine that there exists, this particular example may not work, but imagine that this thing's in gamma k, and it is maximally QMD consistent. And imagine we don't throw in a substitution instance at the point k. Now imagine somehow that, you know, so consider gamma star such that every substitution instance that could be added at a later stage. So So imagine that every time we do hit a substitution instance of this at some later stage like n, once we've added this thing, we've added some other sentences such that every substitution instance for this that we could be added later would make this gamma n inconsistent. Then what would happen is you would build up a maximally consistent set, but it wouldn't be existentially complete. Now, my thought is perhaps it's possible to think of an example like this. I couldn't think of one off the top of my head. But if you could, then that would be a counterexample to this thought of, oh, let's just wait until we hit these substitutions. Yeah, Henry?
I mean, if you're adding something in that's inconsistent with every substitution instance of fxx, I guess how would that be consistent with for some x?
Yeah, no, that's when I was trying to think of an example of like basically you'd have to add this thing in at like the case stage where it was already there before. Then you'd have to add in some sentence, probably of a universal, that contradicted every substitution instance of this. But somehow, yeah, but some. Oh, well, I guess. I don't know. Yeah, I mean, let me know if you guys can think of one. Because it does seem weird. It seems like, yeah, you need something that in some sense, you know, entails, at least derivationally, that this thing itself is false, but then you'd be able to derive in your system the negation of this thing, so it wouldn't be consistent. So yeah, it's a good question. And regardless, you know, keeping with the fact that this is very elementary proof, we at least do this because now we make it explicit if we can prove this thing's existentially complete. Yeah.
Yeah, I think, yeah, like for each constant, you could add something different that contradicted P sub k dagger, like maybe like right before you would add P sub k dagger.
Yeah, okay. Thanks. Yeah, so I think, because we might also, in this thing, at this point in gamma k, we might have, we might have the negations of F, we might have like all these, like not FCC, not FAA, and we might also have them with the prime things, like A1 prime, A1 prime. So imagine that those were all in there, and now every time I hit this, actually, I mean, this specific example might not happen based on our lexical ordering, because it seems like we hit the unnegated things earlier, but imagine we had, so I think this actually would be, I think this is why we really need it, because imagine we have things of the form, there's this next not fx, then consider gamma star that has every instance of f c for x. So imagine gamma star has all these things, f, cc, FAA, etc. These all occur earlier in our enumeration than the instances of this, like not FAA. So we would hit these before, and if we added them, then we end up with a maximally consistent set that nevertheless doesn't have a single substitution instance of this thing. So I think at least something like this, I think, seems to motivate this condition. Yeah. But yeah, thanks for helping me think through that, because so I was working on this yesterday. This thought occurred to me as well. So, why do we really need this condition? So. All right. So after this detour, in virtue of which we're probably not going to finish this proof, that's okay. So at this point, we take ourselves to have constructed gamma star, and now we just have to show gamma star has these two properties. So we have to show that gamma star actually is maximally QMD consistent and existentially complete. So we got to prove three things. One, it's consistent. Two, if you were to add any additional sentence to gamma star, then it would be QMD inconsistent. And finally, that for every QL prime sentence of this existential form, there's at least one substitution instance. And so this, this stage 2 is like really obvious. There's a sense in which I shouldn't even walk through this proof, because it's just like, hey, by construction, we basically, did this whole thing. In the SL case, this is what we have to show, and it was, really obvious. And there's one part where you do, one part is, I guess, in some sense, non-trivial, where there really is something to show. So we'll try to get to that part. So imagine you assume for a contradiction that gamma star were inconsistent, then there'd be some finite subset of gamma star that derived a contradictory pair. Then this thing's finite, so it would occur in some gamma k plus 1, and so that gamma k plus 1 would be QMD inconsistent. Now the contradiction is to show, hey, we actually have every gamma k plus 1 is QMD consistent. So if you can show this, then you would reductio, the thought that gamma star could be syntactically consistent. So you just go through the cases. There's 3 cases, 3 ways that gamma k plus 1 could arise. The first one, which I probably didn't list here, is if in adding the sentence you formed an inconsistent thing, well, you just didn't add that sentence, and you let gamma k plus 1 be gamma k, which by assumption was consistent. So that's really the first case. So second case, if pk is not existential, we throw it in only if the resulting thing is consistent. So this is just like what we said for SL. And at this point in the SL case, we were done, basically. Now there's a further thing you have to show. What happens if pk is of this form existential, well, we said we put it in only if Q and E is consistent, but this thing on its own, gamma k with the existential thing, was not the whole gamma k plus 1. We threw in a substitution instance. So there is a further thing to show here, which you actually do have to do a proof for. You have to show that gamma k plus 1 with the existential and with the substitution instance is Q and D consistent. And what you get to assume is just that gamma k with the existential is Q and D consistent. So you basically have to show, hey, if I have a consistent set that has the existential, throwing in a substitution instance with a constant that has never occurred before is also Q and D consistent. So here's a lemma, which in some sense is not obvious. So you really have to prove this. If the constant C does not occur in this Q and D set gamma k union existential Q, then gamma k union existential Q, Q of C for chi is Q and D consistent. So this is a hot tip for you guys. There is some chance that proving this lemma will occur on the final. I think this is a nice problem. It doesn't take that long, and it shows, requires some facility with our derivation system and reasoning a bit about what these words mean: Q and D consistent, Q and D inconsistent. So try to think about this. Basically, the mega hint that I'll give, try to remember if this does happen on the final, is you just want to look at the rule existential elimination. You want to look at that rule, and you just want to notice that, so in existential elimination, you have some existential, we can let it be, there exists something Q. So, we have other stuff in gamma, we have some finite delta subset of gamma k. We have our existential. Now, what do you do when you do existential elimination? You assume a substitution instance for existential elimination. So we assume something like Q of C for chi. This is assumed for existential elimination. Now we're assuming that we can't get an R and a not R from just these guys. Any finite delta and the existential Q. Now imagine for contradiction that throwing in the substitution instance resulted in an inconsistent set. That would mean when I have these guys and I've thrown this in and this is accessible, then I could get contradictory R and not R. So at this point I could get R and not R. Well, hey, remember, if you can get R and not R, you can prove anything. So in particular, I would be able to assume, the new subproof, assume the negation of, don't want to do that. Just assume there exists something that's a Q, assume this for negation intro. Assume for negation intro. Now get my R and my not R from above. Then I can pop out with not there exists an exit Q by negation introduction. And now this thing doesn't have the constant C occurring in it, and C doesn't occur anywhere else outside the subproof because we chose C as a constant that's never appeared before. And so I meet the conditions for existential elimination, and so now I can pop out of the whole subproof and I can write not there exists exit Q. This contradicts this thing, and now this shows, hey, from something I assumed that was Q and D consistent, shit, I got a contradictory pair. Well, that's a contradiction, because I assumed that I could never get a contradictory pair from these guys. And here I just did it, assuming for contradiction that adding in the Q, the substitution instance, resulted in a consistent set. So that's basically the thing. So mega hint to you guys is remember this shit could be on the final, right? So thanks for coming to class today. Otherwise, it'd be really sad to do this with like one person, even two people is a healthy number, I would say. Cool. All right, so we did the lemma, and so gamma star's got to be Q and D consistent. Oh yeah, and I say this part of the book really screws up at this point. they cite something that's like a semantic condition, has nothing to do with what's going on. So the book notes that you have to prove this, but they cite this other lemma that is just not set up properly to show this. So it's really a mistake in the book. Cool. So we got to show the maximal part. This is just like SL, so we'll glaze over this. We're basically just, hey, assume for contradiction it worked, maximally QMD consistent, then you'd be able to add in some sentence to make it bigger, but hey, that sentence appeared earlier, blah, blah, blah. You know, so that, yeah, so then we would have had some earlier thing that be QMD consistent. So, all right, so we got to show existential completeness. And so we just have to show that for every single one of the existentials in gamma star, there's a substitution instance. This is really trivial. We constructed gamma star so that this would be true. So each one of these existential sentences occurs, and if we could have added it at the kth stage, well then we also added a substitution instance. And furthermore, imagine that this existential, whatever it is, was already in at the initial stage. Then what happens? Well, then this k+1 stage would just equal gamma k union the substitution instance, because we still, you know, this thing, the existential, even if it starts off, you know, its life in gamma, it is still the kth sentence. We will still consider it at the kth stage, and at the kth stage we'll know, well, hey, it's already in the gamma thing, so of course we can add it while preserving consistency. And so then at the kth stage, we also, by our construction clause, we throw in a substitution instance. So even if you start off with gamma where this thing's in and doesn't have a substitution instance, when you hit its number, you throw in a substitution instance by construction. So we don't miss anything. And these are the only two possible cases. Either the thing was already in gamma at the 0 stage, or it got added at some later stage. So we expand logical space. Questions on this? Cool. All right, so, so now we go to the model. So, cool, so this is the fun part. We get to build this thing. Yeah, we got 35 minutes. We might do it. We might, glazing over some steps, right? So remember, we're gonna hit a membership lemma. We're gonna have to prove shit about that. And then we're gonna hit an induction, and that will require proving things as well. So those are, the two tedious parts. But so this is our goal in stage 3, is to show, given we have this existentially complete, maximally consistent set gamma star, show that this thing's satisfiable. Construct a model that satisfies our gamma star. And this will be a QL prime model in QL prime. We'll call this fractor M star. This is just like the book's I star, though the book's I star occurs in QL, and we are in QL prime. Cool. So our proof idea is just the same as before. For everything, either you're in the club or your enemy is in the club. So P is in the club or not P is in the club. And this holds in particular for every one of the atomic sentences of QL prime. Where the atomics now, since we're in predicate logic, they include not just the atomic sentences of SL, they include the atomic QL terms, which are things just like this, FCC. So FCC is the QL atomic predicate followed by some series of terms, constants or variables. And when you focus on sentences, you can't have free variables. So sentences never have free variables. Cool. So we're going to construct our model such that for each atomic sentence, it's true in the model if and only if it's in the club. So this notation, M star entails A. This is just shorthand for A is true in the model M star. Just a convenient notation for that. And in some sense, this is an abusive notation because double turnstile is semantic entailment. And that's a relation between sentences, sets of sentences, and sentences. M star is a model. It's not a set of sentences. But we abuse notation because we're trying to save ink in our virtual reality. So this was the same idea as what we did for SL. Remember, SL, our thought was we just need to make the interpretation I assign every atomic sentence true if and only if that atomic sentence is in the club. And then you're basically using the fact that the club is consistent, you never have contradictory pairs appearing to say, yeah, the club itself gives you the model. Everything in the club is basically the model. So again, the idea is just like what we did for trees with complete open branches. You know, from the complete open branch, you never had a contradictory pair, and so you said, oh, I can construct a truth value assignment on my complete open branch that made true everything in my set. This maximally consistent thing is just like a complete open branch. It's just, you know, infinite, whereas complete open branches were finite. Cool. And so then, you know, QL prime is the same recursive structure, and so if this property holds for the atomics, you can do an induction and show it holds for any QL prime sentence. That sentence P is true in the model if and only if it's in the club. Questions about our motivation? Cool. All right, so we're going to do this membership lemma thing again, where in principle you could avoid doing this and go right to the induction, but then you'd have to just prove this in the midst of your induction, and it's like, you know, hard to keep in your head. So we split it off as a separate lemma, and it's purely syntactic, has nothing to do with semantics, although it's motivated, of course, by truth conditions. So this gamma star is the club with the baddest mother effing bouncer you've ever seen to enforce its maximal consistency. I can't, we'll see where this goes, right? Before this gets, let's sense in the gamma star. He checks who else is good. You hear? All right, so this is our membership lemma. You know, we get a little bored when we're making these slides, right? So we gotta, especially, you know, we hit this part of class where I'm like, oh my God, we're still here. So this is our membership lemma. We have 5 conditions which are exactly the same as what we had for FL. So these are the ones for our 5 connectives. And now, you know, the only difference is P and Q, they don't have to be atomic sentences. P can be some, you know, quantified expression. You know, it can be a sentence of QL, but of course sentences of QL prime can still be connected by these 5 connectives. So these are all motivated by the truth conditions for these connectives, but this is syntactic. And so now we just have 2 more lemma conditions. We have one for the universal quantifier, we have one for the existential quantifier. So for the universal, everything as a P is in the club if and only if for each constant C, there's the substitution instance is in the club. So you only put this universal in the club if you put in every single one of its substitution instances for this infinity of constants. So it's a lot of things in the club. This is a big club, the baddest mother club. Yeah.
With that, kind of like if and only if statement, your earlier example of why we need to like include like the immediate existential instance, wouldn't if you put in like for every single one FCC, FDD, you know, et cetera, wouldn't that require that for all x,
I see. So this is the word.
CC be in there, which would be inconsistent?
So let's go back to our little thought. So our worry was, what if we have in every single one of these negation guys?
Yeah.
And by this condition, that would entail that we also had for all x, not.
For all f, or for all x, yes.
Yeah, for all x, not fx. So then we'd have that, and now the thought is, well, doesn't that derivationally contradict? There is something that is a not fx. So could I have a set that had both of these that was S and D consistent?
Then you drop the not from the top, or like there shouldn't be a not in the top one.
Oh, well, so we're considering these. We're considering a set that is all these substitution instances, not F that AA. So here our P is not. We're basically like it's a not thing. So our substitution instances are not blah blah blah. So the for all is still on the outside. It's still everything is the P. We're considering
the reason that you had to immediately put it in was because if you didn't immediately put it in, you would have, you know, infinitely many instances of yes, f, x, x, right? So that would entail for all x, f, x, x, not f, x, x. Yeah.
I'm not sure if I'm tracking. Yeah, they would. I feel like I would love to talk about this later because I am still Yeah. Not totally sold on why we need. I mean, it totally works. Like having the condition works. We prove the thing was substantially complete. So we're at least good to go. You know, interesting question whether we need it. Yeah. All right. Let us proceed for the sake of time. So here's our membership clause for the existential. Existential P is in the club if and only if there's at least one constant C that has a substitution instance that is in the club. So both of these just motivated by the truth conditions, although again, purely syntactic, just about what is in the club or not. Cool. So we'll now have the stairway. Previously we had the door, now we have the stairway. That is our technique we use to prove the membership lemma. And so we're buying a lemma, we would say. So this is our stairway, which it is just the door. We just gave it a new name because now, you know, we're bigger and better things, right? So we're moving up in life. So if you can prove some sentence from a subset of a maximally QND consistent thing, then the thing you prove from the subset is in gamma star, is in the maximally QND thing. So our mnemonic is the subset proving P pushes P into heaven. All right. So you know we proved this. It's the same proof. So we will also. It's just another proof by negation introduction. But it's in the slides. So I have a feeling. Do I have a feeling? I don't know what comes next. I have a feeling that we've seen this shit before. Okay. Yeah. So we've seen cases A through E. And the next slide, I guess, has an example of one of them. So yeah, there's a feeling I get when I look to the west, and my spirit is crying for leaving, which is probably how we feel at this point in the class. Right? Get me out of here. All right, so this was a recap for case A. So you know, we proved case A, not P is in the club if and only if P is not in the club. The proof is exactly the same. We just change S and D to Q and D, and we use the stairway. Yeah, it's cool now. So we moved to case F, which is something new. So we're trying to prove everything as a P is in the club if and only if for each constant C, the given substitution instance, P of C for chi, where you replaced all the chi's and P with C's, is in the club. So we got to prove two directions, you know, the forwards and the backwards. And the forward one, we assume that this thing's in the club. And now we're like, okay, what could I prove from that? So we just note, all right, for any substitution instance, you could prove that substitution instance in QND by using universal elimination. Just be one application of universal elimination. This is so chill you don't have to write a derivation out. It's just like the case of or introduction was so chill you didn't have to write a derivation. You can just see, okay, yeah, that totally works. So by the stairway, you know, the fact that you can prove this thing from a subset of our superset, this thing has to be in the superset. It's got to be a gamma star. Cool. So in the backwards direction, we assume that this thing is not in gamma star. So here we're showing the contrapositive. So the contrapositive. So the backwards direction is assume that every substitution instance is in gamma star. Show that the universal is in gamma star. Contrapositive of that is assume the universal is not in gamma star. Show that for some constant C, the substitution instance wouldn't be in gamma star. So is the logic on that clear? All right, cool. So if this thing's not in gamma star, then by the membership clause A from the previous slide, the negation of this thing would be in gamma star. And so, oh, okay, here we go. So if I have no life, and derivation is on the next slide, or you can look at the book, page 573. So this is a non-trivial derivation to show that you can derive, there exists something that's not a P by assuming it's not the case that everything is a P. So this is just one of our De Morgan's laws for quantifiers. This is just quantifier conversion. The negation pushes through, converts this universal to an existential, and then the negation carries through to the P, negates that. So we proved at least one of the quantifier conversions on problem set 10. We didn't prove this one, probably because this one's in the book, and so you could cheat. We're all cheaters. You guys are stand-up intellectual citizens of this great nation. So yeah, but this is a few lines to show. So yeah, we're gonna do a poll. Who thinks that I have no life and that I put the derivation on the next slide? Raise your hand. This is not a blind poll. Okay, we got one. Anybody else? All right, who thinks that actually maybe this guy does have a life and he didn't put the derivation on the next slide? Wow, okay, that's some real confidence. All right, so we'll see. We'll stay tuned, right? So since this thing's essentially complete, if you could prove that there's something that's not a P, then there would be a substitution instance, not P, B for chi, member of gamma star. So yeah, this is, to go back to Henry's question, this is, thinking about this kind of thing seems really relevant for our putative counterexample to not having the way we build up existential completeness. And the key thing is just to note, the substitution instance of this existential has this thing not P. Similarly, this not P, this is an instance of a universal that is a for all x with a not after the thing. Cool. But anyway, so we're guaranteed to have this thing, and then again by the membership clause A, if this negation is in the club, then the substitution instance not in the club, that's what we're going to show. There's some B, so this substitution instance not in the club. Cool. Now we get to see, do I have a life or not? I have a life! Thank you for your faith in me. Cool. So now we have case G, membership lemma. I feel like for the sake of time, maybe we will press on and come back to this if we get through the rest. It's just another instance of membership lemma. This one is probably easier to think through, the existential. So we'll just fast forward again, show two directions, do some derivation stuff. Cool. All right, so then assuming we've completed the membership lemma, we go to construct this model, gamma star. All right, so this is the key. Smart choices are lazy choices. So we make some lazier choices than what the book does, and it just makes things easier. So the book constructs a model over the natural numbers. So they use that as the domain, the natural numbers. We're gonna note the following. A domain can be any set of objects, and symbols are objects. Words are labels on boxes, which is words are labels on boxes is a quote from this guy Alan Watts, who was like a spiritual literature person in like the 50s and like 60s, and there's a lot of really great Alan Watts lines in this band Starfucker. So Starfucker often samples Alan Watts, and so in the song that I linked for this week, this occurs in the background, which is kind of funny, it sounds really deep, right? Words are labels on boxes. Somebody might ask, what are words? You might say, they're labels on boxes. To go back to the philosophical investigations by our hero, or at least my hero, Wittgenstein, the book really starts out essentially in a scenario where you're using language to label drawers in a grocery store. And there's drawers that have, the word apples. And then you have numbers that count things. And so you really are thinking about words as just being labels on boxes. And really, that's what our predicates are. Our predicates are words for properties, property box. All right, so we're going to define Fracker M star, which is a domain, and an interpretation function as follows. So we're going to let the domain just be the set of constant symbols in QL prime. So the domain just is the names. And so QL prime is an extension of QL, and so it has all the QL constants as well. It has all the unprimed subscripted constants. In addition, it has the prime subscripted constants. So that's our domain. For the zero place predicates, which are the sentence letters B, we'll say the interpretation function assigns a sentence letter true if and only if it's in the club. So this condition is exactly what we did for the SL case. And there, all we had to do was handle sentence letters. Here we have to handle assigning constants as well. So, unsurprisingly, if we're going to let the domain be the constants, we will send each constant symbol, each name, to itself. So the interpretation function says, every constant is a name of itself. So we're basically saying, I am me. Me I am. That's what we're saying here. And then for the k-place predicates, I star of p, which is the extension of p, so these are just equivalent notations. This is the k-tuples, objects. This is a k-tuple of objects such that the predicate, now with these names, which are themselves the objects, it turns out in this case, is in gamma star. So this fourth condition is really just the generalization of this condition for the sentence letters. It's basically going to tell us that an atomic sentence is true in the model if and only if that atomic sentence is in the club, gamma star. Because these things are the QL atomic sentences. It's just predicates, a k-place predicate followed by constants. Those are the atomic sentences. Questions on anything on this slide? Definitions, words? Cool. All right. So this is our model, and now everything's going to work out. So just some things to note about our model, which we will appeal to below, sometimes implicitly. So note that every constant refers to a unique member of the domain, namely itself. And it's also the case that for the atomic guys, the atomic sentence A is true in the model if and only if it's in gamma star. So this comes from conditions 2 to 4. And by condition 3, another thing, every member of the domain is named by a constant, namely. So everything in the domain has a name itself. And so yeah, we'll occasionally use these guys. All right, so now we finally move to our induction. We've shown the membership thing, we have given a definition for our model, and now the goal is just to show that the model as defined does what we want it to do. The model as defined satisfies every sentence in gamma star. It is a model for gamma star. So we want to show that our model, as we just defined it, makes true everything in gamma star, such that, again, I'm using notation, M star, in some sense, entails gamma star. So it would suffice to show that for every sentence in gamma star, that sentence is true on the model, and that's what we'll say is clubbing, just like before. So sentence is true on the model if and only if it's in the club, then it's clubbing, and we just do induction. Because QL prime has a recursive structure, we basically extended our recursive structure from SL to QL prime by having two new clauses for the existential and the universal. So we just really have to handle the two quantifier cases. So for short, you could call these 7 things conquants, which I've heard some people say before, conquants. But we'll probably just call them operators, logical operators. So the base case is just to show that every QL prime sentence that has 0 logical operators is clubbing. So these just to show the atomics are clubbing. The atomics have 0 logical operators. They don't have any connectives, and they don't have any quantifiers. And then we'll assume, for induction hypothesis, every QL prime sentence that is anywhere from 1 to k operators is clubbing. It's in the club if and only if it's true in the model. And then we'll show that an arbitrary QL prime sentence that is k plus 1 many operators is clubbing. It's in the club if and only if it's true in the model. And if we've shown this, then we've shown the thing we wanted to, that every sentence is in the club if and only if it's true in the model. And so this would be a model for gamma star. Questions about this structure? Exactly the same as we did for SL, so that's nice. Cool. So base case, it's a little bit different because now we have to handle the predicates. So we just handle it by cases. If you have an arbitrary atomic, then it's either an atomic sentence letter, an SL thing, or it's this kind of n-place predicate with n many constants after it. And so if it's a sentence letter, then by part 2, we just said, well, okay, the sentence letter is true if only if the sentence letter is in the club. And so this if and only if handles to both directions. If it's of the form key C1 through Cn, then again, by definition, this thing is true in the model if and only, okay, well, so this is the definition of what it means for this thing to be true. What does it mean for an atomic sentence to be true? Atomic sentence is true in a model if and only if the objects that these constants name are in the extension of P. So C1D is the object that C1 names. And in our model, the object that C1 names just is C1. And we define in part 4 of our model construction, we said C1 through Cn, these things in our domain, this is in the extension of P if and only if P C1 through Cn is in gamma star. And so that, that's what we wanted to show. We wanted to show that this thing is true in the model if and only if it's in the club. And so we've done that. So key thing, just a little notational difference. Notice how there's no commas here, P1, C1 through Cn. This thing in the extension, this is an ordered, tuple, so it is commas. Cool. So this is a base case, a little bit more complicated than SL, but the same idea. We chose our model so that it would satisfy the base case. If it wouldn't, we would have chosen a different definition for the model, obviously, carry on our induction. Cool. So now we do these 7 cases. So 5 of them we have, basically done before. You just have to, for each of these 5 cases, technically, you'd have to replace the notion of true on a truth value assignment with the notion of true in a model. You just have to make that replacement. So I think, on this slide, I walk through how that works. If P is of the form not Q, you're just showing that this thing's clubbing, and Q, the smaller part, well, it has exactly K operator, so it's clubbing, and that just means Q is true on M if and only if it's in the club, and then you just argue from the truth conditions, just like we did in SL, that P is true on the model if and only if P is in the club. And so you're really just replacing like truth value assignment talk with true in the model talk. Cool. Otherwise, everything's exactly the same. So now we hit the new cases. So existential quantifier, P has the form of an existential. Now, one thing, a pitfall you might fall into is you might think, just like what we did here, we looked at P, not Q, and we said, oh, well, Q has K operators, and so it's clubbing by IH, and we could immediately apply the induction hypothesis. You would really screw up, potentially, if you said that Q is clubbing, because Q is not a sentence. Q is going to be something like not fx that has free variables. And something with free variables is not a sentence. And so only sentences can be clubbing. This is an exclusive club. It's not that exclusive, obviously, because it's infinitely large. But it does have some standards, okay? Not anything can get into the club. So we can't immediately apply the induction hypothesis to Q. So instead, we're going to use the membership lemma. So we remember from case G, so it's just this case G, and existentials in the club if and only if there's at least one constant C such that the substitution instance with that constant is in the club. And my pants have started vibrating, which is our 9-minute warning. So since I don't watch today, we set pants alarms. So we might actually finish this thing, or be like pretty close to it. So that's pretty cool. I mean, we'll at least do this case, and then it's like you basically seen the whole thing, right? So I'm kind of shocked, honestly, that we're like getting, especially with our little tangents and things that we've made it this far. Yeah. Wow. I mean, probably just it really is structurally exactly the same as what we did for SL. Just further reference. So cool. So we use the membership lemma. So in the forwards direction, we assume that the existential thing is true in the model, and we just have to show that the existential thing belongs to the club. It will belong to the club provided there's at least one substitution instance that is in the club. And so we really just ask, what does it mean for the existential to be true? And in the background, there's satisfaction semantics, but we say, screw that. Intuitively, what does it mean for the existential to be true? It means that there is at least one object in the domain that is a Q. That's what it means. Something is a Q is true, provided there's at least one object in the domain that is a Q. Avoiding variable assignments, we'll just say that object, whatever it is, satisfies the existential. So by the truth conditions for existential, there's some object R in the domain that satisfies Q. And so R is a name for object R, by the way we set up our model. So the substitution instance Q of R for chi is true in M star. Now this thing is a sentence. Q of R for chi is a sentence. There's no free variables in this. And Q of R for chi has less than k plus 1 connectives. So Q of R for chi is clubbing by the induction hypothesis. And we've just shown that it's true in the model. Since it's clubbing by the induction hypothesis, that means Q of R for chi has to be in the club. And that's basically what we want to show. So this thing has less than k plus 1 operators, it's clubbing, so by induction hypothesis, since it's true in the model, just argue that, it's in the club, and in the forward direction, we needed to show that the existential's in the club. By the membership lemma, the existential's in the club, provided there's at least one substitution instance in the club. Here's a substitution instance that's in the club, and so by the membership lemma, the existential's in the club. Questions on this argument? It's all straightforward, you just follow where logic takes you, we might say. So the backwards direction, P has the form, again, existential Q. We again use the same membership lemma. Now we're assuming that this thing's in the club, and we're trying to show it's true in the model. So that's the backwards direction. Assume the thing is in the club, show it's true in the model, or you can do the contrapositive, assume it's false in the model, show that it's not in the club. Either one would work. I think this way is easier to proceed directly, not assume contrapositive. So assuming this thing is in the club by the membership lemma, there's at least one substitution instance in the club for some constant C. This thing again is a sentence, so it's clubbing by the induction hypothesis. So given that it's in the club, it has to be true in the model. And so by induction hypothesis, this sentence Q of C for chi is true in the model. And now we notice, well, hey, C is a name for the object C. And so that object C satisfies Q in M star. Or again, when I say the object satisfies Q, this is shorthand for there is some variable assignment, blah, blah, blah. But this is the intuitive thing. And so this just means that the existential is true in the model. This is the truth condition for the existential to be true, is that there's some object that is a Q. Here is the object C that is a Q. And so by the truth conditions, this thing is true in the model, which is what we want to show. And so that's our case 7. So case 6 is super chill. And I feel like for the, we have 5 minutes. I think, we can do at least the part that I think I did. So again, watch out, Q is not a sentence. So now we use the membership lemma case F. Everything as a Q is in the club if and only if for each constant C, the substitution instance is in the club. In the forward direction, we assume that everything as a Q is true. In the model, we just want to show everything as a Q is in the club. And then, real fast, we're like, what does it mean for this thing to be true? It just means every object satisfies Q. And note that every substitution instance for every constant is true in M star, so every object is named by itself. And all of these substitution instances, they're less than k plus 1 connective, so they're clubbing. So since they're all true, they all belong to gamma star, which then by the membership lemma, if all these substitution instances are in gamma star, the universal is in gamma star. So, cool. And then reverse, which I say, do this yourself. Practice your brain. Cool. So then we've shown the induction. Anyone saying practice your brain probably has to practice their brain because that's not grammatical, you would say. So now, so upshots of our induction. So, we handled every case. So we've shown every sentence is clubbing. And so we've shown for all the QL prime sentences, that sentence is true in the model if and only if it's in the club. And so we've definitely constructed a QL prime model that makes true all these guys. And so we've shown this lemma, the existentially complete maximal consistency lemma. Given something like gamma star, there's a model that satisfies all the gamma star guys. So now we just have to finish, which I think is like one slide, the consistency lemma. Any Q and D consistent set, like our original gamma, is satisfiable in QL. Now we have to get back to QL we've been working in, QL prime. So we've shown that gamma star is satisfiable in QL prime. We have to show that the original, just Q and D consistent gamma is satisfiable in QL. So we need a QL model. This is what we're asking. Is there some QL model M such that M satisfies everything in gamma? So our hopes and dreams gamma is a subset of gamma star, and so definitely the model M star we constructed makes true everything in gamma in QL prime, but how do we get a QL model? And so our savior, we just note that the model M star is not just a QL model, it is also, sorry, it's not just a QL prime model for the gamma stars, it's also a QL model for gamma. A QL model for gamma, already on its own. So the language of QL is contained in QL prime, and so this M star model, it maps all the symbols of QL to objects in the domain. And that's all we required for a model in QL. We just required something that took all the symbols of QL and mapped them to objects in the domain. Satisfying some restrictions, it's the same restrictions. And so we've done that. This model M star does that. And so it is a QL model. And so we're done. There's nothing else really to say. If you don't like this way of thinking about it, you could explicitly define some QL model M with a new interpretation function I that's just a restriction of I star to the unprimed constants of QL. And then again, gamma would be satisfied now. So that's the whole thing. We did it. Thanks, guys. So we've proven this, and the upshots of this we'll talk about on Monday is compactness. So now for both SL and QL, we have compactness. That has lots of cool applications, which are on problem set 13. And we might talk about why it's called compactness and connections with like topology. So that stuff probably won't be on the final, I think. There could be some simple application of compactness on the final, but like the deep meaning of it probably would not be. Cool, and I have office hours now and on Friday at 1. Thank you for witnessing this. As well, we probably won't get to so yeah, we probably won't get to the last proof, which would be using topology. Is there a little thing, guy? I meant to grab another battery too. All right, I'll be gesticulating wildly because I think these are all double A's. Ooh, what about this guy? No, that's double A's. Well, if anybody has a AAA battery, let me know. So yeah, we probably won't get to the topological proof, but we'll probably do the other ones. And we'll talk about some applications of compactness to the various sizes of models you can get. And we'll basically show that anytime you can have a model for a theory, you can have a model of any size. So you got a finite model, you could have a countably infinite model. Once you have a countably infinite model, you can get a model of any arbitrary infinity for the thing. And if you had a model of any arbitrary size, you could always move it down to a countably infinite model. That will lead to something that kind of looks like a paradox called Skolm's paradox. We'll probably get this far, knock on wood, which basically is the issue is we have set theory, and in set theory you can prove that the power set of the natural numbers is uncountable. It's basically the size of the reals. And based on these results, you can have a model of set theory that has countably infinitely many things. So you basically have a countably infinite model that makes true the claim that the real numbers are uncountable. So in this model, the real numbers are represented by a countable object. That's kind of strange. So you might think something's gone terribly wrong. That's why it seems to be a paradox, but it's really not a paradox. So there's actually no problem. But it's still kind of weird. So, and the Skolem guy, he thought this was really weird. This is like 1930s stuff. He thought this was like, whoa. And he drew some radical conclusions from it that, you probably don't have to endorse. Cool, so that's pretty much the plan. We'll start off with super chill proof of compactness, which is in many ways aesthetic disaster of a proof that the book does, but it is, really easy to do once you've done the soundness and completeness results. So we proved soundness. So in quantifier logic, in our natural reduction system, we go from single turnstile to double turnstile. And we also proved completeness from double turnstile. We have to go to our single turnstile in our natural reduction system. And so once you have these two results, then you get a really easy proof of compactness. The problem, with proving compactness this way is you're relying on syntax. And in the statement of compactness, for essential logic, for instance, there is no mention of anything syntactic. It is a purely semantic statement. So it says, for any set gamma of SL sentences, that could be infinite, gamma is satisfiable if and only if every finite subset of gamma is satisfiable. So it's basically saying there is at least one truth value assignment that makes true everything in gamma, if and only if gamma is finitely satisfiable. Where finitely satisfiable means take any finite subset of the gamma guys, there will be a truth value assignment that makes that finite subset true. So one of these directions is totally trivial. If you know that gamma is satisfiable, then you know there's a truth value assignment that makes true everything in gamma. And so you know, of course, that guaranteed one truth value assignment would make true all the finite subsets of gamma. You'd have at least one truth value assignment that made true every single finite subset. So the non-trivial direction is from the finite to the possibly infinite. The non-trivial direction is assume that gamma is finitely satisfiable. Then, left to your own devices, you might think, oh, well, maybe for every finite subset, they have their own truth value assignment that makes true that finite subset. But what's the guarantee that there'll be one truth value assignment that makes everything in gamma true? What's the guarantee of that? So in general, you wouldn't have a guarantee, but in compact theory, like central logic, you do. So that's the result. So we can use our soundness and completeness proofs to give a proof of this. It's in some sense empiric, because we're using soundness, we're using our derivation system, and there's a ton of conventional choices that go into writing down a derivation system. We saw trees, we did natural deduction, we could have done an axiom system. So, for the natural deduction systems, there's 5 other ones that we could have used instead. So it's a huge element of conventionality with anything syntactic. But this is semantic. So here's our impure proof. So we're trying to prove this, and this direction is trivial if you assume that gamma is satisfiable. Then of course there's a TVA that makes sure everything in gamma, and so of course you satisfy every finite subset of the gamma guys. Is this clear? It's trivial part? Cool. So then, the work is in the non-trivial direction. We assume every finite subset is satisfiable. Now we want to show that there is one truth value assignment that makes everything true. Yeah, that's not it. Daniel, my little laser thing died today, so we're gesticulating wildly. Unless you have AAA battery, in which case, we're in business. I had a spare, but then what happened was I meant to get AAAs from the philosophy department, which has tons of supplies. And I got a thermometer and a hygrometer for my office, because my office seemed very uncomfortable, and I wanted to determine if that's true based in reality. So I used my spare AAA for my thermometer, and there we go. So, life choices. All right, so we're going to assume every finite subset is satisfiable. And so we'll just assume for contradiction that gamma is unsatisfiable. So we're going to assume that there isn't a truth value assignment that makes sure everything is gamma. And then we'll derive a contradiction from this. So basically, if you assume that gamma is unsatisfiable, then you can basically say, well, for any contradiction, it'll be the case that gamma semantically entails that contradiction. So, you could use P and not P, you could use anything, and now you're looking at this and you're like, well, hey, gamma semantically entails a contradiction. We have a completeness result, so there will be a derivation from gamma to a contradiction. And remember, derivations are finite, so then there'd be a finite subset of the gamma guys that derives a contradiction. And then you can just apply soundness whenever you have a single turnstile, you get a double turnstile. So from those finite guys, you would single turnstile contradiction, and then finite guy with double turnstile contradiction. But we assumed that all the finite guys were satisfiable. But if you semantically entailed a contradiction from these finite subset of gamma, that finite subset would have to be unsatisfiable. So that's our contradiction. So that's our impure proof of compactness using soundness and completeness. So that's probably what this shit says. Let's go. Yeah, gamma is unsatisfiable. So gamma semantically entails a contradiction. So we apply first completeness, convert this double turnstile to a single in SND, and then derivations are finite, and so we have this finite delta that single turnstile is a contradiction. And so for soundness, the finite delta semantically entails C, but C is unsatisfiable, so anytime you semantically entail an unsatisfiable thing, that set has to be unsatisfiable. Because the only way, this is saying there's no truth value assignment that makes true everything in delta and everything in C. Well, there's no truth value assignment that makes the C things true. And so there can't be a truth value assignment that makes the delta guys true. Cool. And so there's our contradiction, because we assumed all the delta guys are satisfiable. And so gamma must be satisfied. So that proves it. Any questions on our impure proof? Cool, so now we do it all over again. Oh wait, no, we have a moral. So if we ask, what does compactness tell us? And our question is, are there any arguments of sentential logic that have infinitely many premises where you actually need every single one of the infinite premises? A volunteer from our esteemed campus. What is the answer to this question? This question won't be on your final, but maybe it should, you know? Is this answer not obvious? Is there a thought that maybe the answer could be yes? Do you think so?
Well, only if you wanted to like draw infinitely many conclusions, but.
If you want to draw, yeah. So yeah, I guess implicit. Yeah, that's a good point. Implicit here, I was assuming there's a single conclusion. Yeah, so that's true. You were thinking of a better question than what I'm asking. So let's do an argument. So yeah, so I'm assuming single conclusion P. Assume that the gamma guys semantically entail P. Then the thing we can say about gamma union not P is what? What can we say about gamma union not P?
It's not satisfiable.
Not satisfiable, yeah. So definitely memorize that. This kind of thing, this claim that gamma union not P is unsatisfiable, this claim will, in many forms, be on the final, I think. Because if I put little proof problems on the final, a lot of the little proof problems will involve this inferential step from gamma double turnstile as a sentence to gamma union not P is unsatisfiable. So that's just like crucial proof move. So we would know this, and then we'd apply the contrapositive of compactness. And so, compactness is a biconditional. So one of the contrapositives of one of those biconditionals is if the gamma set is unsatisfiable, then there has to be at least one unsatisfiable finite subset. So there has to be some delta that's a subset of gamma union not P that's unsatisfiable. Is that clear? Any questions about that? Cool. So then it's easy to show that not only do we have this subset finite of the gamma union not P, we have specifically a subset gamma little f of our gamma guys such that gamma little f union not P is unsatisfied as well. So that's easy to show. And then this finite gamma f would semantically entail P. And so yeah, upshot is every Val argument only uses finitely many premises, so we never need infinitely many premises to derive any single conclusion. So, and this is something we showed on problem set 12. On that proof, we used the syntactic properties of soundness. Here we see if we had a purely semantic proof of compactness, right now we don't, but if we had a purely semantic proof of compactness, then we would have given a purely semantic argument for this claim, that you only ever need finitely many premises. So that's what we turn to next. Let's give it a purely semantic argument. for compactness. Yeah, this is our hope. If only we could prove compactness, purely semantically. Alright, so the idea here is really similar to how we proved completeness. And there's a sense in which really we should have just done this from the start. Here we are. So, whereas in completeness we proved that there's a maximally syntactically consistent set, so an SMD would be SMD consistent, we can have basically a semantic analog of this in terms of satisfiability. So this is our proof sketch. So we're going to start with some set gamma. We're going to assume that it's finitely satisfiable, and that just means we're going to assume that every subset of gamma, every finite subset of gamma is satisfiable. Then we're going to construct a superset gamma star, and using the superset, it's going to have certain semantic properties that allow us to define a truth value assignment that makes true everything in gamma star. And so just like in our proof of completeness, once we showed that there was a truth value assignment that made true everything in gamma star the superset, that of course entailed that everything in initial gamma was also satisfiable. And so we're basically doing the same thing, constructing one of these maximal like clubs that contains gamma. So yeah, and the key thing is that gamma star will have a membership lemma, and it'll be the same membership lemma, written in exactly the same way, now for a different kind of entity. Not a syntactic thing, but a semantic thing. And with the membership lemma, then the induction over SL, it's exactly the same. The induction over SL just relied on that membership lemma. And so you can do the same inductive argument. So the key thing really is just to think about what semantic properties would you use to define this kind of gamma star, and then how would you prove the membership lemma? That's basically the game. Cool. So again, we have this trivial direction for compactness. We're assumed that this possibly infinite set of SL gamma guys is satisfiable. Then of course there's a TD that makes sure everything in gamma. And maybe just so we hold it in our heads, maybe I should write on the board the statement of compactness, since it was slides, ages, and ages hence. All right, so compactness. SL. So this is for any SL set gamma. Gamma is satisfiable if and only if every finite subset is satisfiable. Alright. So one direction is trivial, and then the other direction is we assume that every finite subset is satisfiable, and our goal is to show that gamma is satisfiable. And of course, if gamma is finite, this is trivial, because then gamma itself would be one of its finite subsets. So it's only interesting if gamma is infinite. Then it's not a trivial thing to show. Although, of course, in the grand scheme of mathematics, maybe there is a sense in which this is pretty trivial. As we'll see, if we make it really deep in these slides, if you were going to make the set of atomic sentences in SL have arbitrary cardinality, so right now we're working with countably many SL sentences. If you allowed arbitrarily many SL atomic sentences, then you would have to use something like the axiom of choice to prove compactness. So you might think, oh, okay, maybe that is not totally trivial, because the axiom of choice is very controversial. And it leads to puzzles. And so there's something. And you can't prove the axiom of choice within set theory. So it's a real commitment mathematically. All right, so we're going to introduce an analog of our maximally consistent in S&D set, but now we'll just use semantic versions. So basically, the only thing we know about this gamma we're starting out with is that it's finitely satisfiable. So just like in our completeness proof, the thing we knew about gamma starting out was that it was syntactically consistent, and then we made a maximal thing that was syntactically consistent. Now we're going to make a maximal thing that's finitely satisfiable. So we're going to introduce the notion of a maximally finitely satisfiable set. We'll call it an MFS. And it'll have two properties. So of course it has to be itself finitely satisfiable. So every finite subset of gamma star is satisfiable. And then we have the second property, which we cook up basically to function like our door lemma. But we won't have a door lemma because the door lemma was syntactic. That was if you could prove in S and D something from a subset of gamma star, then the thing you proved was in gamma star. Now we're going to have this semantic analog, which is for every SL well-formed formula P, if gamma star union, that sentence P is finitely satisfiable, then P is a member of gamma star. So basically, whenever you're wondering, oh, is a sentence in gamma star, if you can argue that adding that sentence in preserves finite satisfiability, then the sentence is in gamma star. If you can argue that adding in the sentence would result in at least one finite subset that is not finitely satisfiable. I mean, yeah, so one finite subset is unsatisfiable. Then you get to say that the sentence P is not in a gamma star. So basically, P is not in gamma star if and only if gamma union P has an unsatisfiable finite subset. So our goal is just to show that any maximally finitely satisfiable set is satisfiable, namely there's a truth value assignment that makes everything in gamma star true. Then, provided we can construct this gamma star from our starting gamma that's finally satisfiable, we'll just piggyback on that truth value assignment. And the TBA that makes everything in gamma star true would make everything in gamma true. That would show gamma satisfiable. That's what we want to show. So then we've done Axe proof. Yeah, and so if we get a membership lemma, then we can do the same induction over SL that we did for completeness. Questions on the structure of this proof idea? I was all proud of myself when I thought of this over the weekend because I was gonna, this class I was gonna do, we were gonna go really into the topology stuff, and I was like, man, we're really gonna go from for all x to, for some x, because our book, is for all x, and this was gonna be, no, not for everybody. And then, thought of this thing, and we're like, whoa, this is so similar to what we did, before. And now the topology stuff is at the end of these slides, and we probably won't get there, so we're all saved in a way. But it's in there, if you want to look at it. But it's unlikely, I think, that we'll do the topology proof, but it's cool. Cool. So once we do the induction, we're not really going to do the induction, obviously, that would be super boring. Then we just have to show that we can construct this maximally finitely satisfiable gamma star from any finitely satisfiable gamma, because that's what we assume at the start. That would have a finitely satisfiable gamma. All right, so we got our bouncer again. We love our bouncers, big bouncer fans. So membership lemma, if P and Q are SL sentences, then we have clause A, which is the most important clause, used to prove all the other ones. The negation of P is in gamma star if and only if P is not in gamma star. So that's really the key thing to show. And then you get, for every other connective, something that mirrors the truth conditions for that connective. And because it mirrors the truth conditions, that's why it's convenient to use this lemma to do the induction over SL. Because when you do the induction over SL, the goal is to show that a sentence is in the club, the maximal club, if and only if it's true on a given truth value assignment. And you define the truth value assignment such that an atomic sentence is true if and only if the atomic sentence is in the club. And then based on this membership lemma, something like P and Q, where P and Q are both atomics, would be in the club if and only if the two atomics are in the club. If the two atomics are in the club, they've been assigned true by the way we're defining the truth value assignment. And so then by the truth conditions for conjunction, P and Q would have to be true. And then you get to say that, P and Q is in the club if only if P and Q is true in the club. All right, definitional. So we won't rely on a proof system. because we have this analog of the door into the definition of maximally finally satisfied sets. So really the thing to show is case A, that not P is in gamma star if and only if P is not in gamma star. So you want to use condition 2, and then you want to show this. So I'll say to you guys, it's possible I might ask you to prove this on the final. I would obviously define the relevant terms, but proving this could be a question on the final. So that's a heads up to you guys. I think about how to do this. You know, there's 2 directions to show. Assume that not P is in the club. Show that P is not in the club. That direction is definitely super easy. So assume not P is in gamma star, which we're assuming, you know, which is finally satisfiable, which is FS. Then, if P were in gamma star, then the subset not P comma P gamma star would be unsatisfiable. So that's a contradiction, because this is a finite subset and finite. So then you get to say, so P, so in this case, not in gamma star. So then the other direction is not as straightforward, but it's still hopefully clear. So we assume P is not in gamma star, then we apply this condition 2. Let's see. Yeah, okay, so I didn't restate condition 2. So here's condition 2. For every well-formed formula, if P is not in gamma star, then gamma star union P has an unsatisfiable finite subset. Okay, so assume P is not in gamma star, then gamma star union P, let's see, yeah, has an unsatisfiable finite subset. So, let's see. So we know that there's some, yeah, so basically there has to be some, okay, so we do some stuff and then be some delta union P unsatisfiable. So then we would have delta semantically entails not P. You know, I'm doing this partly because I had a worry this morning that maybe at this point the proof didn't work. In which case I'd have to redefine this condition 2, which I know I could do in a different way, but if this works, it's the most elegant. So you guys are going to help me figure out if this actually, if this goes through. So we're assuming that P is not in gamma star, and then the thing that we definitely get to say based on this condition 2 is that there's at least one unsatisfiable finite subset. And then the question is that good enough to argue that not P has to be in gamma star? Because I think when I was proving this on like a back of an envelope, and I think that this might have been screwed up, and I might have assumed something stronger than what I actually wrote in this condition to. Because we definitely, if we knew that gamma star union P was straight up unsatisfiable, then there'd be, then we'd be able to write something like, so, solely compact, so if we had, so gamma star union P unsatisfiable, then we would know that gamma double turnstile is not P. So then we would know that any true static assignment that makes true all the guys in gamma star would have to make true, not P, and so we would know that any true static assignment that makes true all the finite guys would have to make true, not P. And so we would know that for any of the finite guys, the finite guy union, P would be unsatisfiable, and then we could apply this condition. And so then not P would be in gamma star. But so we're basically saying what? So this thing's equivalent to P is in gamma star. Yeah, so we're basically saying not P is a member of gamma star if and only if gamma star union not P is finitely satisfiable. So not P is in gamma star if and only if gamma star union not P is finitely satisfiable. We assume that P is not in gamma star. Then we know that this thing has an unsatisfiable finite subset. So delta union P would be unsatisfiable for some finite thing delta. So then anytime we made the delta guys true, we'd have to make not P true. Which would basically be saying, at least for this delta, delta union not P would be satisfiable. But then the question is that true for every single delta not P? So maybe this doesn't actually work, in which case this question definitely will not be undefined. Because there is another way to set up 2 that 100% would work, but it just seems aesthetically worse, which is you could instead define 2 as basically define 2 as condition A of the membership lemma. Say that any sentence not P is in this superset gamma star if and only if P is not in gamma star. Then you get this condition A for free, and it's really the condition A that you use to prove the other membership lemma guys. So yeah, I guess I'll think about whether there's a way to save this proof or whether I screwed up when I was, trying to make something aesthetically more pleasing. So yeah, I'll say probably case A will not be on the final version of this possible screw up. So, all right, but so if you had case A, then it's easy to do the other cases, and you could build case A into this gamma star thing. So at least in spirit, we save the proof is secure. So once you had case A, then you would just appeal to the fact that gamma is finally satisfiable to prove the other stuff. Cool. So it's basically like you assume that a given membership case fails. They're all 2 directions. You assume one fails. You apply case A. Then you would show that you have an unsatisfiable finite subset, but that would contradict the condition that we're building something that is finally satisfiable. Cool. So imagine we've proven that. Then we would define this true static assignment I star that makes true every atomic sentence in gamma star, and we would do induction over SL. And so that's just like what we did in the completeness proof. And so that part would go through. And so really the only thing to do is to build this gamma star. And the way I set it up, everything is completely analogous to what we did. Now it's possible we're going to have to modify something. So we enumerate our SL sentences, so everyone has a number. And then when you consider a sentence, if you can add it to gamma while preserving finite satisfiability, you do. And if not, then you don't add it. So otherwise, you just stay put. Now, if we have to build in the membership limit of this, we would just modify this construction clause to be something like you either, at every step, you either add a sentence or you add its negation. So as you consider the sentences, if that sentence would preserve finite satisfiability, you add it. If that sentence wouldn't preserve finite satisfiability, then you add its negation. So that would be the modified construction. And so that, would definitely get us the case A of the membership lemma if we couldn't get it through this way. So it would work ultimately. So we have gamma star be a union of all these gamma k's, just like it was in our completeness proof. Cool. And so yeah, so at this point, it would suffice to prove that gamma star is maximally finally satisfiable, and you're basically like, we've just constructed it to be maximally finally satisfiable. It has to be finally satisfiable, because if it weren't, there'd be some earlier stage gamma k that was finally unsatisfiable, but that contradicts how we're defining the gamma k guys. And it has to be maximal, because if there were some sentence that could be added to it while preserving finite satisfiability, then it would have been added at its enumeration stage. So if Q is not in gamma star, it must be that gamma star union Q is not finitely satisfiable. So maybe this is good, right? Because we're basically, gamma star union P would have an unsatisfiable finite subset. So in gamma star union P, would it be, it wouldn't be finite set, but we need to show that, so it's like what we need to show is, I need to show that gamma star union not P is finitely satisfiable. So you basically need to argue that for every single finite subset of the gamma guys, adding a not P to that finite subset, there'd be some truth value assignment that makes it true. All right, well, let me know if you figure that out. I'll probably think about this after class. All right, so once we've done that, then we're totally done, because we've shown that this gamma star got to be constructed is maximally finally satisfiable. We argued that any maximally finally satisfiable set is satisfiable, and our initial gamma that we assumed is finally satisfiable is a subset of this maximally finally satisfiable set. And so it would be satisfiable. So we can get questions about this, which is a pure proof of compactness. Cool. All right, so now we're going to extend this stuff to first order logic. So quantifier logic is our exemplar of a first order theory in this class. I'll make sure you guys are in a good pile. And so basically, for quantifier logic, we have a compactness result, which is completely parallel to syntential logic. So for any set gamma of QL sentences, gamma is satisfiable if and only if every finite subset is satisfiable. So we're basically saying for all of the deltas, the finite guys, there is some QL model that makes true every sentence in delta. So here, this is another, we're throwing red meat today. So another very plausible final exam question would be, we went over an impure proof of compactness for SL. You could do basically the same impure proof for quantifier logic, where you apply soundness and completeness. I might ask you guys to do that as a sanity check, to make sure that some people I think are phoning it in on this class. I mean, it's a really easy question. You just run through the same argument that we just did. But I might ask it just to make sure, you gotta keep minds right. So make sure that you, if you're, when you're studying, make sure that you can do an impure proof of this compactness result using soundness and completeness. So converting, double turnstile to single turnstile and single turnstile to double turnstile. So I'm not going to ask you guys to do a pure proof, but we could do one for this. It'd be exactly analogous to what we just were doing, and we just have to build in existential completeness. And then just like we got a membership lemma in our completeness proof of quantifier logic, we would get a membership lemma for this kind of maximally finally satisfiable and existentially complete superset, and then we'd be able to do an induction, get a truth value assignment that satisfies everything in gamma star, which would have been constructed to contain gamma, and so we would prove compactness without using the soundness result that way as well. Cool. So what we'll do instead is we'll talk about arbitrary first order languages. So I think when I updated the problem set, I gave some definition like this will be a little bit more precise, and that just means pedantic, because we love pedantry. So we have some set of well-formed formula. We have some recursion clause, exactly like what we gave for quantifier logic, determining what is an expression that's not just like, bizarre, like we're not allowing like left parenthesis, right parenthesis, right parenthesis, right parenthesis. That's not a well-formed formula. The things in the language, the language is just symbols. That's what languages are. Languages are just symbols. So we have variables, and all the first-order languages have variables. They have operators, which are our 5 sentential connectives, and our 2 quantifiers for all there exists. We have the left and right parentheses, and then we get these things that could vary from one first-order language to another. So the different FOLs, they can have different constants, and they can have different predicates. And so the predicates can be 0 place, which are the SL atomics, 1 place, like PA, capital P, lowercase a, 2 place, etc. And you kind of imagine each predicate comes along implicitly with information about how many things it can take in, how many slots it has. So in principle, one could, build that in more precisely, but we're comfortable with mathematical objects, so why shouldn't we be comfortable with invisible labels? What is a mathematical object but an invisible label? And you get function symbols. And so functions are things that they take a name or a term and they spit out another name or a term. And you interpret them via the interpretation function as basically just mapping the domain to the domain. So the domain is objects. So if your domain was natural numbers, a function would just be a map on the natural numbers to the natural numbers. So it'd be like adding, so addition is a function. Cool. So the different FOLs can differ in the last 3 things, the names, the predicates, and the functions. All right. So we'll let script L be some arbitrary first-order language. So counted guys are 0 place ones. Oh yeah, so this is just what a model is. So we went over this maybe like a week ago or something, so just to refresh. A model, Fractor M, has a domain and an interpretation function. The domain has some objects, has to have at least one object. Can't just be the empty set. And the interpretation map I, it just figures out, what's the vocabulary, the symbol stuff going to stand for in terms of objects and properties. So for the constants, they get mapped to objects, and the object something's mapped to is called referent. And for the predicates, they get mapped to these ordered k-tuples, which are the extension of the property. Cool. And then the atomic guys are mapped to true or false, just like in central Washington. All right. Any questions about this stuff so far? It's really, I'll just throw it in there. For the grand show. So we didn't really talk in great detail about extending our deduction system to identity, but we could have. So we could have extended natural deduction to have 2 more rules to handle identity. It would just lead to, honestly, probably more confusion about solving problems on the final of natural deduction. So that's why we didn't do it, because it's like, just anytime you add in new rules, the possibility for making mistakes just, skyrockets. So I think you guys learned enough arbitrary syntax in your rule system. You don't need to know more. I don't think I communicate anything more to corporate America by testing you on QND with identity versus QND. So, corporate America is happy as things stand. But if we had done that, then we could have extended our soundness and completeness proofs. And the soundness proof would be basically the same, just show these 2 new rules are truth preserving. And in the completeness proof, the thing you have to do is basically, you have to talk about equivalence classes of terms that refer to the same object. So remember, the trick we did was we constructed a domain that was just all of the constants. That was our domain. Now, with identity, you might have constants that refer to the same object. And so your domain should really be equivalence classes of co-referring objects. So a little wrinkle, but you know, it all works out. And then adding functions doesn't really change anything at all. So then when we went, you know, when we go to do a completeness proof, just like when we were proving completeness for QL, we just added in some symbol that wasn't in QL, we added in a prime. And the prime symbol let us have countable infinity of constants. And we use that to guarantee that our thing could be existentially complete. We guarantee that we could always introduce a substitution instance with a new name, a name that had never occurred before in our possibly infinite gamma. So for any first order logic, you could do the same kind of proof. That's why, you know, it's good to do that proof because it generalizes well. And you know, there's always going to be some symbol that's not in your first order language. You know, we can always just make up new symbols, right? Even if it's kind of a funny thing to think. Could you have a first order language that, by definition, included every symbol that could be written down? I don't know. That would spoil this proof. So it's kind of you really start to think like, what's going on? What is the essence of mathematics? And when you run into stuff like this, you might think part of the essence of mathematics is we just get to say, oh yeah, this is a new symbol that's never been written down before. We have like unlimited, creative potential in thinking about stuff and dictating rules for it. And does that mean that there really are infinities, or is this more a function of this controlled practice we have, the norms we have governing how we talk about symbols? And it might be that the norms we have governing talk of symbols makes total sense of infinite quantities and uncountable quantities, even if the world itself is finite. Possibly. So if something like that is not true, then if we make it far enough in these slides, we'll see there's real problems for saying that there's finitely many things in the world. And so if you were a hardcore finitist and you thought, yeah, I'm only committed to finite many objects, then if you're going to use the riches of what we've created in this class, you would be contradicting yourself because we're not able to say in these first order languages that there are finitely many things. It's not possible. At least not if you want certain nice properties, like compactness. Or even you just want soundness and completeness, which you might think, if you're going to have any derivation system at all, you don't want it to be sound, at least sound, right? Hopefully complete. Okay, so we could construct another one of these gamma stars. We use our equivalence classes of the co-referring constants, since now some of these things might name the same objects. Cool. And then if we use the axiom of choice, then we can handle languages that have uncountably many predicates or constants. If we don't use axiom of choice, then we're only handling countably many predicates or constants. So that's what implicitly we've been doing all along. So now we're like, imagine we did that. Imagine we proved soundness and completeness for first order logics. Then we could again give an inferior proof of compactness. And so we'd be able to say for any first order logic L, if you have a set of L sentences that's satisfiable, then every finite subset of them is satisfiable, and vice versa. If every finite subset of the L sentences is satisfiable, then the whole set gamma is satisfiable. So basically, first order logic in all of its forms is compact. Like, yay, that's cool. So we could do inferior proof of soundness and completeness. We could again generalize our pure proof, modulo making sure that we fixed it. There's at least one way to get it to work. So. Or we could modify the topological proof at the end of these slides and use stuff from topology. Cool. All right, so now we get some applications of compactness, which lead to some puzzles about infinities. So these are called the Lowenheim-Skolem theorems. And we have a downwards direction and an upwards direction. So I really should say we have a downwards direction and an upwards direction. So just as a reminder, we're saying that a model is infinite. This is really shorthand for saying the domain of that model is infinite. Similarly, if you say a model is finite, that is shorthand for saying the cardinality of the domain of the model is finite. So the cardinality of the domain of the model could be finite, could be countably infinite, or it could be uncountable. Various infinite sizes. So that's just terminology. Then we can state the downward Lowenheim-Stollen theorem, which says, let gamma be some set of sentences L from our first order language L, if gamma is satisfiable in an infinite model, where this just means, so for an infinite model, this could be an uncountably infinite model, this could be arbitrary infinite size, then it's satisfiable in some countably infinite model. So the downward Lowenheim-Stollen basically says, if I give you, a set of sentences that's true in some model of some arbitrary infinity, you could always have a countably infinite model. So, and you might think this is kind of surprising, because why couldn't it be the case that the only way to make true every sentence in a first order language is to rely on a domain that's uncountably infinite? And this shows you that that's never the case. That what you could do with an uncountable infinity, you could always do with a countable infinity. That's cool. Cool. So yeah, so we can always descend from an infinite model to a countably infinite model. We can go from heaven back down to earth, we might say. So we could give two proofs of these. So one would be to piggyback on our completeness proof, and then the other idea would be to use compactness and the satisfiability lemma for our maximally finally satisfiable sets. So I think I might have put both in here, because I think initially I gave the impure one, and then I was like, well, that's bullshit, because again, the Lowenheim-Stollen theorem doesn't say anything about syntax. Shouldn't we be able to do this without needing a soundness result? And so we could just use compactness instead. Okay, so this looks like our impure direction. So remember we had a consistency lemma from our completeness proof, which was the converse of this statement. So our consistency lemma there was the statement, if you have some set that's syntactically consistent, then it's satisfiable. Because we went from syntactic consistency to construct some superset gamma star that was maximally syntactically consistent, and then we showed it was satisfiable. And then we were like, oh, okay, our initial gamma, which was syntactically consistent, is also satisfiable. This is the converse. So this says, if some set gamma is satisfiable, then gamma is syntactically consistent. Assuming that we've shown some proof system L and D, natural reduction system for language L, assuming we've shown that is sound. So allegedly this is a good exercise. And again, this is, red meat. This plausibly could be on the final. And this one I'm very confident works, unlike our earlier quasi-disaster. So this is, to do this is very straightforward. You would just, we're starting out assuming that L is satisfiable. So if this doesn't work, then I quit my job, right? So, okay, but hey, if I quit my job, it's okay, because we made it to the end of the semester, right? So you can't, I still got all the money. Money's in the bank. So honestly, right now, what I'm doing for December is you can have these things called supplemental 401ks or 403bs. So I have a supplemental Roth. I'm funneling my entire paycheck into a supplemental Roth account. So we're saved for retirement. That's my advice to you guys. As soon as you can, as soon as you're fiscally secure enough, start saving for retirement, because the compound interest curves are just they're insane. So it's like rationally good. I might mention this at the final or on the review session. It's really, I think, the number one piece of the life advice that I could give any of you is as soon as you're able to, start saving for retirement. So you will thank yourself later on. All right, so we assume that gamma is satisfiable. We're basically assuming there's some truth value sound that can make everything in gamma true. Now assume for contradiction that gamma is syntactically inconsistent. So for reductio, is syntactically inconsistent. And so really the only thing you have to remember is what does it mean to be syntactically consistent? This is why it's a good exam question. Checks people, really learn what this means. What does it mean to be syntactically inconsistent?
You derive a contradiction.
Yeah, derive a contradiction. So then, there exists an R and a not R such that in our mass reduction system, whatever it is, so we call it L and D. So in L and D, gamma can derive R, and gamma can single turnstile not R. Now we're assuming that we've shown our proof system is sound, and so we can convert these to double turnstiles, so that by soundness, we have gamma semantically entails R. Oh yeah, well really the thing we should say, so remember derivations are always finite, so this means there's finite guys, delta, that does this. So by soundness, so really I should put a little asterisk in here that we can get to the finite guys. Derivations are finite. Now assuming we said that, which is something that you'll write on your final, we have this delta finite such that delta not only single turnstiles are, but double turnstiles are, and delta double turnstiles not are. So then to finish the proof, you basically note the only way that a sentence can semantically entail, the only way a set of sentences can semantically entail R and not R, basically contradiction, is that delta would have to be unsatisfiable. So delta would be a finite subset that's unsatisfiable, so that contradicts our assumption that gamma is satisfiable. Because we assume there's a truth value assignment that makes true everything in gamma, and so that truth value assignment has to make the delta guy true. So, yeah. I mean, honestly, it seems like, we probably don't even have to appeal to the finite delta. You could just say this, do double turnstile, and say, oh, then gamma has to be unsatisfiable. We assume gamma is satisfiable. So, cool. Any questions on this? Cool. So remember that. I think that one totally works. That seems like a good exam question. All right. So then we would use our consistency lemma that we did show for completeness, and we'd be like, okay, anything that was syntactically consistent and existentially, given that it's syntactically consistent, we can make the superset, the gamma star that's maximally consistent, actually complete, show that's satisfiable. We constructed, this is the key point. In our proof had a cool property, which is the model we constructed was countably infinite. We added in a countable infinity of new constant symbols, but that still kept the domain countably infinite. So basically, in our completeness proof, if there's one thing morally that we can say we did well in doing the completeness proof, which otherwise maybe seems to be like this giant exercise in tedium, we constructed it so that the model is countably infinite, and in virtue of that, we get this proof of the downward Lowenheim-Scullin theorem. So that is a cool, surprise inside. So since the superset had a countable infinite model, remember we argued that that thing is itself a model for the original set of sentences. We were in some language L plus, or L prime, where we added in these constants, but then you can restrict that to an L model for your initial sentence, and that would be a countably infinite model for the gamma guys. So basically, our proof of downward Lowenheim-Scullin is just, we showed how to construct a countably infinite model for any set of sentences that is satisfiable. And all we assumed in the assumption phase of downward Lowenheim-Scullin is that it's satisfiable. It's basically all, If it were satisfiable on a finite model, of course, you could always extend a finite model to an infinite model. Cool. Questions on this? All right. So, okay. Here proof. Let's see. How are we doing with that? I think this is probably a sketch. Let's see. So, yeah. So we would assume gamma is satisfied in the model, okay? So it's, okay, so then it's satisfiable, so by the compactness theorem, it has to be finally satisfiable. So we would apply compactness, and then what we would do is just modify the construction we were doing earlier, where we had the maximally finally satisfiable thing, throw in existential completeness, get the membership lemma for that thing, and then show this gamma star is satisfiable. And at this point, the proof would basically be exactly what we just did in the completeness proof. We would be constructing a countably infinite model for this superset gamma star. So rather than a consistency lemma, we have this satisfiability lemma. Given a gamma star, that is maximally finally satisfied and existentially complete, such a gamma star is satisfiable. And we would construct a countably infinite model in a language L+, where you've added in some new symbol to get countably infinitely many unused constants. And then we would basically argue, okay, well, the L+ model for gamma star is also giving you a countably infinite L model for your initial set gamma. And so again, we would have shown that gamma has a countably infinite model, just assuming that gamma is satisfiable. Okay?
I guess I'm a little confused, and this might just be like a math thing on my part, but how would you construct an uncountably infinite L model when it only has like a countably infinite like set of symbols?
Oh, okay. Yeah. So basically, it's there's a disconnect between the cardinality of the language and the cardinality of the domain, where what a model is doing is basically taking, you have symbols in your language L, and the interpretation function is mapping these to some domain of objects, D. And the only thing you need for the interpretation function I to be well defined is that it's a function on the symbol. So it just has to be the case that for every symbol in L, I interprets it. And so the size of D could be anything. I mean, it would be the case if D, is arbitrarily big, there might be tons of stuff in D that's never named. So it might be the case that, you have countably infinite many names. Those names name countably infinite many things here, and then there's an uncountable set of objects in D that are just never named.
Okay.
And that would be fine. Qua the model. So, it's a good question. That these two things are, they really can come apart in this way. Yeah. So, but it's like one thing that's maybe a little surprising about this kind of thing is like, you might have thought that there could be a scenario where the only way to make true everything stateable in your language was to, I give you a model that seemingly relies on this thing having arbitrary large size, relies on the domain being uncountably infinite. That's kind of how it seems to be like for the real numbers. Like, we prove in ZFC, in set theory, that the real numbers are uncountable. It seems like I'm relying on the uncountability of the actual real numbers to ground that statement. And then it's kind of weird to be like, actually, no, the same set of statements about the real numbers could be true in a model whose domain is countably infinite. That's kind of strange. Yeah.
But then when we're constructing the maximal set for quantifier logic, wasn't one of the things that if you have any for all x, then every instance of the domain needs to be also in that set, in the maximum set. So that need an uncountably infinite.
That's it. So I think maybe so again the weird disconnect that's going on is so we're saying something like for all xp is in gamma star if and only if every p of C for x is in gamma star. Now, this might make you think of the objects, because we use the same notation when we talk about the variable assignments. And the variable assignments are definitely about the objects. But this thing is actually just a sentence in your language L. So the condition is still just in terms of the sentences. We're basically saying the sentence for all xp is in gamma star if and only if every substitution instance of that sentence is in gamma star. These substitution instances arise just from our countably infinitely many constants. So again, there could be over in domain land an uncountable infinity of objects that aren't named by any constant. That's another good question. Yeah. Cool. So yeah, weird shit, right? All right, so then we have this upward guy, which may, the upward guy might not seem as strange. It's like, yeah, if you had a countable model, of course, yeah, why couldn't you, basically for the reasons we've been talking about, the domain can just be kind of, doing its own thing. Why couldn't you just always extend your countable model to an uncountable model? That's basically what the upward low and high lets you say. So, so if you have gamma that's satisfiable in an infinite model, where this, could be any cardinality, then it would also be satisfiable in models that are arbitrarily larger than this thing. So even if you start with an uncountable infinity, you could have, any larger uncountable infinity. So like just keep taking power sets. Power set would always give you a larger cardinality. So I gave a proof sketch, but maybe we'll just bail on the whole proof sketch. Blah 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 blah. Blah 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 blah. Yeah, I feel like we're basically just adding in an uncountable set of constants. So the game plan is like to expand the domain, you just throw in uncountably many constants, and you can always do that. Just throw in an uncountable set that contains the initial set of constants that you started with. Then you'll end up with something bigger. Cool. All right, so now we hit this paradox. It's in scare quotes because is this really paradox? And I checked, and this paradox I don't think comes up in the paradox and infinity class next semester. So I'm not spoiling anything in that class. I think right now there's one student enrolled in this class who's pre-registered for that class. So you don't want to spoil things, right? So gotta check that shit. All right, so to set this paradox up, we'll say a little bit about ZFC. So Zermelo-Fraenkel set theory with the axiom of choice. So this is just some other first-order language that we could name, script ZFC language. It has an identity symbol, and it has a two-place predicate for set membership, where just like identity, we abuse notation, and because identity, we write things like x equals y. Technically, identity is a predicate, and so it should be out to the left, and we should be writing equals xy, to keep our predicate notation like PAB. So we do the same thing with the membership sign. We write things like x is a member of y, where this is really just a two-place relationship between x and y. So it's an abusive notation. And so we interpret the objects as sets, when we do the interpretation function stuff. And then it's just a list of axioms. So there's like 10 or 11 axioms. I wrote a couple of them just to give a flavor. So one axiom you can see, it's stated in a first-order language. We have our quantifiers. We say something like, there is an x such that for all y is not in that thing. So we're basically saying there is an empty set. The empty set is a thing such that for everything else in your domain, those things are not in the x. That's what the empty set is. So this is kind of cool. You might think, why do we care about quantifier logic? Well, with quantifier logic, we can give a rigorous foundations for mathematics. That's a payoff if there ever was one, right? So another axiom, for all x, for all y, for all z, z is in x if and only if z is in y. If that's true, then x is equal to y. So we're basically saying, if it's the case that everything that's in set x is everything that's in set y, and vice versa, then the sets x and y are the same set. So we're basically saying two sets are the same if they agree on their members. So that's the extensions of the sets are the same, then they are the same set. Axiom extensionality. So we have an axiom of choice, which I did not write in our quantifier logic, but so this one, the devious one, says if you have some set x whose members are all non-empty sets, that's one condition. So all the members of x are non-empty, and also no two members of x share a member. So x is some set of sets, and all of those subsets never have a member in common. The axiom of choice says you can pick an element from each of those subsets of x. So you have all the subsets of x, there could be uncountably infinite subsets of x. The axiom of choice says you can pick an element from each one of those, take those ones you've picked, and form a new set. A set y that has exactly one element of each of these disjoint subsets of x, and nothing else. So that's it. It sounds really harmless. And then it leads to all these bizarre puzzles. And it's like, it's logically equivalent to other statements that sound even less harmless than the axiom of choice. And they're equivalent, so they lead to the same puzzles. So it's kind of strange. Yeah. But this is why it was a real achievement to set up set theory in a way that is, as far as we know, genuinely paradox-free. Because the initial attempts to set it up ran into all kinds of paradoxes because of how bizarre infinities are. So to end up with this edifice that, as far as anybody knows, is consistent, that's a real accomplishment. You can't prove within ZFC that it's consistent. That's a bummer. That's the second incompleteness theorem. Shows that within ZFC you can't prove that ZFC is consistent. So there is a sense in which, you think about like the evidence for science is largely inductive, right? We have inductive evidence that the standard model of particle physics will keep saving the phenomena at the Large Hadron Collider. You might have thought that in mathematics we don't really need inductive evidence. This is at least one instance where we're basically riding on confidence. We're riding on confidence that in the last 100 years or so, nobody has derived a contradiction in set theory. That is, part of our evidence for set theory, and thus, most of the rest of mathematics being consistent. Thanks, induction. And we can't have a logic for induction. People tried that and they failed. So that was another thing that we could have talked about. All right, so then we hit this paradox. So if there's any models for Zermelo-Frankel set theory of choice, then it has some countable model. So if you had an infinite model, you could apply the downward Lowenheim-Stolem, you could get to a countably infinite model. Of course, if you had a finite model, that would already be countable. Yeah. So we definitely have, if there are any models, so basically if ZFC is consistent, which we are, hoping, praying that ZFC is consistent, then that would mean that everything's satisfiable. That would mean it has a model. So here we're just saying, well, if it is consistent, then if it has a model, it has to be a countable model by the downward Lowenheim-Stolem. So within ZFC, we can prove that there are uncountable sets, such as the power set of the natural numbers has the same cardinality as the reals. So the set of all subsets of the naturals is uncountable. And so this is our paradox. How can a countably infinite model make true the claim that there are uncountable sets? Thoughts on the paradox? Does it seem genuinely paradoxical? I mean, we have, green and pink colors, and so those seem like they're conflicting with each other, right? All right, so we'll give the resolution of the paradox. Maybe you'll still be dissatisfied. I think Skolem was still dissatisfied, even with this resolution. He still thought it showed that something's messed up. So suppose ZFC is consistent and so it's satisfiable, so that's a countable model. Then this thing would make true everything in ZFC, so in particular make true all the axioms, and it would make true everything the axioms logically entail. And one of the things that the axioms entail, because there's a power set axiom, So the axioms entail that the power set of the naturals is uncountable. So note this set as 2 to the n. Those are power set of the naturals, basically the real numbers. So what claim U is saying, U is just a sentence in ZFC. That is true. And U is basically saying there is an injection, but there's not a bijection from the naturals to its power set. And our model, M, which we're taking for granted exists, makes true this claim U. So M, we're assuming, is a countable model. And so within this model, we're definitely representing the sets n and 2 to the n as countable. Because M, if it's a countable model, only has countably many objects over here in its domain. And so the representation in the domain of the stuff in L, the L sentences, has to be countable. There's only countably many objects to work with in M's domain. So this is the weird part. As represented in the domain, whatever objects are standing for the naturals and whatever objects are standing for the reals to the n, there is a bijection over here. In the domain, there's a bijection between n to the n. And we can say this in meta language, I just did. In the meta language, I just said and verbally proved that there is a bijection between the natural numbers and the real numbers. But, and this is the key thing, this bijection that we just talked about, it's not itself an object in n. It's not an m. So it's not like we're saying that ZFC is making this further claim that the cardinality of the naturals is the same as the cardinality of the reals. ZFC isn't saying that. We can say in this model that there is a bijection between the objects representing stuff. But ZFC doesn't see that. The model doesn't see that. That claim is not true in the model. And so as far as the model is concerned, yeah, 2 to the n is uncountable. And that, that was all we asked of ZFC, was to make true all the claims that logically follow from the axioms. And this model does. And so there's no problem at all. Do people feel at ease, or or is this still unnerving? As far as anything about mathematics is unnerving, right? It's like we're not, we really gives a shit. We're gonna go home. We're gonna watch football, eat popcorn. We're not gonna think about this again. Cool. All right, we have 3 minutes. And so in 3 minutes, the thing that I can say very quickly, I think, is this issue that arose on problem set 13, where we showed that you basically can't have a sentence that says there's finitely many things. So in 3 different problems we proved, you can't say with a sentence. Now you might think, I really want to be able to say there's finitely many things. Is there some other way to do it? And if not through sentences, the only other thing obviously you might use would be operators. So the thought is, what if we introduce a finitely many quantifier to first-order logic? So flip the F, we'll call this a finitely many quantifier, and the way we'll define it is that, so P is a formula where X does not appear down, and this thing's a well-formed formula, so you have to extend satisfiability semantics, and you say fxp is true if and only if there are finitely many P objects in the domain. And so the question is, what would it take the modifier derivation system to make this thing sound incomplete for finitely many quantifier logic? So quantifier logic with finitely many operator, what would it take to make this, a sound incomplete derivation system? That's the question. Any thoughts on this?
We need to add this to the membership level.
Yeah, we would need a membership loan, yeah. But really it's a trick question. That's a good answer, but really it's a trick question. Because the claim, you couldn't do it. And so here's why. So imagine for contradiction that you did have a sound incomplete quantifier logic with this operator, finitely many. Then, by our impure proof for compactness, this thing would have to be compact. But you can show that quantifier logic with this operator is not compact. And so since it's not compact, there can't be a derivation system that's sound complete for it. And the proof that it can't be compact is basically the same as what was on the problem set. F, infinite F. So this is our finite hopes and finite dreams dashed upon infinitely many rocks. So, assume that this thing, we're sounding complete, we could show it's compact, see the earlier slides. But this entailment relation is not compact. So consider this sentence, which basically says, fx, x equals x. There are finally many things that equal themselves. That's true if and only if there are finally many things that remain, that everything's identical to itself, nothing else. Then you consider this set, which is just like what we have on the problem set, this sentence f, and these L1s that say, LK says there's at least k things. This set x is finally satisfiable, but it's not satisfiable. There's no model that makes true x. Because any model that made true all of the L's would have to be infinite, but then it couldn't make true the sentence f, which is only true in a finite model. So there's no way to satisfy x, but it is finally satisfiable. Just take an arbitrarily large k. It'll make true all the smaller LKs and f. So basically this set x shows you that we have a compactness violation. So this logic can't be compact, and so there can't be a sound complete derivation system. So our hopes and dreams with dash. Yeah, Henry?
For finite satisfiability, do the finite subsets have to be in the order in which you made them? Like, would not like L5 in and of itself be a subset of X? And L5 says there are at least 5 things,
Mm-hmm.
and that wouldn't be.
No, so that would be satisfiable. Yeah, to say that there's, so you could make true any subset of the L's or the L's with an F that's finite will have the largest LK. They'll have an LK of the largest index, and then just pick a domain that's at least that big, it'll make true that finite subset. So that's the sense in which this set X is finally satisfiable. So if the logic were compact, then the set X would have to be satisfiable. But basically, the set X can't be satisfiable because the set X could only be true in an infinite model. An infinite model wouldn't make the sentence F true because F says there's finally many things. So we have, a contradiction. So it's just, it's kind of a bummer, right? You might have thought it wouldn't be so hard to say that there's finally many things, especially if you think that they're, I'm inclined to think we live in a universe where there's finally many things. It's a really large number of things, but it's finite. So it's, why can't I say that in my logic? And again, you might think this is telling us something about the nature of mathematics, not really about the nature of reality. Something about the nature of our thought process. All right, well, thanks so much for coming today, guys. I hope there was enough red meat, possible final exam questions.
Thank you.
Totally. I'll let you know if I figure out our little, proof construction to save its elegant nature. Otherwise, I'd have to retreat to this gimmick. We want to avoid gimmicks. Here I am, right? So it's like, I've been handling this all semester. Final review is what the people crave. I'll make sure you guys are on a good pile. That you're not on Santa's naughty list, we might say. And you're Jen, right? Cool. Got you, man. did check on my walk over here. It seems like 124 is the next lecture room over. So if you accidentally come to this room, it's not really a disaster. What would suck, right, is if the final exam was in a room that was like across campus, right? You showed up here and then you were booking it to, but I think, so, you know, it's a 3-hour slot. I don't think I'm gonna write the exam for 3 hours, so you guys should have plenty of time. And I'll probably write it for, because, you know, in the future, I think my typical final exam blocks would probably be 2 hours. So I might throw in some bonus questions for you guys, because, you know, MIT. So it might be like, you know, 2.5, but I don't think you'll need the full 3 hours, but, you know, my advice will be the same as last exam, which will be to slow down. I was really impressed. You know, often when I've said to people to slow down, take your time, students rush anyway. You guys actually did seem to genuinely slow down, take your time, which I think was really nice. So, you know, I admire that. That's definitely my attitude in the exam, just trying to relax, you know, think the clear thoughts. Do you guys have any general questions or concerns before we do a blitz of final review? Yeah.
So like on the midterm was like open note.
Yeah. So it's gonna go open note again.
Okay.
Yeah. And the only thing that wouldn't be legal is like, I don't know, if you're on like Logic Stack Exchange or some shit, you know, trying to like Google, you know, an explicit answer, you know, that wouldn't be legit. Yeah, everything else, so all the slides, the Carnap problems, any notes you've taken, you know, the book. I think in a sense, pretty much like any logic book, right? Because, you know, you could have been reading a logic book for fun the whole semester. So bring your laptop. I'll probably have scrap paper. That seemed to be popular last time, so I'll try to bring a lot of scrap paper, but bring a pen. I don't think I'll have pens. The world needs more pens. Trying to think what else. Yeah, so in terms of like the grading, so I think the final is 27% of the course grade. So the Carnap portion will probably be 13.5%, written 13.5. So basically, you know, you're gunning for the Carnap portion. Like last time, will probably boost your grade. So the Carnap portion is going to keep anybody from failing. You know, that's the dream. And yeah, so other stuff, you know, that could be relevant. I might repeat this at the end if other people come in. I don't think there'll be anything about trees on the test. At least no like tree derivations. I don't think you're gonna have to like have the tree rules in RAM. I might ask a question, kind of like a short answer question about what is the relationship between a complete open tree and the proof of completeness for STD, and the relationship between a maximally syntactically consistent set and the proof of completeness for a natural reduction system. So it might be something like, you know, describe the similarity between these two constructs. And it's a short answer in the sense like, if you get asked this question, basically the gist of it is, you know, in the tree case, you use the complete open branch to construct a truth value assignment that makes true everything in the root of the tree, satisfies the root. And in the natural reduction case, you use the maximally syntactically consistent set to construct a truth value assignment that makes true everything in your premise set. So, you know, so it might be a little short answer question like that, just to keep you guys honest on, you know, the meta logic for trees. But I think there's enough more interesting written questions to ask people than to check that you guys can do a tree derivation again, you know. So rest in peace, trees. Oh yeah, I gotta go on full screen. Full screen this sucker. All right, so basically our game plan for today, we'll see, you know, how much we get through. We'll do a practice problem for soundness proof for natural reduction with an alternative rule. So it'll probably be a question like that. We'll do some sample problems of applying the soundness and completeness theorems. There'll probably be at least one question like that. Again, it's really, you know, short. This thing, especially applications of soundness and completeness theorem, they're pretty short, you know, arguments. And then we'll probably do an alternative case of the membership lemma. So that'll be a sample of that. And then you basically go into the stuff that would be on CardNet. So we go into the schematizing sentences and quantifier logic. So problem set 8 didn't use anything about identity. Hey, how's it going, Manny? So what's up, Tim? So I feel like if I say hi to somebody, somebody else recently walked in, well then it seems rude, right? If I don't say hi to them both. So problem set 8 had no identity. It might be the case that on the CardNet portion I just mix those things together because, sentences are more interesting if you can use identity. So it might not be like a clean separation on CardNet between ones that use identity and ones that don't. So you just want to, know how to handle any kind of schematization question in quantifier logic. And specifically the things that I'll flag are know how to do only, neither, the counting stuff like at least and at most, exactly, and know how to do the definite description. There'll probably be at least one question, testing each one of these things. So make sure you have those in RAM. And then we'll have interpretation model stuff, which is like problem set 9, and then derivations. And what we might do is because I feel derivations probably trip people up more, so we might jump to derivations and then backtrack based on how much time we have in review. Any questions about this stuff? Cool. All right, so like with trees, we could modify S&D and put in new rules, and if you're trying to practice it at home, you can just take a case in the book and just start adding negation symbols in places, and then try to add more negation symbols to make sure the rule stays sound, i.e. preserves truth. So you just want to make the case that whatever sentences are accessible higher up in the proof would semantically entail the sentences lower down. So we can do an example like that, negated conjunction introduction. So I'll work alongside you guys for the sake of time. So this is a practice problem. Basically, imagine you had this on an exam. Your goal is to show, really the goal is to, figure out first, does this rule preserve soundness? If it does, then extend the proof by adding a case to our induction. If not, then give a concrete counterexample to the soundness of this modified system. Cool. And I think, yeah. So, strategy here is just like with trees, do a heuristic. Is it the case that the earlier accessible sentences semantically entail the final sentence? If so, extend the proof. If not, then you should be able to construct some concrete counterexample where you have a single turn style but you don't have a double turn style, and then you want to give that concrete counterexample. So anybody need scrappy work? Cool. So yeah, we'll just work on this and then we'll talk about it. So the first thing you do is draw a picture, obviously. So if you get, if you're totally stuck, you can look up what I'm doing and try to do it on your own, right? We're doing interactive learning, You can tell it's interactive because nobody's talking to each other. That's what we like in practice. not supposed to be looking here. You're supposed to be trying to do this from your own righteous heart. All right, so let's talk through this just so we keep moving. So first thing to do is just make sure you draw your picture and you label your lines schematically. Now probably on the exam, I'll probably give you guys the picture. The derivation just so everybody has the same line numbers, because that facilitates grading. I am the grader. So then, you just look at this and you notice, based on the deduction, you have some single turnstiles. The fact that you could legally write not Q on the H line means the set of open assumptions, gamma H, single turnstile is not Q. So you can just appeal to the gamma H, I'll know what you mean, I'll know that you mean the set of open assumptions or premises at line H. Then you can apply the induction hypothesis, make sure you explicitly say that you're applying the induction hypothesis, convert that single turnstile to a double turnstile. So gamma H now double turnstile is not Q. And then you're going to have to note some kind of subset relationship between the premises that are open at line k plus 1, which is denoted gamma k plus 1, and earlier sets of premises. And so here we see, okay, gamma H is a subset of gamma k plus 1, because everything that is accessible, gamma k plus 1 is also accessible the way I should put it, everything that's accessible at gamma at line H is also accessible down here. So this guy's a subset of the earlier guy. And so there's just this fact that if a subset semantically entails something, then the superset semantically entails it. Because whenever I make all these gamma k plus 1 guys true, I have to make all the gamma H guys true. Whenever I make all the gamma H guys true, by this relationship, not Q has to be true. So we can say, okay, the set of open assumptions at line k plus 1 also semantically entails not Q. So that's the key thing to do in terms of the turnstiles. So once you end up basically arguing that the set of open assumptions down here semantically entail the relevant bits up top, then you just switch to arguing about basically the truth tables. And essentially what we're saying at this point is, by a truth table, whenever not Q is true, the negation of Q and R is true. And there'd be a ton of ways you can say this. The way that I chose to say was just to say, hey, notice that this sentence is logically equivalent to not Q or not R, G. So just apply Morgan's, saying it's not Q or not R, and then notice that whenever not Q is true, of course not Q or not R has to be true because, this, you make one disjunct true, you make a disjunction true. So really, we could have done this is basically an OR rule, in fact, so, we could have put something totally insane here. We could have been like, let's put M, and not Q and M still would have been a sound rule, because this is basically a version of disjunction introduction. It's like negated disjunction introduction, essentially. So then you get to say, okay, whenever the gamma k plus 1 guys are true, not Q is true, whenever not Q is true, this not Q and R is true, and so line k plus 1 is righteous. It has the inductive property. And so you've extended the inductive proof, and you're good. Questions on this? Cool. So, the only wrinkles are like some of the rules involve multiple lines here, like conjunction introduction. The normal conjunction introduction has two lines, like a Q and an R. You have to cite both, apply the subset relationship twice. So, understand stuff like that. Cool. All right. In case you're totally lost on anything I said in the slides, I wrote everything out, not the actual argument for this case, but just the definitions and what you're doing. But I'll assume that we can press on. I will email you guys these slides from the review. If you haven't gotten these slides from me by 5 p.m. today, feel free to send me an email. It might mean I screwed up. So I might do it right after class. If nobody comes to office hours, or somebody does, but then I have to be present. I can't be only And then after office hours, I'm going to brunch in Boston with a friend. We're going to like a diner, so I'm pretty pumped about that because it's gonna be. I'm gonna get like you can get like insane French toast where like this isn't really like lunch food, this is like dessert basically. You go straight in for that. So that's what's going on, right? And I'm gonna try not to get any French toast stuff on my little reindeer. So I'm not sure how eating this is gonna work right. I'm gonna be like, I would like a bib. All right. So this is what we just did. Concretely. And yeah, if you're totally so this is really explicit shit. This is stuff I wrote out for people who are tracking this a lot less well than you guys. So it's in there. If you're trying to practice these kinds of problems, it's coming from section 6.3. You have most of the cases. We did, remaining case on problem set 12. There's also exercises. Problem 4 has variants of these things. So if you really want to get at practice, and you can think of your own cases. Again, I'm not out to get you guys, and so it's not going to be like something insane. It'll be, straightforward test of comprehension. All right, so applications of soundness and completeness theorem. So problem set 12, numbers 4 through 7, give some simple examples of applying soundness and completeness. So there's probably going to be 1 or 2 problems that are similar. They're typically pretty short. So the key facts to remember are these ones in terms of unsatisfiability. So if you're told that a set of sentences gamma union with not P is unsatisfiable, what can you immediately say? This happens. This is the case. What else is the case? Yeah, man.
Gamma could not semantically entail not P.
Yeah, so definitely gamma can't semantically entail not P. Is there something stronger we can say? Yeah, Henry?
Gamma entails P?
Yeah, gamma entails P. Yeah. So if this is unsatisfiable, then whenever the gamma guys are true, not P can't be true. And whenever not P is false, then P is true. So whenever the gamma guys are true, P must be true. So you get to convert an unsatisfiability relationship into a double turnstile. And now that you have a double turnstile, you could apply the completeness theorem, because the completeness theorem lets you convert a double turnstile into a single turnstile. So the trick is you might be given some information in terms of unsatisfiable sets. You want to get that shit in terms of turnstiles. Just like a carnival, right? The only way to get on the ride, you gotta go through the turnstile. So that's what we gotta do. So similarly, if you're told that gamma semantically entails not Q, what else could you say in terms of satisfiability? What set union what is unsatisfiable? If you're told this. Yeah,
Q is unsatisfiable.
yeah, so gamma union Q in this case is unsatisfiable, and vice versa. So you can you move back and forth between these. Basically, just remember, if you have gamma union not P is unsatisfiable, you drop the negation sign when you go to the double turnstile. And this is stuff, in principle, you should be able to give these arguments by the heart. Yeah, what's up, Luna? So yeah, Luna, as I said to all these fine people, if I hadn't sent you the slides by like 5 p.m. today, feel free to shoot me an email. It means I probably screwed up. So, all right, cool. So let's do some examples of applying soundness and completeness. And just to be really concrete, we'll focus on sentences from QL, although everything's schematic here. It doesn't really matter. And we'll let the single turnstile be in QND. So you'll probably have a sentence like a problem like the following, which will be prove or provide a counterexample to the following statement. So you're told if it's the case that gamma semantically entails a sentence P and delta derives Q, then is it the case that the union of gamma and delta derives P and Q? So I'll work through this with you guys. Does anybody need scrap paper? Cool. call you, yo, how's it going? Cool. I'll put you in the good pile and ask you. If I haven't sent you the slides by 5 p.m. today, shoot me an email. It means I screwed up. Hopefully that's not the case. Sorry, so let's run through this. So I've been a little pedantic in writing this out, probably more pedantic than necessary, but you know, we're illustrating all the good stuff. So by the completeness theorem, we can convert this double turnstile into a single turnstile and say gamma derives P. Now what that means is that there's some finite natural reduction, so it means there's some finite subset of gamma, call it gamma prime, such that you could write the gamma prime guys and you could get P from it. So that's technically what that means. You know, you haven't been told that gamma is finite, so gamma could be infinite. And so in that case, you know, technically you'd have to note that, okay, there's some, you know, finitely many premises gamma prime from gamma, and likewise, you're told delta, you know, proves Q, so again, there's some finitely many delta prime guys from delta, such that from the delta prime guys you can get Q. And so you can get one deduction with the gamma prime, the delta prime, get P, get Q, and then by and introduction, you could derive P and Q. And so then you basically get to note this finite gamma prime union delta prime is a subset of the possibly infinite gamma union delta. And so by definition, this possibly infinite thing derives P and Q provided there's some finite subset that derives P and Q. And so here's our finite subset that derives P and Q, and so the answer is yes. So I didn't totally finish out, you know, saying here I should conclude by saying therefore, you know, gamma union delta, single turnstile, P and Q. So, questions about this? All right, let's do another one. So if gamma single turnstile S or R and gamma single turnstile is not S or R, prove or provide a counterexample that gamma semantically entails S. So again, try to do it on your own. I'll be working alongside you. You guys don't know that you need scrap paper? I have to ask that just because new people. I have to be polite. All right. So, you see a single turnstile, and the question's about a double turnstile, and so you're thinking we're going to convert the single turnstiles to double turnstiles using the soundness theorem. So, you just have to note, okay, by the soundness of our induction system, gamma now semantically entails S or R, and gamma also semantically entails non-S or R. Now, these are both a contradictory sentence pair, and so you would have some set that is essentially entailing a contradiction. And so any set that semantically entails a contradiction must itself be unsatisfiable. You know, if I'm a set of sentences and whenever I'm true, P and not P is true, well, P and not P is never true. So the only way it's possible for the claim, whenever I'm true, P and not P is true, for that claim to be true, I have to never be true. You know, it must be the case there's no truth value assignment. That makes me gamma true. So we basically could say, okay, gamma's unsatisfiable, and so an unsatisfiable set surely entails anything. Another way to think about this in terms of our unsatisfiability relationships is that if gamma is unsatisfiable, then the union of gamma with anything else would be unsatisfiable. And so gamma union the negation of S would be unsatisfiable. And based on those, you know, conversions we just went over a couple slides, you know, before, this again would mean gamma semantically entails S. So really, again, I could have written anything here, right? It could have been any sentence, and those statements were true. Questions about this? Cool. All right, so I think I put 2 more examples in here. I think for the sake of time, I'll just leave these in the slides for you guys to practice. So that, you know, this is one illustrating the rule we went over. If you're told something like this, gamma union not P is unsatisfiable, think to yourself immediately, okay, cool, I can get a double turnstile. So gamma double turnstile is P. So whenever gamma is true, then P is true. Here applies soundness. Whenever delta is true, R would have to be true. And now you're like, okay, is this thing true? And you're thinking, well, you know, it doesn't look good, right? Because whenever the gamma guys are true, P is true. Whenever delta is true, R is true. This thing, not P if and only if R is true, only when P and R have different truth values. So now you think, okay, there's probably a counterexample. You'd have to give concrete sentences. You'd want to think, what are the simplest ones that'll work? You know, a single sentence is still a set of sentences. So here, the simplest counterexample would just be, let gamma be P and let delta be the sentence R. And that would be your counterexample. You just want to explain that. All right, so we press on. Yeah, so stuff in the slides. If you're totally lost, feel free to review this. And solution tips for logically complete students, which is what we're all aiming to do. We can always, you know, I'll remind you this, pray for a stroke of insight. Look to the heavens. All right, so let's do membership on the case. So in the completeness proof, we have these 5 membership one-off cases, A through E, and they're each motivated by you know, truth tables for the connectives, or 5 connectives, but they're totally, you know, syntactic statement. And so just like with, you know, modified completeness rules, modified rules for soundness, we can examine modified cases of these membership lemmas. And so here's one, for instance, modified case E, not P if and only if Q is in our maximally syntactically consistent set, gamma star, if and only if either both P is not in gamma star and Q is in gamma star, so, you know, they disagree on the membership, or the other way, they could disagree on the membership. And you think, okay, yeah, this is going to be true, you know, for the same reason the normal case is true. We're just mirroring truth conditions. Not P if and only if Q is true, only if these things disagree on their truth value assignments. Gamma is syntactically mirroring truth value assignments. But again, you know, if you were asked this case, this is probably too complicated for me to ask you guys because it'd be too long. You know, you have 2 directions for this, the if and only if direction. And then this is 2 cases, and so in each of those forward backwards directions, you would have 2 cases. And they would involve some deductions. And probably at least one of these deductions would suck ass, right? So if I ask you a question, I'm going to make sure that the deductions involved aren't totally awful, because I don't want to, you know, destroy anybody's hopes and dreams, right? Not from the membership lemma. So again, if you're trying to practice this kind of thing at home, you can just look at our existing cases, start adding negation signs, and see, okay, what kind of membership relations would have to hold in order to get a modified rule. And you end up using the door lemma. And remember, you got to do 2 directions, forward and backwards. So first you assume the thing on the left, and then you derive the thing on the right, and then apply the door. Second, you assume that the claim on the right is true, and then you derive the sentence on the left, and again apply the door. And sometimes these cases involve subcases, and so you have to know that. And they often involve some non-trivial natural reductions. And if it's a non-trivial one, you gotta write it out, actually show the steps. And don't mention truth value assignments because there's nothing to do with truth value assignments. It's purely syntactic. So let's do, okay, so here I think I just collected the membership lemma so that we have the cases. And the one, so I'm probably not going to ask you to prove a variant of case A, and so you'll be able to appeal to case A, take for granted that it's true. So case A, super useful one, not P is a member of gamma star if and only if P is not in gamma star. So, and likewise, P is in gamma star if and only if not P is not in gamma star. Where I probably should remind you guys, this gamma star thing, this is a maximally syntactically consistent set. So it's a set of sentences that is syntactically consistent. You can't derive a contradictory sentence pair from gamma star. There's no sentences of the form are and not are such that gamma star derives them. And it's maximal in the sense that if you were to add in any other sentence to gamma star that's not already in there, then gamma star, the union of that thing you added, would be syntactically inconsistent. And so that's the way you would prove the first case. You're basically going, well, if P is not in the club, then adding in P, the gamma star union P would be inconsistent, so I could derive a contradictory sentence pair, so then I could do negation introduction, and I could derive not P via negation introduction, and then apply this Door lemma, which hopefully I put somewhere. All right, so maybe I put the Door, we'll do an example, but just to remind you guys of the Door. All right, so here's definition of maximally consistent. I just said verbally. All right, here's our Door. So this is the key thing that you'll use to handle these cases. If you can derive a sentence from a subset gamma, where it's a subset of a maximally syntactically consistent set gamma star, then S is a member of gamma star. So basically, Door. We have a gamma is a subset of a maximally, gamma star, maximally, I'll just say syntactically consistent set. Then, if gamma derives some sentence S, then S is a member of the club of the maximally syntactically consistent set. So this is the result you'll use in these membership cases. Yeah. All right. So strategy is just figure out how to derive the stuff you're interested in from the sentences you've assumed to be in the maximally consistent set. So let's do an example. So let's do modified case B. So in this modified case, we're saying P and not Q are in gamma star if and only P is in gamma star and Q is not in gamma star. So let's try to work through this. I'll be working through it as well. But try to do it on your own without looking necessarily what I'm sprawling on the board. Do you guys have any questions about this before we do the example? All right, cool. So yeah, try to set this up yourself. And remember, I was lazy here. These bold P's and bold Q's, these could be anything. So really, I should be using the script P's and the script Q's, but I took a lot of this stuff from a previous final review thing I had made where I hadn't started using the script notation, so I was using the bold, so we stuck with the bold. We're bold today, we might say. chill example, probably the problem on the midterm will be a bit more involved than this one. This is probably the easiest example one to give. So we basically know, the forwards direction, backwards direction. In the forwards, we assume the thing on the left is true, that P and not Q is in the club gamma star. And then we just note, okay, there's some syntactic rule we can apply, and elimination. And by and elimination, P and not Q derives P, and P and not Q derives not Q. So if you were formally writing the deductions, you would have a deduction with the sentence P and not Q, and then later sentences P and not Q. And then, you'd say :1 and elimination, :1 and elimination. So, but since it's so obvious, in this case, you could just write this because, it's a single rule, and so you don't have to draw the picture for a single rule. If it's like multiple steps, then you got to draw this thing. As you saw on the homework for OR, the OR rule, case 3, one of the deductions is around 9 lines long. So I'm not gonna take it on faith if you say, oh yeah, I saw in my head, that these sentences, derive these other ones, that the thing's 9 lines long. Some of you, it might actually be the case that you saw the whole thing in your head. You gotta prove it to me. So you gotta draw that shit. Because I can't read your mind. I don't even know if you have a mind. You might be zombies for all I'm concerned, Okay, so then we have P and not Q derived from a subset of gamma star. So then by the door, since P and not Q is a subset of gamma star, P is in gamma star and not Q is in gamma star, then that case A, Q is not in gamma star. So we show the right-hand side by assuming the thing on the left. So we do backwards direction, assume this is true, so assume P is in the club and Q is not in the club. Then again, by case A, not Q is in the club, and so we have a subset of gamma star, namely the set P, not Q, that derives P and not Q, namely by and introduction. So here, this other deduction, you basically have P, we have not Q, and so then we do Pn not Q by lines 1 and 2 and intro. So again, super chill. And then we apply the door, and so we have to say P and not Q is in gamma star, which is what we want. So this is schematically what goes on. Now it gets a little bit more complicated when you have to know cases, like in something like case C, you have to, at parts of the proof, basically be like, well, either P is in the club or P is not in the club. If P is in the club, well then this right-hand side would be trivially true. So now let's handle the case where P isn't in the club. That would be not P is in the club. And we'd also, then you'd have to derive this thing in either scenario. So that's a bit more involved, so know how to do that. And yeah, also this case D is a good one. So the case D is for the conditional. I say the conditional involves 2 deductions. One of the directions involves 2 deductions that are both not trivial, but they're not insane. They're not super long. So there's a good chance that the problem will involve the conditional. So I say study the conditional case. If you can do case D and you understand it, then you probably could handle a modified case. So that's my advice to you guys on membership lemma. Oh yeah, and the thing to note as well, if you're studying this, there's a typo in the book that I meant to note in the PDF, that line 2 of this deduction should be : assume for conditional introduction. So, or : as for conditional introduction. So I think it writes like negation elimination or something, which is insane. So, don't write that. Questions on this? Cool. You're now all officially in the club, we might say. We're all in the club here. All right, so cool. All right, so now we have like 30 minutes for the Carnap stuff. So that's cool. And I say, just to make sure we hit it, let's jump to natural deduction, which is probably everybody's best friend, right? So, derivations. thought about wearing this thing to the final, but then I was like, I'll be jingling right as I walk around answering questions, and that could, just like people coughing or sniffling. Sniffling is one of the worst, I think, during exams. Or the pencil clicking, you know? I don't want to contribute to somebody's exam anxiety misophonia, right? So I will make sure that I bring tons of bananas and that I'm eating a banana, you know, at every minute of the exam. That's also a very annoying sound, you know, it's like, that's the banana sound, right? Which is, you know, you're on a plane and that's all you hear, that's pretty, yeah, well. All right, so yeah, general tips on this stuff. So yeah, so if you can do this stuff on prompts at 10, you're probably in really good shape. So you can do that stuff cold. And there's a practice version now of prompts at 10, so you can, you know, test those out to your heart's content. Again, I'm not out to get you guys, so I'm probably not going to ask anything that involves like, you know, like 3 or 4 subproofs deep. You're assuming, you know, like stuff that's really counterintuitive, you know, requires like great leaps of creativity. It'll be some creativity involved, but not like, you know, great leaps because this is a timed exam. So it's like, I won't put a derivation question on that I couldn't solve myself cold without like, you know, really thinking about it. So let's see, yeah, so the main things are make sure you understand existential elimination, make sure you understand universal instantiation. Those are the 2 rules that have constraints on them, non-trivial constraints. That you gotta follow the, you know, for existential elimination, it's like 3 things you gotta follow. 1, if you use, you know, slightly easier, but, you know, stronger than necessary constraint. And then I love conditional introduction. It's great to test people's understanding. Conditional introduction throws people, but you know, it's super important. We're doing modus ponens all the time. If there's one thing you walk away from this class with, you should be, you know, modus ponens for the rest of your life. Where modus ponens things, you know, are ways to financial security. That's it. Yeah, I might mention this to the finals. I said to some people on Monday. My main life advice to you guys is, as soon as you are fiscally stable enough, start saving for retirement. Anything to compound interest. And I meant to say this on Friday. This isn't like, you know, save in a bank. You know, most bank savings rates suck. This is, you want to be in like mutual funds. So you want to be like, you know, when you're relatively young, you know, you probably want to be like pretty aggressive, like at least, you know, like, I don't know, 80% stocks in a mutual fund. So like, don't buy like individual stocks because that can be risky. As somebody who bought some Coinbase stock and then, whoa, man, Coinbase went, I lost some money on that. So, you know, don't do shit like that unless you're really playing around. You know, you want to have, you know, most of your retirement savings in mutual funds where, yeah, it's going to be, you know, volatile, but this is like 40 years out, you know, so in the long run, you'll get a way greater return. You know, assuming induction, right? We all have faith in induction. You know, it is possible, you know, the American market could become like Japan in the 90s and you could have awful growth for like, you know, a decade or 2. That could happen, but you know, we take risks. I'd rather not have to work my ass off when I'm above 70 and have a nice cushion, so it's a, you know, risk I take. So that's one of my main life advice things to you guys. Sponsored by Modus Ponens in some capacity, right? Modus Ponens plus induction. Cool, so tip, if you're gonna do existential elimination, you typically wanna start your proof of that. So once you've copied the premises, the first non-premise line you want to do is existential elimination. That starts a subproof, and you want to work within that subproof basically for as long as you can until you get the stuff you need. And that is the least risky thing to do to follow the rules for existential elimination. All right, so let's do an example. And I was going to use it on the board, but then I was like, you know, we don't really handwrite these in this class, and so probably electronic practice is better. So if you go on the Canvas page, you can get to, let's see, I linked it in our famous week 14 module. You can go down to week 10 practice problems. And so at the very bottom of week 10 practice problems, I put 3, so I'll bring you to this page, practice stuff, proofs. And at the very bottom, I put in 3 practice problems so that you guys can practice these. And you know, obviously, if you don't have a computer with you, you can do handwriting, which is what I would have done if I hadn't had the mental fortitude late last night to think that would actually be kind of, you know, possibly a waste of time to be handwriting these, because we're computer people for Carnot derivation. So I'll work through this as well, but I'll mute my screen so that you guys don't see what I'm doing, and then we'll talk about it. Oh shit, I don't want to have to mirror. Too muted. I don't know if I could, I mean, in principle, right, I could type this, you know, on a totally blank screen, but I don't think I remember the sentences. All right. Duplicate. Cool. Yeah, on the final, you're going to have to do natural reduction blindfolded with one hand tied behind your back. So this is, a relatively short one. I'll probably try to keep any problem on the exam less than 12 lines. So probably 10 lines will be the longest thing. You'll see this one's 7. So, it's always good to look at the sentences and just assess what they mean. Because if intuitively you see why it's true, then that, will help you with proof strategy. So here we're saying, all right, there's something that's a Q, and everything is such that if it's a Q, then it's a P. So this means every Q is a P. Well, here's something that's a Q. If every Q is a P, then whatever over here is a Q would have to be a P. And so there'd have to be at least one thing that's a P. So intuitively, this makes sense. And so we think, all right, we're going to do an existential elimination on this guy, and we're going to eliminate a universal on this. And then put it together, and then we'll have to build up. Here the main connected is an existential, so you think I'm going to have to do existential introduction to build up this guy, and then ultimately have to finish the existential elimination. So following our pro tip, when you see, okay, there's an existential, and you think I'm probably going to have to do existential elimination, make that your first step in the proof. So we assume an instance for EE. So remember, you don't get to write like the instance for QB and then justify by EE. This is an assumption. You're assuming an instance for EE, and then the thing you have to do is follow this rule schema where here's your existential, you assume an instance of it, you derive something psi, where inside you don't have the free instance. So the free thing, in our case B, we instantiate B. B cannot occur, little b cannot be inside. Then you get the psi within the scope of the subproof, and then you write psi again, right outside the subproof. And that's when you justify it with existential notation. We got our QB. Now we, eliminate the universal using B. Because you can eliminate this universal for anything, little a, little c, little d. Well, we instantiated B, we want these things to be connected. So we'll use B again. So if QB then PB, now by conditional elimination on lines 3 and 4, you get PB. And now you're like, cool, I got PB, but you can't pop out of the subproof yet because B is free in PB. So we need a sentence that doesn't have the free B. And so we instantiate it. So if we have the thing we want on line 6, but it's in the subproof. So now, little b doesn't occur, so we follow the 3 restrictions on existential elimination. So we write it again now, not in the subproof. And that's where we want. And then we cite 2 things. The line that started off for our existential, and the whole subproof lines 3 hyphen 6. And remember, subproofs need a hyphen. Hyphen, from the starting line of subproof to the final line of subproof. And then you write the rule. And my advice to you guys is always, when you do a subproof, I count by tab. So start a subproof, I press tab once, and then whenever I start a new line, I press tab however many times to get to the right subproof level. So if I was, 2 layers deep, I go tab, tab, blah, blah, blah. And then to stay in that subproof, I go tab, tab, and then, I stay in the subproof. So we're thinking to ourselves, any questions about this one? Cool. I really want my green check mark back. Yeah. All right. Let's do another one. So this is one of our fun little conversion relations. And remember, you can always, to start, you can always just copy the starting premises, paste each starting premise in, and then write colon PR. That can save you, a little bit of time. Cool. All right, I'll mute again so that I do not corrupt your QND intuitions. So again, it's pretty short. In principle, this one is definitely trickier. You just want to follow the tips. You know, it's a good illustration of how if you just stick to the plan, it works out. And so the plan is basically, you're going to have to build this thing up. The main connective is a universal, so you think the last rule I do is probably going to be a universal introduction. Now, what are you introducing a universal on? You're introducing a universal on a conditional. How do you get conditionals? You build them up by a conditional introduction. So it's a good illustration of how, you know, if you get something that's a quantified conditional, you're probably going to have to, you know, do a conditional introduction pretty early on to start building this guy. So if you're going to do universal introduction, well, you can't build it with a GX. GX is not a sentence. You're going to have to pick some constant. So I picked B. And I picked B because B has not occurred yet, and it's always safest to, you know, use a constant that hasn't popped up yet. So I assume GB for conditional intro, and then I'm like, great, I can introduce an existential. Now I convert it to an X, because, you know, keep the sentence. There's an X, GX. This is, fortuitously, the antecedent of this conditional. And so now I can apply conditional elimination, and I can get FA. And that's basically what I wanted. I wanted to go from an instance of GX. So I'm going to go from GB to FA, and then I get my conditional that I wanted to build. If GB is an FA, to -4, remember the hyphen, conditional intro, and then I can check that I have obeyed the rule for universal introduction. It has to be the case that a little b doesn't occur in an open assumption of line 5. And I look and I say, okay, the only open assumption is line 1, and there's no little b in line 1. So this would not work. If I had used A here, if I instead had assumed GA, and then I had if GA then FA, I would violate the constraint on universal introduction. And Carnap would say, no way, hombre, and it wouldn't give me the green check mark. But, you know, I satisfied the condition. It's basically this first condition right here, provided that the constant C does not occur in any undischarged assumptions that phi is in the scope of. Here my phi is GD, this guy, here's my phi. If GD is an FA, and little b is not in an undischarged assumption of line 5. Sound good? Apply for all introduction, and we got it. Questions on this? So it's very short, but it is, you know, it's tricky in a way. Like, I think, you know, a lot of people screw this up. So there might be an analog like this problem. So, you know, basically know how to do for all introduction, know how to do existential elimination. And often, the key thing to remember really is like in this problem, often to do existential elimination, the penultimate step before you pop out is an existential intro. You do an existential intro to get rid of the free constant. And now, you know, the free constant doesn't occur in the last step of the subproof, and then you can pop out. So that's, you know, a thing that people often forget to do. All right, so there's another, so yeah, the other direction is definitely trickier. This is probably too tricky, then it's something I'd ask you guys to do on the exam. But if you want to, you know, practice it, you can. I think for the sake of time, we will press on to greener pastures, you know, like our green check marks. So let's see, we're back in slide review land. All right, yeah, so we did one of those. So yeah, I put some more advice in here that you can read, you know, to at least, you know, give yourself the illusion of studying, right? But, you know, the main thing is just to be able to do these problems. So yeah, so, you know, more specific advice. I probably said most of the stuff verbally, but feel free to read that. I think there's more advice in the week 10 slides, probably as well. But I think it's too easy to have a false sense of security of like having read the advice and be like, oh, I understand the advice. The main thing is test that you can do problems. That's the main way to study this kind of thing. All right, so I think we can burn through the interpretation stuff real fast in terms of just advice for you guys. So my main advice is to look at problem set 9, make sure you can do problems like 9, 10, 13, 15, these guys. So that's my main bit of advice. Know the syntax to put it into Carnap. And yeah, so understand what it takes to make an existential true. There has to be at least one object in the domain that satisfies, the substitution instance. And for a universal, every object in the domain must satisfy, the relevant statement. And then the key thing to watch out for, if I'm going to be tricky, and I probably will put on at least one or two questions that will be a little bit tricky. They won't involve like an insane model, but like they will have embedded conditionals. And remember, conditionals have counterintuitive truth conditions, and a conditional is truly true whenever the antecedent is false. So whenever an object, doesn't satisfy the antecedent, that object will trivially make the conditional true. And so that is something to watch out for. Yeah. Cool. And then I think, I just put in review stuff. All right. So cool. So we got that. Any questions on interpretations? All right. So let's do the translation stuff. So just have this in mind. So there probably won't be specifically sentential translations, but quantifier logic is an extension of sentential logic, and so the same constructions can appear now as well as quantifiers running around. So some of the ones that are easiest to forget from sentential logic I've put on this slide. So remember that P only of Q doesn't change the order of the P and the Q. So P only of Q is the same as if P, then Q. And mnemonic for this, at least for me, if you're as high on your own supply as I am, then I think, okay, P only of Q. Well, that means if not Q, then not P. And if not Q, then not P is the contrapositive, which is logically equivalent to P and Q. So that's how I always remember this one. If in my mind I start to have doubts about, shit, is this the case where we flip them, or is this the case where we don't flip them? From through this argument. Unless you're really losing your mind, in which case remember or unless. So unless B comma C, equivalently C unless B, just use or. Don't try to do this in terms of conditionals. You'll probably screw it up. I screwed up if I try it in terms of conditionals because I think that this schematization is bullshit. But this is what we're doing. So it's or. Arbitrary rule. Just like at your job, you're gonna have arbitrary rules. Just one of them. J just in case K. So just in case I'm not kidding, this is J if only if K. JK. No JK. I really mean it. I'm serious. This is for real. J if only K. So just in case is the biconditional. Weaker than the biconditionals provided that and given that. So I often screw up provided that, and I think of provided that as the biconditional, but it's not. Provided that is just if P then Q. So these are the ones that flip the order. These are the tricky guys. The lonely if, the if all by its lonesome self, Q with P is if P then Q. Q provided that P is if P then Q. Q given that P is if P then Q. So those are, I think, some of the trickier ones. Questions about these? Cool. All right, so we have some simple examples, which we can go through if we have time. So these are ones, they don't involve identity. Everyone who went to Disneyland knows someone who didn't go there. So basically, you'll be given a domain, which will probably be people, maybe some other things as well, and then some predicates, and then some constants and names, J for John, M for Mary. One thing that could trip people up a little bit is I think I'll be pretty inclined on the exam to give a name for yourself. So I might stipulate that little u stands for yourself. So little u will be a name of you. You personally. So for me, little u is a name of me. For you, little u is a name of you. And the things that I think probably will happen when I do this, and I'm going to regret it, are people are probably going to start writing y's instead of u's, but y is a variable, so y is not a constant, it can't be a name. Little u is not a variable, so it can be a constant name. So think about that. I think I really want to have you guys schematize the sentence only that which is truly you has the power to heal you. And which basically means only you can heal yourself. So that sentence. So it's an only sentence. Only you have the power to heal yourself. And to do that, we needed a name for you. So that's just to give you guys a heads up. Because it's a lot to process. There's going to be a lot of words on this exam, right? And so it'll be pretty easy to just feel disoriented. All right, so go back to these examples of time. So remember only Greta is a hero. And so this just means no one other than Greta's a hero and Greta is a hero. So you gotta say two things. So you're saying for everything in the domain, if that thing is a hero, then that thing equals Greta. So this is the no one other than Greta part. And then you also have to know Greta, by the way, is a hero. So think about how you would modify this to be the sentence, only you can heal yourself. It'd be the same, the same structure. Okay. Or you can do this biconditional thing, which, because I told you guys about this, I'm going to type this shit in Carnap, because Carnap doesn't view these as logical equivalent. Probably because, predicate logic is not decidable. This one should be decidable, though, because this is monadic, and monadic quantifier logic is decidable. So I don't know what's up with that, Carnap. All right. Neither, or neither, neither pronunciation is standardized, we might say. So neither hero inspires. This means that there's exactly 2 heroes. So this is a thing that's easy to forget. It's this very specific claim about how many heroes there are, and then it's also saying neither of them inspires. So the neither of them inspires part, that's easy. It's just not the case that X inspires, and it's not the case Y inspires. The exactly 2 part is trickier, because you're basically saying there are at least 2 things. You have to say they're different, so you're saying not X is equal to Y, and then you have to say they're both heroes. So here we said, at this point on the first line, we've said there are at least 2 heroes. There's an X, there's Y, they're different, and each of them is 0. So this first line is there's at least 2 heroes. Now we have to do the exactly part, which is for any other thing Z, if Z is a hero, then Z is either X or Z is Y. And then you note that your 2 heroes are not inspiring. So, this is totally harder to remember, so just have this in RAM. If you write a little cheat sheet, have this on your, again, it's open book, but you might feel free to have some quick access notes. And if you do that, I'd recommend putting something like this on it. All right, so at least then, we basically just did an example of that. The only trick here is, if you're told something like 3 heroes are inspiring, this just means at least 3. So, unless you're explicitly told, it's exactly 3, it just means at least 3. I don't think I'm gonna do one like this, because I feel like this is a convention and it's just needlessly tricky, and I'm not trying to be needlessly tricky. All right, so yeah, at least then, blah, blah, blah. Okay, at most then. So yeah, so this is another one that you could get tripped up on. So at most, the easiest way to schematize this is it's the negation of at least n plus 1. So if you're saying at most 5 people are crooks, you're saying it's not the case that there are at least 6 crooks. That's what you're doing. And that I think is the easiest way to do it. So if you had a sentence like, at most 1 person who knows Mary doesn't know John, you're basically saying it's not the case that there are at least 2 people who know Mary and don't know John. So it's not, so you know how to do at least 2 people. There's an X, there's a Y, they're different, and X knows Mary, Y knows Mary, and it's not the case that X knows John, and it's not the case that Y knows John, and then you just negate that whole thing. So that's the at most. Oh, yeah. Definite descriptions. So another thing, easy to forget, something like Earth's moon, this just means the moon of Earth. So if you get asked something like, Johnny's soul means the soul of Johnny. And so it's a definite description, and you handle them by saying there is something, namely, a moon of Earth, then it's the only. So you're doing the only construction again. So for anything else, if it was this thing, if it was a moon of Earth, it would have to be the first thing. And then you're also saying, of that thing, the thing that's the only A, it has this property B. So it'll probably be at least one schematization with the definite description on there. So yeah, so quantifier logic, there is an x is an a, and for all the y's, if y is an a, then x equals y, and we get x. So, cool, all right, and then we have some examples. So that's basically, you know, all the stuff to have in RAM. And then I think you guys should be in great shape for, you know, the test. There might be some other, you know, proof questions, but it's like if you can't do, you know, a single, you know, like written proof question, it's not the end of the world, right? Like my main advice to you guys is don't get bogged down on a single question. If you can't solve any question within like, you know, 5 to 10 minutes, just, you know, write your scrap work, which I'll see and give partial for, and move on to the next question. Make a note to yourself to come back in time. So that's, you know, strategy. Do you guys have any questions about this? Cool. Thanks so much for a wonderful semester. It's been great having you all in class. And so I'll look forward to seeing you guys on Monday for the final, and I have office hours after class and on Friday. So. And again, if I haven't sent you the slides by today, then